Sure. Yeah, go ahead, please.
Right, so, okay, I'm going to assume that there are people here. See this? And I'm just going to pick up from where we left off yesterday. So I'm still at home because I'm still faintly testing positive for COVID. So fortunately, I'm not there again. But still, I can lecture fine. So yesterday, we finished up seeing a convergence proof for gradient descent. It was under these sort of rather strong assumptions of saying that the total training optimization problem was strongly convex and smooth. And we showed this kind of linear convergence result. This is sometimes called exponential convergence because you are exponentiating, well, highlighted. Well, there's a t here. You're exponentiating a number to the power t, so you're contracting at an exponential rate. Here, but in logarithm terms, it's linear. So we did the proof, which was just 2 slides, I think. Yes, just these 2 slides. Obviously, still hard to follow proof on slides, to be honest. So I'm actually going to not do any proofs like this anymore, since this is our last lecture. Instead, I'm just going to let you know that you can still show convergence of gradient descent. This is, again, the exact same method from an iterate WT. You take a step in the negative direction, the gradient, and I'm using a step size that's exactly 1 over L, where L is the smoothness constant of the function, in other words, the Lipschitz constant of the gradient. In this case, you still converge, but now it's the difference of the function f at WT minus the function at W star. So you want this to contract to 0. And this is less or equal than a constant. All this is a constant, 2L times the initial distance to the optimal point divided by t minus 1, where t is the number of steps. So as you take more steps, this thing is decreasing. But this is a sublinear convergence, 1 over t. The proof for this is significantly more involved. I won't do it. The only thing I will say is just something odd. If you want to get the right proof for these things, you can't use just convexity or just smoothness in isolation. You have to design a property that is a perfect combination of both of them. This is kind of odd, and it escaped people for quite a while. And it's called something, I'm just going to name it, it's called Co-Coercivity. And you can prove weird bounds like this thing here. So you can see something going on that looks a bit like a bit of convexity here, because you can show a relationship between the function, its linearization, but then just something else, difference of gradient and norm squared. I'm not going to do this proof here, but this is you can get these kind of new lemmas or these new bounds by figuring out how's the best way to combine convexity with smoothness to get the tightest upper bound possible. But I'm not going to do that because it just takes too long and it's too, I don't know, it's too detailed and gritty for slides. So I'm going to leave the slides online, and I'm not going to show you this proof because it would just take forever. Okay, and now I have a passing fact I want to share with you all, which is a bit less ML, machine learning, and a bit more of an obsession of optimizers. This is actually a real obsession of optimizers, almost unnaturally so. And I just wanted to share just a little bit of this. It's called acceleration. Now, acceleration is a way that you can formally show and make gradient descent much faster in terms of convergence. And the trick is you have to add another sequence of iterates. So if you look here, this is the algorithm, accelerated version of gradient descent. And here you can see the same old WT as we had before. And here we have WT minus a step in the direction of the gradient. But now we store that result in a new variable, yt plus 1, and we compute wt plus 1 as a strange extrapolation between the yt's and the wt's. Now, this is particularly weird to see and hard to understand, and a lot of people spend their careers actually just giving interpretations to this. There are many interpretations. None of them are really super intuitive. They're all a bit odd. But you do this just the right way, you can prove things like this. You can prove that instead of having a convergence rate of 1 over 1 minus mu over L, you're going to get the square root of that number. So I have to define a kappa, which is now L over mu. And the convergence rate is going to be 1 minus, well, 2 divided by the square root of kappa. This is actually an entire order of magnitude faster than the previous algorithm. And what this theorem says, and what this obsession that optimizers have, is that not only can we prove that gradient descent is faster by incorporating an extrapolation step, but we know it's the fastest possible algorithm that fits these assumptions. So what do I mean by these assumptions? So Nesterov showed that for any optimization algorithm, any one you can possibly imagine, if the iterates Wt plus 1 are a combination of the previous iterate plus anything in the span of all the previous gradients. So you can use any gradients from past iterates in any way you like, as long as you linearly combine them. Then there exists a function that is smooth and strongly convex, for which the difference between FWT minus FW star is greater or equal than this convergence rate. So this is the exact opposite of what we've been showing. We've been showing that the difference between FWT minus FW star is less or equal than something that's collapsing to 0. But this is actually a lower bound. This says that nothing can be faster than this rate of convergence, this 1 minus 1 over square root of kappa to the power t. And it just so happens that accelerated gradient descent, this strange method I showed before, achieves that exact rate. So this is obviously very hard to digest, and I'm not going to go into details of this either. I just wanted to let you know that this is a side obsession of many optimizers, is to come up with lower bounds, show that there's a fastest possible rate for any algorithm, and then find that algorithm that achieves that rate and prove it. And sometimes these algorithms actually work super well. In fact, accelerated gradient descent is an example of a method that works extremely well, but not in the stochastic case. So not so interesting for machine learning. Okay, so that's my weird caveat into just some random optimization knowledge, which is not going to be used for the rest of the slides. Any questions, or are there too many questions because this is too technical? I can't hear anything in case anyone's saying anything. Or maybe it's just this silence.
So when you're like putting, or when you're talking about like smoothness and convexity, those constants, like you're putting them kind of like in front of the gradient, like to multiply the gradient. So it's kind of like a learning rate, like in the previous slide. You have
Yes, it's exactly a learning rate.
So like learning rates are kind of dependent on the smoothness properties and convexity. So when we pick learning rates, are we effectively like trying to figure out the geometry of like your loss surface? And is there like kind of principled ways to do that?
Yes. Okay, good question. Actually, it's just a smoothness constant. It doesn't depend on convexity, the step size. This same step size also works for some non-convex things as long as it's smooth. The reason you choose a learning rate for this exactly 1 over L in terms of geometry, I have two ways of saying this. In terms of geometry, it comes down to what was the smoothness lemma, the descent lemma. Descent lemma, we showed that if you minimize the quadratic smoothness, says that your function is upper bounded by a simple quadratic. So you know that there's an up bowl, tangential bowl sitting on top of the graph of your function. And you can minimize that bowl to get to the bottom of that quadratic. And this is the step size that does it. This is the learning rate that it does exactly that. So that's, in a sense, the geometric intuition that you know this bowl or a paraboloid sitting on top of your function. You can get to the bottom of that one. Another way of seeing this, and I like this a lot, is if you think about the units, thinking like a physicist here helps a lot. Imagine F has units, dollars, I don't know. And imagine that the iterates W have no units, they're unitless. And you can't add together, unitless minus dollars. It makes no sense. Or at least you will always be having to tune the learning rate by hand because the learning rate will have to fix the units. This learning rate, 1 over L, fixes the units immediately because L has the same units as F. So 1 over L times gradient of F actually means that this is unitless again. So this is a very good, very nice way of thinking about it. Okay, I'm going to move on before I show any more acceleration. So this is the last slide of the previous lecture, which I should have shown, which I didn't. Just to say that there were exercise lists on complexity and convergence rates to understand what did I mean by linear convergence and why was I then passing it to the logarithm to talk about the number of iterations required to reach an epsilon precision. Exercises on convexity and smoothness. Oh, this complexity word is not meant to be there. And an exercise on proving convergence for ridge regression. These are all on my webpage, and later tonight I'll put the solution of these three. Okay, so now we move on to the main subject today, which is stochastic gradient descent. Would you like a question in the chat? Can you adaptively pick the learning rate by doing line search? Absolutely, yes. In fact, traditionally, outside of machine learning applications of optimization, the go-to for gradient descent is not to have a fixed step size, 1 over L. You kind of figure out the local best L or the local smoothness constant by doing a line search. And this works much better in most applications. But the reason we don't focus on line search, or I don't focus here, is because though line search works well on gradient descent, it's not clear if it's the right thing for stochastic gradient descent. At least, I guess the jury is still in. People are trying to decide and figure out if there exists a line search procedure for stochastic gradient descent that works as well as the traditional line searches for gradient descent. But if you really are using gradient descent, just gradient descent, a line search is better than a fixed step size. Okay. So moving on, let's go back to our training problem, which is you want to minimize this average of fi functions. And let's look again at gradient descent algorithm, which is here below. Now, the issue with gradient descent is essentially, if you think about the number n here being an extremely large number of samples, each step of gradient descent requires you to compute the gradient over all n of your data points. And this can be extremely slow. If you think about, for instance, the cat problem, imagine you have, I don't know, 1 billion photos with or without cats. What gradient descent wants you to do is wants you to compute the gradient of your function over every single photo in this set, 1 billion photos, to make one single update. And this is actually computationally very inefficient. It's much better somehow to figure out how to make progress if you're given just a mini batch, just a small subset of your data, and then be able to update your parameters with only that. So this is how I'm going to motivate stochastic gradient descent in a very informal, slightly informal way. So can we design a method that if you give it a single fi function or a single data point I, it can update the parameters. Now the idea is very, very simple, is that we can replace the full gradient, now above f, with an unbiased estimator. So what I mean by this is if you select an index j uniformly at random from the indices between 1 and n. So that means that every single index has a probability 1 over n of being sampled. Then the gradient of fj, where this j has been randomly sampled, in expectation under this distribution of J, you have to sum up all possibilities, so from I equals 1 to n, and multiply by the probability of sampling each index 1 over n. And that in itself is the average of gradients. So that is the full gradient already. So it's a very simple idea. You can replace the gradient by an unbiased estimator of the gradient. And maybe that will work. Let's see. Here's an exercise which I won't do just now, but though I said uniform sampling, you don't have to do uniform sampling. You can introduce probabilities pi from 1 to n. You can sample j according to the law, well, sample j with probability pj. And you could show that a different unbiased estimator of the gradient is given by this, the gradient of fj divided by n times pj. So I leave that as a small exercise if you just write it down now. Okay. So now the stochastic gradient algorithm looks just like gradient descent. We have to choose the initial parameters, W0. We have to choose a step size, alpha. We're going to iterate from t to capital T, from t equals 0 to capital T. But at each step now, we're going to sample an index j from between 1 to n. And then we're going to compute just the gradient of fj, not the other gradients, and take a step in the negative direction of this gradient. Is the algorithm clear?
Are you using a single point as the estimate for the gradient at this point? Like,
we are, to simplify exposition, we are using a single point, but in case your question is about mini batching.
well, I guess it was towards there, but I was just wondering about the definition. So like just the definition of what's on the screen right now. So.
Okay, yeah, good. Definition of what's on the screen, it is just a single data point.
Thank you.
But in practice, we would use more than a single data point, always. Always use a mini batch. But actually all the proofs, all the concepts will carry over. Fine, it doesn't make it much of a difference. Okay, so I want to give, so that was one way of saying gradient descent. All I'm saying is we're replacing the gradient by an unbiased estimate of the gradient. But I want to give a slightly different perspective of what some other machine learning people would see, how they would see stochastic gradient descent. So I'm being a bit sort of, I don't know, practical and just saying we're given one problem, we're given one data set. We can only we can only work with our training data. We have nothing else to do. Let's replace the gradient by an unbiased estimator. But you can see things differently. So let me just give this other perspective. Consider here the whole training problem, and I've exposed all the details again. The loss function has come back. Here is the actual model parameterized by W, and here are the data points xi, yi. Here's the regularizer and the parameter that trades off regularization and fidelity to data. The thing is that if you think about it, these xi, yi's, these are data that we've labeled ourselves already. We've had someone go through all the photos and say, there's a cat, there's no cat, there's a cat. And so we don't really need to label these data anymore. It doesn't matter, really, if our model fits perfectly all this data we've already seen. What we really want, instead, is to solve a test problem. So a test problem is like this. You have to imagine that there is an expectation or some distribution for which you can draw your data. So somehow there's this very, very strange distribution that uploads cat photos every day to the internet. It's all these people, everyone online who can upload a photo. It's the distribution that governs that. And what you would like is you'd like your model to perform well if it was given some new photos, potentially with or without cats. So what this means here is you want to minimize the expectation of all possible photos that are being uploaded, and you want to minimize the loss. Notice I've dropped the regularizer because in this case, we kind of have sort of infinite data. We're being able to generate, this is an expectation over the entire data generation process. So it's hard to overfit it, let's say. And I would say that what many statistical machine learners would think of as stochastic gradient descent, they think of it as a method that can solve directly this problem. They can interpret it as that. And why is that? So if you look at this problem, minimize expectation over this crazy cat distribution thing, you obviously don't know this distribution D. It's completely unknown to us, which makes this problem very challenging. But we are able to sample from this distribution because we are able to go online every day, collect the new photos, label them, and then do something with that. So stochastic gradient descent can be interpreted as a method that if you're only able to sample from some unknown distribution, you can still run stochastic gradient descent, even without knowing this expectation. And in this notation, what it would look like is, again, initial W0 step size. I've added a time dependency step size. I don't know why. This doesn't matter right now. Iterations T from 0 to capital T, and every iteration we're going to sample a data point somehow, either by going online and downloading the new photos, labeling them, and then we can compute the stochastic gradient just over this data pair. And right now I'm outputting the average of all the iterates, and I'll explain that later. I shouldn't have put that here, but this is also the typical output of stochastic gradient descent. So it's a slightly strange, subtle point to make that stochastic gradient descent is sort of able to directly solve the true expectation. But in practice, if you're given one big data set, one big training data set, like many times we are, then the previous interpretation of just using the stochastic gradient as an unbiased estimator is fine. So these are subtle differences. Any questions about that caveat? Okay, let's start plotting stochastic gradient descent and seeing what happens. So here I plot the level sets of a logistic regression problem. The red point is the minimum. These concentric ellipses are the level sets of a big, massive bowl. And we're trying to get to the minimum of the bowl. So each one is like a level of the bowl. The blue dots here are the iterates of stochastic gradient descent. I didn't put the direction on them, but they start at the bottom and they're working their way to the top. So they make great progress in the beginning, but they start to sort of bunch up and become sort of noisier as they get close. So I wonder why that happens. Let's see if we can understand that. So let's compare to gradient descent. I've now tilted the level sets so you can see a different perspective. Here are the iterates of gradient descent converging beautifully to the solution. Here are the iterates of stochastic gradient descent. They start off great and they just sort of start to wander before they often get to the solution. And let's see if we can understand why this happens and how we can stop this from happening. But first, we need assumptions. We cannot talk about generic functions. And of course, I'm going to talk about smooth and convex functions again. In particular, I'm going to use strong convexity of the full training problem F. So this is again on the above inequality here is strong convexity, but here, as you can see, there's a lower bound, so it's greater or equal than this simple quadratic function, and there's this constant mu. I fixed one of the arguments at W star, which is all we need actually for the proofs, and that's called quasi-strong convexity. But you can ignore that. Just pretend this is strong convexity. I'm also going to assume that each individual fi function is smooth. So each fi is the loss over a single if data point plus the regularizer. So what that means is that fi of y is less or equal than this quadratic centered around w with its own constant li. And I'm also going to define the maximum of these smoothness constants to be L max. I also need a definition. Okay, one more definition. I know this is probably already too much to hold in your mind, but I'm going to give this following quantity a name. I want to name the expectation of the norm squared of the stochastic gradient evaluated at W star. So if this was the full gradient, if this was nabla of f without the j at W0, this would be 0 because the gradient at the minimum is 0. But the stochastic gradients at the minimum point are not 0. They're only 0 on average, because on average they make the full gradient. And this is this is kind of why stochastic gradient set doesn't converge naturally, as we saw in those plots. Because the stochastic gradients themselves are not 0 on W star. Okay, so I have a series of exercises, which again, since I'm not there, I'm not quite sure how I feel about people doing exercises in silence without me being able to help. So I'm going to just walk you through these exercises instead of asking you to do them. So if we consider the following training problem, which is ridge regression, we're given a capital matrix, capital X is a matrix of features of inputs, and Y are our labels, the vector of labels. Now, can you compute what is the Li smoothness constant of each of the individual Fi functions? And my hint here is that one way to think about smoothness, which I find a little bit easier, is that Fi.
Rob, we got disconnected. Can you hold on for a few minutes until we reconnect?
Sure. Yeah.
Did you hear me?
Yes, I heard
Okay,
you.
great. Yeah, give me a second. We got
Okay.
this. It just happened right now. Good timing on your part.
Okay.
All right. Give me a minute. I'll let you know when we are reconnected.
Cool. Right. So I'll take it away. For those of you who wrote this down fast enough, you've had some time now to try. So I'll walk you through the solution here. So if we have a ridge regression function, this one here, what is the smoothness constant of the individual Fi functions? And I gave a clue saying that, well, the Hessian of the Fi function, its largest eigenvalue actually is upper bounded by Li. And I find this an easy way to compute. And the trick is first you have to identify what is the Fi function. I mean, it's actually not written in the exercise, what is Fi? So you have to sort of write it out yourself. So here is the full ridge regression function again. And what I'm going to do is I'm going to break up this norm, this vector norm. So this vector norm is the sum, it's the sum of the squares of the individual elements of the vector. And now I'm going to name the individual elements. So I'm going to say that xi is the ith column actually of x. So the ith element of this vector here is xi transpose times w minus yi. We have to take the square because we sum the squares. I'm also going to put the regularizer into the average like we did before. And this way, I now have an average of individual functions, of Fi functions. So I can call this thing Fi, this entire thing in the brackets. And now to compute the smoothness constant, I'm going to do the laziest, quickest way, which is also the most obscure, probably. And I'm just going to differentiate twice in my head, which obviously takes some practice here. But if you differentiate twice this thing here, differentiating twice the norm squared of w over 2 actually gives you 1. The first time the 2 drops and cancels, you're left with the w, differentiate it again, gives you identity. So that's why we get this lambda here, just lambda times identity. Differentiating twice this guy here, this is just a quadratic term in w. And the only term that survives differentiating twice is exactly the term that has a power square in w. And that's only this guy squared, xi transpose times w squared. If you differentiate that twice, you get xi outer product xi transpose. So outer product means that there's a column matrix times a row, sorry, a column vector times a row vector. And that makes a matrix. And this is the whole Hessian matrix. It's actually particularly simple. The Hessian matrix doesn't depend on W. It's a constant. And now I'm going to use tricks that I know how to compute the largest eigenvalue of a matrix that is, actually this should be identity, I'm sorry, it should be identity times lambda, identity plus rank 1 outer product. I know that it's actually upper bounded by the norm squared of x, of that vector in the outer product, plus lambda. So I've used lots of tricks here that I know how to bound the largest eigenvalue of particular matrices. So this is my Li. It's just the norm squared of xi plus lambda. But what I wanted was L max, the largest of the Li's. And for that, I just take the max over all the Li's. And because lambda is constant, it comes outside the max. So L max is the max of the norm squared of xi plus lambda. Now, the reason I'm showing everyone this boring exercise is because this is one of the tricks for setting the learning rate, or the step size of stochastic gradient descent. Will be computing Lmax or finding approximations of Lmax. And this is one of the simpler cases. You can do it for more involved cases, for instance, like logistic regression. So this is exactly the loss of the logistic regression over a linear hypothesis model. I don't know why I'm using AI instead of XI. Some sort of mistake, really. It should just be XI. This is slightly harder to compute Li and Lmax. In fact, I'm not even going to walk you through the computation. I'm just going to first state what is Fi. It's a little bit easier to figure out what Fi is because it's already written as an average. So each Fi is just getting one data point, the loss of one data point, and adding the regularizer. But now the computation of the gradient and the Hessian is too much. Okay, so I'm not going to walk through all these computations. I'm sorry, but doing this online, I think, is too tedious and hard to follow. But moral of the story is it's still very easy to compute Li. In fact, the Li is extremely similar to the previous case. If you again substitute in your mind that AI should be Xi, each Li is the norm of Xi squared divided by 4. That's the only difference, plus lambda. And that's already the Li smoothness constant for logistic regression. Now these derivative calculations, I'll put the slides online and you can look and see through them. All right. So
can I ask something before we continue?
yes.
Isn't the Li and the Lmax that you found this way pretty loose, like a loose upper bound and not the actual value?
I think actually they are the tightest. But in terms of a global upper bound on the eigenvalues of the Hessian, I think this is actually the tightest upper bound.
So the eigenvalue for the low rank matrix will always be the norm of the.
Yeah.
Okay.
This is actually yeah. So this matrix here, the eigenvalues are either lambda. Lambda is an eigenvalue if you just choose any vector that's orthogonal to xi. But as soon as you choose a vector that's in the range of xi, your eigenvalue will be this.
Oh yeah. Oh, yeah, I see it now. Okay.
That's a good question, right? Yeah, I didn't say anything about tightness. I just said it was an upper bound, but actually it's tight.
Okay, thank you.
No problem. Thanks for the question. Here again, it's a little harder to argue tightness because I did a very odd step where I had to drop any dependency on W. So if you look over this, you'll notice there's a number here, a very strange number, exponential to minus something divided by 1 plus exponential to minus something squared. And to get this bound, I just said that, well, this number is less than 1. Which is, maybe not so easy to see, but this entire thing here is less than 1. And to say it's tight, you have to find a W that takes the limit that makes this 1. So you have to make, I think, the term in the top go to positive infinity. Although it looks like.
Isn't that just logistic? Yeah, it's just a sigmoid. So yeah, that sounds right.
Yeah.
Okay. Yeah.
So I'm not even totally sure how tight. I think this is tight, but I have to stop for a second to double check for this one. Okay. So now we have all the ingredients for me just to tell you first what is the convergence result we can prove for stochastic gradient descent. And the result is this. If the total loss function, the total training problem is mu strongly convex, each individual Fi is convex and Li is smooth. We choose a learning rate that is between 0 and 1 over 2 L max. So this is why I was painfully computing some of these L maxes. Then we kind of get the following convergence result. We get in expectation the norm squared WT minus W star squared is less or equal than 1 minus alpha mu to the power T. Now this number here, because of how I bounded alpha, this is always a number less than 1, which again, I haven't explained exactly why, but it is. So as you take this in the power T, this is collapsing exponentially fast, times a constant. Now, if it was just this, we would be in business. This would be linear convergence, it would be amazing. But that's not the only thing. This is another additive error, just a constant being added on. And what is this constant? It has this sigma squared, which I often call gradient noise, which is again the expectation of the norm squared of the stochastic gradients evaluated at some minimizer W star. Now, if you stare long enough at this, you realize that the constant term, well, it also depends on alpha. And so you could decrease the constant term just by choosing alpha approximately 0. That would just make this constant term disappear. But the problem is here. If you look at the linear convergence rate and you ask yourself, what should alpha be? The best possible rate comes from alpha being approximately 1 over mu. In fact, if you could get up to 1 over mu, then this would be 0, and you would have the most incredible linear rate. It would be done. But mu is typically a really small number. Mu is related to the smallest eigenvalue, actually, of the Hessian of the total training problem. So these two things are in contradiction. One of them wants alpha to be small, the other one wants alpha to be big. And that's a problem. Let's see what this looks like. Okay, I don't think I want to. Let me just double check what's next. I think, yes. Okay, so what we're going to do is we're going to skip the proof. The proof is 2 slides, but it's too much as well. The proof relies on something I mentioned earlier called Co-Coercivity. That's this sort of perfect combination of smoothness and convexity. But we didn't do that earlier, and so we're not going to use it now either. But I'll leave the slides if anyone wants to see the proof. In fact, this proof is also in an exercise sheet is dedicated to understanding this proof. I think it's one of these things that's better learned by staring at something alone. Okay, so let's see what does this convergence theory mean in practice. You can actually see this happening, this sort of result happening in practice. If we take a really small step size, alpha equals 0.01, on this particular problem, what you will see, these blue points, which are the iterative stochastic gradient descent, is that they're moving very slowly towards the solution. Very slowly, because this linear term is quite large. It's not so small. So it's contracting very slowly. If I use a larger step size, 0.1, then the iterates run up closer to the solution, but then they soon become sort of a noisy cloud. If you use even larger, 0.2, or even, it's my favorite, 0.5, you have that the iterative stochastic gradient descent do make good progress in the beginning. They sort of run up to the area where the solution is, but then they become a point cloud mess of noise around the solution. This radius of noise, of mess, is pretty much determined very precisely by this constant. So what can we do? How can we move towards a solution quickly, but also make this cloud of noise smaller? Anyone want to take a guess? Any guess?
So because nobody is talking, I guess we can just decrease the learning rate as
Yes.
it goes on.
Yes. Good. That's it. Because you can, you know,
Yeah, sorry, just because I already have the mic on, and I wanted to ask a question as well. If you go to the previous slide, so if I use an alpha that is too big, then this diverges, right?
yes. Well,
So, like if I use alpha that's bigger than 1 over mu, then the whole term. Oh, I see. Yeah. Okay.
well,
So that's because you chose alpha in the right. Yeah. Okay.
Yeah.
Okay. Thanks.
if alpha is bigger than 1 over mu, this actually theoretically is not true. That's just the.
Yeah, I see. Okay. Right.
But I see. You can imagine already that if you for different alphas, this thing could be not contracted at all. Could just be increasing. And maybe, I don't know, maybe it does still hold for alpha greater. I'm not quite sure. I think something might break in the proof though. I mean, I know it breaks. I remember where it breaks. It breaks somewhere here. So yeah, I know it breaks.
Okay.
Good questions. Good to ask these questions because you can piece apart what is true and what is not in the proof. So I've constrained alpha quite a lot already. In fact, you can't even choose alpha equals 1 over mu. It's not even that's allowed because of my constraint here. Anyway, 1 over mu is massive. It's too big. Okay, so we can make use of the fact that the first iterates go quite quickly close to the solution, get up to a certain noise radius, and then we can decrease the step size to shrink these noise balls. So idea number 1, start with big step size or learning rates, end with smaller learning rates. But idea number 2, which is another one, you could just look at this noise cloud and be like, the solution's kind of like in the middle of this noise cloud. So what happens if I just take a few of these last points and average them together? What happens then? So if you get the noise cloud and average it together, you might end up with a point just bang next to the solution. And this also typically works very well in practice. So here we go. Idea number 1, shrinking step sizes. You don't choose a single learning rate alpha t. You choose a sequence of learning rates that are positive. They converge to 0, and that's necessary so that the radius of that noise cloud converges to 0. And there's another technical condition which says that they go to 0, but they don't go to 0 too fast. And one way of saying that is that on average, they actually sum up to infinity. If you sum up all the step sizes, they sum up to infinity. So there are many. You can think of things like alpha equals 1 over t, 1 over square root of t, 1 over t to any power that's less than 1. This will happen. the series will sum up to infinity.
Excuse me, I'd have a question. So if you do this approach of averaging together the points in the end, wouldn't that basically be like taking a batch size which is larger than 1?
It's not exactly, because in the end, if you think about for each of these points, they were evaluated on different data points at different parameters as well.
True that. Mm-hmm.
So if you take a larger batch size, in the end, what you have is that you have one set of parameters W, and then you take lots of data points. So
Yes,
averaging is a slightly nicer use of past information in a sense. You don't have to compute new data points or load new data points. But it's a good question. There are certainly similarities. And mini batching does this as well. It cancels noise. And you can prove that as well. You can see it in one of my papers. Okay, so this is our first attempt at fixing the noise cloud, is to use a decreasing step size. So here I have a horrific theorem to read about how decreasing step size works, or one way to make it work. And it's quite hard to digest, but let's go through it. Same assumptions as before. The total function is strongly convex, which probably means you're using an L2 regularization. Loss function over a data point is convex and smooth. I'm going to define a weird constant, kappa, capital kappa, terrible, equals L max over mu. So the largest smoothest constant of the individual Fi functions divided by the strong convexity. And now here is my alpha t, my decreasing step sizes. Eventually, I want to decrease the step sizes, and they're going to decrease at this rate. It's going to be a fraction that is 2 times t plus 1 on top, but t plus 1 squared on the bottom. So this entire fraction is decreasing at a rate of something over t. But I'm not going to decrease right away. In fact, what I'm going to do is I'm going to hold the step size constant for at 1/2 L max, which is exactly the same constant step size we saw before, for a number of iterations t, so long that t is less or equal than 4 times kappa. Well, the ceiling of kappa. As soon as t is greater than that, it switches to a decreasing step size, which is proportional to 1/t. And what you get in the end is that if you do this scheme, eventually, when you have enough iterations, the expectation of the norm squared between Wt minus W star squared is less or equal than a weird constant divided by t, and an even stranger constant divided by t squared. So this is kind of unnecessarily difficult. In fact, I think I'll never teach this slide the same way. I will simplify this next time. The only thing you need to pay attention is that this part here is decreasing at a rate of 1/t. Even though I put a weird quotient of polynomials, it was unnecessary, because this is a proportional to 1/t plus 1.
Excuse me.
Yes.
Could you remind me over what distribution the expectation is again?
Yes, good question. For now, we're just uniformly sampling at each iteration an index j for the stochastic gradient. So this total expectation is in fact the filtration defined by all of these iterates, where each iterate you do a uniform sampling of an index j. So this is an expectation over all those past samplings.
Thanks.
To write it formally, actually, you have to write the whole like filtration and sigma algebra, but it's a bit unnecessary because the sampling is very simple. And I have a caveat here. So right now, I've shown the convergence for strongly convex. A similar result holds just for convex, but instead of 1/t, that result is 1/square root of t. And in practice, because many of the objective functions we work with are not strongly convex, this is a more commonly tuned sequence. If you were going to tune by hand, you just try to find a constant c such that dividing by square root of t plus 1 works. But for my experiments and for what I'll show you now, I'm actually gonna implement this theorem. So let's see what this theorem looks like. Okay, I think this objective function here we're using again is a logistic regression. On the y-axis, I plotted the distance to the minimum, that is wt minus w star norm squared. On the x-axis is the number of iterations, t. In blue, I had the convergence of stochastic gradient descent with a constant step size, 1/2 Lmax. In orange, I've implemented this step size, this strange switching step size. I call it switching because there's a sudden point when t is suddenly greater than this number that it switches from constant to decreasing. And here is this, I've even indicated the exact switch point, the dotted orange line. And as you can see, as soon as it switches, it continues to progress and decrease in terms of distance. Okay, that's good. But if you look at the end, still, you know, a bit weird, right? I mean, you can still see it's kind of decreasing, increasing. It's still very noisy. So let's try and take averages as well. So what does averaging look like? Now, in practice, we use late start averaging. So what I mean by late start is you don't want to average all the iterates. In fact, you know that the first set of iterates were kind of running towards the solution. You only want to get that cloud of points and average that. And one way to try to do this is that we guess after some point, when will the iterates become noisy? So I'm going to choose that point as S0. The start of the averaging is just the integer S0, which is the, after you reach iteration S0, we're going to start averaging. So initially, we're just taking normal stochastic gradient steps. In fact, we always take normal stochastic gradient steps for every iteration t. But when t is greater than S0, the start point, I'm going to start accumulating this expression W bar, which is going to be, which is equal to the average of all the iterates for which t is greater than S0. This should be Wi here, because it's the sum of all Wi starting from S0 to t. And this idea of averaging was, I believe, introduced by Polyak and Judiski in '92 and shown to work. Okay. Yes, here's a question. In terms of implementation, this is clearly inefficient. This is very inefficient. At every t greater than S0, I have to recompute this average. So I want someone to tell me at some point, when I'm around in person, I guess, as I keep saying, how do you efficiently accumulate this expression without having to recompute the average across every t greater than S0? Let's see how that works in practice. So now I have constant question.
Would something like a exponentially weighted moving average work?
Yes, an exponentially moving average, otherwise known as momentum. Yes, it works. And I have some slides about that, actually. So it's a good question. So it's coming up. I think we have time as well. We have half an hour, so we will talk about that, I hope. But it's a very good point.
I had another question.
Yes.
I had another question. So in the setting of like online learning that you talked about like a bit before, like, you know, where we sample a data point at every iteration and then there are like some other algorithms, right? So like, is Sgd like optimal in that sense, or like, is it?
Oh, it's not optimal across. If you, it depends really precisely what is your assumption of this online setting. If you're allowed to remember what data points you've sampled before and keep a table, then Sgd is not optimal. In fact, the variance-reduced stochastic gradient methods can be optimal. If you can't remember the point you've sampled, you can't collect a table that tells you, I've seen this data point before, then Sgd is optimal.
Okay.
But it's quite subtle. It's a very good question, but there's subtle differences between what setting are we in exactly to say it's optimal or not. In fact, the first time people proved the convergence rates of variance-reduced methods, they thought it broke the lower optimality bounds because we knew Sgd was optimal. But it turned out that that little tiny assumption of remembering the data points you sampled changes your optimality.
So this is like a bit of a difference from the offline setting where we know that accelerated Sgd is optimal or accelerated GD is optimal.
Well, accelerated GD is not optimal in terms of sampling, though, in terms of how many data points you need to sample to get to. But it's optimal in terms of full gradient samplings. The number of full gradients you need, in other words, the number of iterations, it's optimal.
Yeah. So I also ask another question. So when you introduced the Sgd, we took into account that the estimate for the gradient is unbiased, but the estimate for the weights, do we have any reason to assume it's unbiased so that taking the mean like you do is a good decision or yeah.
Yes, it's good. Well, interesting question. I guess you mean is it an unbiased estimate of the weights of gradient descent?
Yeah. So is it an unbiased estimate of the optimal weights? That's kind of what this is doing, right? When you're taking the mean, the average, it's like saying that it's an unbiased estimate of the weights, I guess, or it could be a biased estimate, I guess. But.
Well, it's a very interesting question. I have two answers for this. First, oddly enough, even if it was the unbiased estimate of the weights, that is not that good. The thing is that having unbiased estimators of something is not a very good estimator. And the kind of convergence we want to prove is much stronger. We're trying to show that the expectation of the norm of the iterates converges. So this is called convergence in L2 or convergence in mean squared error. Think about moving the expectation inside. If we had they were unbiased estimators, for instance, then we know that the expectation of WT minus W star equals the same as gradient descent, and we know that that converges linearly. That's kind of good, but just knowing that the mean of your iterates converges is nowhere near good enough for practice. It means that your iterates could be highly stochastic, highly noisy, have massive variance and massive tails, and you would have to rerun your algorithm, hundreds of times to take the average. So even if it was an unbiased estimator, it's not that good. But now comes the truth is that they're not unbiased estimators anyway. So because you're passing through this nonlinear function, the gradient, unless the gradient is the gradient of fj is linear, this is going to be a highly nonlinear function, and so we have no hope that they're going to be unbiased estimators.
Okay.
That's a good question, but we can still prove that this works, actually. This is actually one of the easiest proofs is to show that averaging works for stochastic gradient descent.
Okay, thank you.
No problem. But I'm not going to prove it. I'm going to just show you a plot and hope you're convinced. So in blue, we have, again, constant, Sgd constant step size. In orange, we have this switching step size, this sudden decreasing at this orange double dotted point at the number of like 4,000 iterations, quite a lot of iterations. And now we have green, which is also the switching step size regime. So it switches as well, but later on at 22,500 iterations, it switches. So instead of just spitting out the last iterate, it spits out the average. And you can see right away this sudden decrease in the distance to optimality. So yet another trick that works well. Both of these tricks actually work well, and they're also theoretically justified. You can prove that they work well. Okay. So now that's my initial collection of tricks with stochastic gradient descent. I'm going to show one other for sparse data. Oops. Which you have sparse data, and then I'm going to show a little bit more about using momentum, and then that will be it. Any final questions about this? Okay, here we go. Sparse data. So this is another thing that's really important if you want these things to work at scale. So for this, I need to expose again the exact structure of our training problem. And I'm also going to restrict myself, I'm going to restrict things to a linear hypothesis model. So that H function is gone, H of W, and it's been replaced by an inner product between W and Xi. And I want to show you guys a trick. So let's assume that our data, in other words, the inputs Xi, this vector Xi, is sparse, and it has at most S non-zero elements. And imagine S is a small number. So let's say it only has like 1% of non-zeros. How many operations or floating point operations does each step of Sgd cost? Let's have a look. So I'm going to write down one step of Sgd. So from iterate Wt, I take a step in the negative direction of the gradient times alpha t. And the gradient in this case is just this. It's a scalar derivative of the loss prime. And you use the chain rule to differentiate this linear term inside, which is a product between W and Xi. And because of the chain rule, this Xi pops out here on the other side. This is a vector. Okay, so this is a scalar times a vector. And we also differentiate the squared norm bit here, and that gives you just lambda times Wt. And the first thing I'm going to do is rearrange. I'm just going to join together the terms in Wt. So here we have a Wt term, and here we have a Wt term. And if I join these two together, I get 1 minus lambda alpha t Wt. And this is how actually L2 regularization is implemented for deep nets and things, and it's called weight decay. It's called weight decay because you get your, I don't know, weights or the weights of your neural network, Wt, and you just shrink them by a bit. Because this number, this lambda minus alpha times alpha must be less than 1. Or is at least typically much smaller than 1. And here's the last term. So the last term, alpha t times L prime, this is just a scalar. And Xi is our sparse feature vector or data point. So here we have it. We have a very sparse addition. So we just need to add a sparse vector to a rescaling of Wt. Now, sparse addition of a vector that has only S non-zeros costs only typically S operations, because you only need to focus on the S non-zero elements to add. And all the zero elements, adding them does nothing. But so this almost looks like the cost of Sgd would be S operations. But there's this very unfortunate rescaling, and rescaling a vector of size d costs d unless you know something about its sparsity. But we don't know anything about the sparsity of the weights or the parameters w. They could be dense. So very unfortunately, the iteration of Sgd costs O of d, but it kind of feels like it should be O of S. And in fact, you can make it O of S just by a small rearrangement and introducing another variable. And the trick is you have to sort of isolate this rescaling. So let's do it. And I normally pose this as an exercise, but again, I'm just going to do it. So if you try to rewrite the iterates and rename, instead of calling it Wt, let's say that Wt equals a constant beta t, a scalar, sorry, times a vector zt. So betas are scalars, the vectors, zt's are vectors. can you choose beta and z so that the total cost of Sgd is only O of S operations? The answer is yes. So first, let's just substitute in. What we know up here is what Sgd looks like. Everywhere I see Wt, I'm going to now substitute beta t times Zt. So here we have beta t times Zt. Here we have beta t plus 1 times Zt plus 1. And we have another one hiding in here. So now the trick is, can we rearrange this and figure out how we should update beta t and how we should update Zt so the total cost is only O of S? It's almost magical. So what I'm going to do is I'm going to bring out beta t. I'm going to put a parenthesis around all the terms and multiply them by 1 minus lambda alpha t times beta t. So this first term Zt came from here, it's fine. The second term is not happy with this. It needs to be divided by that exact same constant to bring it into the parenthesis. But this way of rearranging is very suggestive, because now, if I call everything inside the parenthesis the new Zt plus 1, everything outside the parenthesis the new beta t plus 1, then this gives me a perfectly adequate update for beta and z, because the result is now beta t plus 1 times zt plus 1. But this seemingly weird rearrangement is really meaningful, because here we have it. Here's our new update in zt plus 1. And here is our new update in beta. Who can tell me what is the cost of updating our scalar beta this way? By multiplying it by this constant. How many operations? Multiplications, additions, and subtractions.
Is this a constant, right?
Yeah. Yeah. Computer scientists would just say O of 1.
Yeah.
Mean constant, but there are like 3 or 4 operations. Whatever. Now the trick is, what is the complexity of updating this z? This is more tricky. Let's say that this entire, see this big constant here for the xi? Let's just call that 1. Okay, that costs 1, because it's just a bunch of scalars being multiplied, divided, whatever. That's 1. So how much is it to add zt to the vector, sorry, to subtract xi from the vector zt?
Yeah, order S. Yeah.
Order S, exactly, because there are only S non-zero elements in xi. So you're going to get this constant, multiply all the S non-zero elements of xi, and then you're going to subtract that from z. So there are only S operations. So magically, we now have a version of stochastic gradient descent that costs O of 1 to rescale, O of S to add the sparse vector, and that is O of S. This is massive. If you think about this, imagine you have a gigantic genomic data where the sparsity of your data is like 0.001% of the data is non-zeros. So you're decreasing the cost of a single update by about 10 to the 5. It's a huge difference. Later, I want someone to tell me what is the problem with this update. This is a very subtle point. I could update Z like this and beta like this, but what issues could I have by only storing beta and Z? This is very subtle. Notice I never store beta times Z. I'm going to leave that because it's a subtle point. Unless someone can tell me right away, but it's not obvious.
The betas go to 0 kind of fast, right?
Well, that's an interesting point I hadn't even thought of, actually. Yes, the betas are going to 0. So I don't know if there's a numerical accuracy problem because we have something going to 0 and something not. That's something I didn't even think about. The problem is that we want the iterates Wt. We don't care about, you would never output ZT. It has no meaning on its own. So eventually you need to monitor your algorithm. You need to output your weights of your network to say what's happening. And you don't have them. You don't know what they are until you compute beta t times zt. And the cost of multiplying beta times zt is O of d, because z could be dense. So every so often, you still need to do this O of d operation, but only every so often when you want to see what the weights are. Once every epoch, let's say.
Are you also kind of assuming that in each iteration you know what the indexes for the sparse operations are?
The index? You mean the I? No.
Yeah, like which are not 0 in xi.
Oh, yes, this is a good question as well. So you're referring to how do we actually, why is this actually O of S, right? Because you would have to sort of know.
So if you know the indexes, it's O of S. But if you don't know the indexes, then you have to find them, and that would be O of D anyway.
Yes, yep, it's a very good point. Another way of saying that is if xi is a dense, it's stored as a dense array anyway, like a NumPy array, this would still be O of D.
Yeah.
So this only works in sparse linear algebra if xi is stored in the sparse format. That would make that you would then know for the non-zeros, and that's all non-trivial. I should say to get that to work well is extremely non-trivial.
Also,
for deep nets, I would give up probably.
Yeah, the sparse indices have to be kind of constant across all of the xi's, right?
No, actually, they don't. They don't have to be. This is still O of S anyway. The Z is going to be dense. The storage would be O of D.
Okay.
Yeah, but good point. Yeah, I see what you're thinking. That Z is now not sparse. But even though the storage is O of D, the operation is still O of S. Okay, so this kind of way of thinking is good if you really want to try to speed something up, especially for sparse data. But sparse data structures can be a pain. We'll talk about that another time. Okay, for the final part, my last 10, 15 minutes, I'm going to talk a little bit about momentum, which is, again, one of the most popular tricks used to speed up stochastic gradient descent. And I don't know why, but every time I introduce momentum, I reintroduce the very basic assumption behind gradient descent, which is probably unnecessary. So forget stochastic gradient descent for now. Let's go back to full gradient descent, just so I introduce momentum, and then we'll go back again to stochastic. So here's gradient descent. I don't know why I've switched my notation from alpha to gamma. I'm very sorry about that. Gamma is now the step size and learning rate. I don't really know if this is necessary, but the motivation behind gradient descent is very specific. The motivation says that gradient descent is the steepest direction downhill if you take a really small step size. So let's quantify what that is. Let's define delta D, and delta D is the local rate of change of our function along the direction D. So in other words, it's f, fix the point you're starting x, plus d times s, and s is a scalar, minus f of x divided by s. And this gives us sort of how much we've changed if we take in the direction D, if we take a step size s. Now, if we take the limit of s to 0, this then tells us our local rate, just how much we changed if we take an infinitesimally small step size s in the direction D, starting at x. Fun fact about this is that using this idea of local change, you can then ask yourself, well, what is the direction D that gives me the biggest change possible? And that you can actually answer that. The maximum, this is clearly meant to be D. Wow, there's many issues with this slide. The maximum of D over the local rate, if you constrain the size of the vector D, because we don't need to worry about size anyway, because we're already rescaling by S. Then the answer is it's the gradient also rescaled. If I made this the minimum, sorry, if this was the minimum over D, this would be minus the gradient. So in terms of taking if you're going to take a very, very small step size, the best direction to go in is the gradient to increase your function and the negative gradient to decrease your function. Now, what this means in practice is not always good. And the classic function that someone asked me about if I would show this, the classic function to show this issue is the Rosenbrock function. Now, let's have a look at the iterates of stochastic gradient descent over these new level sets. This is a different level set. This is actually a deep cut valley in the shape of a smile. And the solution is somewhere deep down the valley, but the valley only steadily decreases. It only gets deeper little by little. But on either side of the valley are these big hills. And we're going to start at the top of one of these hills. At the top of the hill, if you ask what is the steepest direction, it's straight down the hill. So from here, a gradient descent jumps straight down. And in fact, the step size I took is too big, so it crosses over to the other mountain. From here, if you ask what is the steepest direction again, it jumps down straight. You can even see it's orthogonal to the level sets, so orthogonal to these faint orange lines. And that's exactly the steepest way down, is to go orthogonal to the level sets. And then eventually it starts zigzagging back and forth, back and forth, back and forth. And the reason is because the steepest directions of descent are on either side of the valley, even though the solution is in direction of this very gradual descent. So gradient descent kind of gets stuck in valleys because of this. It slows down a lot. One way to fix this is just not to get too focused on trying to take the local steepest descent and give gradient descent a little bit of momentum. Don't allow it, to stop it from zigzagging. We can just say, I don't want you to change direction instantaneously at every step. I want you to maintain a little bit of direction you were already going. So from here, graphically, the first step is the same, gradient descent. But the second step, the steepest descent is down, but the previous step was really in the opposite direction. So gradient descent kind of compromised between the steepest descent and where it was going. And you can see how it's kind of struggling to change direction because I'm not allowing it to change direction because I'm giving it a bit of momentum, like a ball with friction. I mean, if you roll a ball actually in a valley with friction, it could go up and then down again. It would do this shape. This shape is impossible in terms of friction mechanics. What this looks like in terms of algebra is very simple. I just take a gradient descent step, but then I add the previous step direction. So that is WT minus 1. So that is the exact step it took last time. So I'm going to add a fraction of the step it took in the previous iteration. And that fraction is going to be determined by this constant beta. And this is how you add momentum or inertia. And this way of writing momentum is called the heavy ball method. But this is just one of the many ways to write it, as I will show you. Is it kind of clear why this adds inertia, or why this adds momentum?
So when we look at like accelerated GD, we also look at something similar to this, right? Like how is this conceptually different?
It's actually quite different in the end, because while this heavy ball method or this momentum is really adding inertia, in fact, you can even write down the equations of motion and add literally momentum discretized, and you arrive at this. That other acceleration was an extrapolation step. You needed 2 iterates to do it. You can't substitute out one of them. So it's actually a bit different conceptually. But both of them actually give acceleration in some settings. They're actually often confused one with the other, but they're different.
Okay.
It's a good question. It's good to point that out. So, but this method does have other forms, and this is not this heavyweight way of writing it is not the most popular way of writing it machine learning. The most popular way is writing it like this, where it's called the momentum method. So the momentum method works like this. Instead of taking steps in the direction of the gradient, you're going to take an exponentiated average of the gradients. So what that means is that at each step, you're going to get the previous estimate or average of the stochastic gradients, of the gradients, multiply it by a constant beta and add on a new gradient. So every time you see a new gradient, you add it onto your estimator, but then you shrink all the previous estimators. And this is why it's an exponentially shrinking average. But these two things are actually equivalent. They may look different, but they're exactly the same thing. And the proof is trivial. I'll show you. More or less trivial. So let's start with the momentum estimate, the momentum method, which is this. So what I'm going to do is update W using momentum. So it's minus step size times MT. And now I'm going to substitute MT out for how we updated MT, which is beta times NT minus 1 plus the gradient. Now I'm going to distribute out this multiplication of gamma. So we're going to have WT minus gamma, the gradient, minus gamma beta MT minus 1. And now I'm going to substitute out MT minus 1. Oh, sorry, this is the first step. I substitute out MT. Here's the second step. I substitute out NT minus 1. To substitute NT minus 1, all I did was look at the updates of the parameters W, but at time T minus 1. In other words, WT equals WT minus 1 minus gamma times NT minus 1, which rearranging gives me an expression for MT minus 1. It's equal to minus 1 over gamma times NT minus 1. And that's how I can substitute out this MT minus 1. And now all I need to do is cancel this gamma with this gamma to get the heavy ball method. So I get the exact same method again. So they're just different ways of writing the same thing. Any questions about that? Okay. Here we are, heavy ball method. Okay. So, fun fact, this is not the only way of rewriting momentum. There's another way which actually me and my colleagues found out, which is very useful for proving that momentum works. So you can rewrite it as, instead of taking averages over the gradients, as taking a particular average over the iterates themselves. So what it looks like now is I have to introduce a different new iterates ZT, and ZTs are updated using gradient set. So I actually go from ZT minus 1. I have a new step size eta. Unfortunately, I need a different step size than gamma. So there's a reason why it's a different symbol. Times the gradient. But then WT plus 1 is a weird average between WT and ZT. I say it's a weird average because if you take these constants, this 1 divided by alpha plus 1 and this alpha divided by alpha plus 1, add them together equals 1. So it's not an extrapolation, it's an interpolation. It's an average between the two. And these two methods are actually the same thing for a particular choice of eta and gamma and beta. And this is actually fundamental to be able to prove that this works. So we have a new parameter, averaging, and a new sequence of variables ZT. So the proof works like this. We can start from the iterative averaging viewpoint, and we just define gamma to equal eta over alpha plus 1 and we define beta to equal alpha over alpha plus 1. With this definition, the two methods are the same. Let's see the proof. I haven't seen it in a while, so I'm hoping it's easy. In fact, even the first step is not that clear. Oh, I see. Yeah, so by the first step, WT plus 1 then equals beta times WT. That's because I've called beta alpha over alpha plus 1. So I'm just taking this update here. And now it seems I'm going to substitute out ZT using how we update ZT. So now we have ZT minus 1 minus eta, the gradient. Finally, if we rewind time on the updates of W to the time t minus 1 and rearrange, we can substitute out ZT minus 1 as equaling alpha plus 1 times WT minus alpha WT minus 1. So this is just rewinding in time by one step here and isolating then ZT minus 1. If I do that, I can substitute out this ZT minus 1, and then we get this strange expression here. As strange as it may seem, all I need to do is multiply out this 1 over alpha plus 1 and rearrange to get the heavy ball method. I kind of wish I had one extra step there. Would have made it that much easier. I think I can see it here. There's 1 over alpha plus 1 times alpha plus 1 WT. That becomes this WT over here. This minus 8 eta divided by 1 plus alpha becomes gamma. This was this here. And then the other two terms, which are left, this beta here goes together with WT, and alpha divided by alpha plus 1 equals beta. Okay, well, you can kind of piece it together, but it's not straightforward. Okay, so we're back at the heavy ball method again. The same method again. Right, I think this is probably all the time we have. I believe this is meant to end at 10:30, is that right?
Yeah.
Okay. So I'll leave you with this last take home is that actually it may not be easy to see, but for strongly convex functions that are smooth, in other words of saying strong convexity is smooth, we say that the Hessian is upper bounded, the largest eigenvalue is upper bounded by L and lower bounded by mu. If you take a particular step size gamma, you can show, sorry, this is gradient descent? Yes, that's gradient descent. If you take it, sorry. This is you can show the momentum also has an accelerated convergence by choosing a very particular gamma and a very particular beta for strongly convex and smooth functions. And you get the exact same square root of kappa kind of convergence rate we saw in the lower bound. Ignore this SGDM. This is not SGDM. This is just gradient descent with momentum. This is the only setting where momentum has an actual accelerated proof. All the other settings are unknown and probably not true. But I'll just end on that note, I think. And let me go to the last slide, which has maybe some instructions. No, it doesn't. Wow, I have so many slides. Nope, I don't have instructions. That's it. I was just going to end on a note saying why Sgd is popular in ML. And the truth is that if you don't plot, instead of distance to iterates or the loss of your training function, if you plot a validation loss, which is how badly you're doing on data you haven't, that the method itself has not seen, you'll find that in orange, stochastic gradient descent with things like momentum has a much better error and validation than gradient descent in blue. But this is a note, this is something that would take you too long, but I'll just leave on that note that actually stochastic gradient descent works better on validation.
Thanks, Rob, for this really cool set of 2 lectures. We're at the time for the coffee break. So that's on the other floor. We're on 14, so it's on 17. And the next lecture is at 11.
Okay, hopefully I'll see you all tomorrow. I think I might be just barely passing my COVID test soon. So
yeah, it'd be awesome to have you back.
yeah.
Yeah, so you'll get a library of pre-implemented computation blocks, and if you use those, then your network will run and leverage all the hardware essentially as best as it can. These blocks, like you might know for traditional blocks, are often developed by the hardware vendors themselves, and they're very optimized. This does mean that if you're not, mostly doing linear algebra or FFT or convolutions, your code might not run as fast as it could, and in some cases, you can gain performance by doing some of the work yourself in the more traditional HPC sense. So this is something that you can integrate, and we'll also discuss this a bit. And finally, this may or may not be relevant for the problems you're trying to solve, but essentially they provide a large library of essentially neural network blocks and layers. So, a convolutional layer, a batch normalization layer, and so on. And also optimizers, which are mostly, modifications around a first-order gradient optimizer. And these are kind of widely used in deep learning to train neural networks and so on, but they are not always the right choice again, and sometimes we have to look outside of those. Okay, so let me kind of go through each of those in a little bit more detail and kind of explain, why we might be interested in this. So GPU computation. Essentially, the idea with these frameworks is that we can very transparently, so using essentially the same code, write computation that executes either on the CPU or on the GPU. And the GPU has an advantage in that for specific computation types, it can go much, much, much faster than a CPU. However, for some other computation types, it will be the same speed or even slower. And often GPUs are more difficult to get access to. At least this is the current experience on most of the computing resources we may have access to, in that they're a bit newer, so the HPC people haven't integrated them as well. So to give you an idea, top of the line, Intel CPU currently, you might be able to reach about 3 teraflops of performance if you have full AVX512 and you're using all the FMAs and so on, but for highly optimized numerical code. So this is called the theoretical peak. For GPU performance, you're picking up about you'll be picking about 9.7 teraflops. So you'll be, 3 times faster, which is fine, but you typically easily can get 3 times more CPUs than GPUs. So if you're just doing a double precision standard 14-point arithmetic, it might not be beneficial for you. If you're going to go to a single precision, you'll get a more significant speed up. But the largest speed up you get is if you're doing these types of small matrix operations, where you see that the jump is massive and you get maybe 10 times more performance between doing just vector operations versus doing matrix operations. And the reason for that is that modern GPUs and a lot of the new accelerators, like the TPU you might have heard of that Google has developed, essentially have special hardware to just do matrix multiplication. So if the operation you're trying to do looks like a matrix multiplication, for example, a convolution or some other advanced linear algebra problem, you get a huge speed up. If it doesn't look like that, the speed up you get might be more modest. So that's something to keep in mind. And a lot of deep learning, in some sense, and maybe kind of philosophically, is about leveraging the fact that we can do these matrix multiplications so fast. So sometimes we have, function definitions or that kind of crazy, why not use a smarter basis? Why not use something that is smarter in the way it uses the data, or because we can do something that's more simple but uses the compute in a more efficient way, and we'll get better results because we have access to so much compute. Okay, so just an example of what will happen if you wrote some computation in PyTorch on the left or TensorFlow on the right. So just a show of hand, who has seen PyTorch or TensorFlow before and used it? Okay, so a majority of people, I would say. So yeah, so you've probably seen something like this before. I just define a function. I kind of use both Python operations, like the multiply with the star, and I can also call PyTorch functions that do things that are not just naturally in Python. And when I run them, so they're slightly different in that, for example, on PyTorch, I need to specify, when I move a tensor to the GPU. So by calling CUDA, I'm saying, oh, please send this to the GPU, and then my code.cpu is please get it back. Whereas in TensorFlow, it kind of does it automatically for you. So by default, if you have a GPU, to put it on the GPU. If you don't have one, it won't try to use one. But fundamentally, the main part of code, and here it just runs a dot product, of course, but you can imagine there's a complex computation that goes there that has to do with the model you're trying to fit. You don't really need to worry about this. You're writing the same code, either it's for CPU or GPU, and the framework kind of tries to automatically handle where it should go and how it should execute. Okay. So this is really kind of one of the main kind of advantages of these frameworks is that they remake these computation and using these hardware accelerators that give you a huge amount of compute kind of much simpler. There's been projects in cosmology, and I'm part of some, and there's been others that have tried to write more standard HPC tools on GPU. I can think of FlowPM and so on that write particle mesh simulations on GPU using these deep learning frameworks. And even though you can do without them, and maybe very optimized codes will do without them by programming the C++ and CUDA directly, these frameworks allow you to bring up these types of things very fast, although you have to kind of stay on the happy path where you're doing most linear algebra heavy operations and big operations. And if you need some custom operations, then you might require some handwritten kernels for best performance. And these types of kernels, some people have written them. For example, if you want to do some segmented reductions or some other types of operations that don't map as neatly into this idea of square or rectangular tensors that are operated on in some way. Now, unfortunately, it's not all roses, and using GPUs is still, in my opinion, quite a bit more frustrating than using CPUs. You gain a lot, of course, but you have to prepare to deal with some issues. One thing is that, of course, you need to, CPU code is very universal. You just compile it and it mostly runs everywhere. GPU, you need to make sure that the hardware is up to date, the drivers are up to date. The hardware is evolving very fast, so depending on which version of the GPU you have, you might have different functionality in what you can access and what you can't access. It makes setup and installation kind of much more difficult. If you've tried to set it up before, you need to write CUDA version and so on. It can be pretty difficult on a custom system. And finally, stability is not always so great. This is a problem if you run like these very large multi-node GPU programs, but if you're interested in this kind of stuff, you can look at, so Meta released this training logbook for the open source language model. And if you read through it, they crash every day. So every day there's a log being like, oh, this node crashed, or this node is not performing as expected. We drop it from the training set, we add new nodes. They have stories like, oh, our ops team deleted all of our nodes, so now we need to restart the training. So this type of stuff, even at the places that have the most resources and try to train the largest models, it's still a big problem. Yeah. Okay, so now that we talked about how to run computation on GPU, the second thing that a framework provides is this idea of automatic differentiation. So really, it's a secret sauce that allows those frameworks to automatically compute the gradient from computation. So you write how you're going to compute a value x or y from x, and then the framework is able to automatically figure out what the gradient should be in a symbolic way. So when I say symbolic, it's not using finite differences, but also it's not using a symbolic differentiation. It's using essentially a sequence of operations that essentially boil down to using the chain rule, and if there are multiple paths, some kind of sum product reduction. So really, the main paradigm for deep learning frameworks is this backward mode differentiation, which what it does, it computes the adjoint vector Jacobian product. So if I'm given y is g of f of x, then the chain rule just tells me that the derivative of g composed with f, viewed as a linear map, right? So derivatives are linear maps, is simply the composition of the derivatives of the Jacobian of g and f, right? So if I apply that to a vector h, then this equation holds. Now, if I take the adjoint or the transpose, then the adjoint of the derivative or Jacobian of g composed with f, when I take the adjoint, the order's reverse, is simply the adjoint of g and then the adjoint of f. So what the framework does is for each g and f you might try to apply, it has essentially encoded already what is the adjoint operation. It has, it remembers if you apply node G, it remembers, oh, for this G, I know by fiat that this other function computes the adjoint of the derivative of G, of the Jacobian of G applied to some vector. And then it just throws it backwards. So this is essentially what's done. More modern frameworks is starting to appear in PyTorch TensorFlow, but JAX really spearheaded this. Also are able to compute a notion of forward mode autodiff, which kind of look more like the computing the first part, but it's somewhat different. They use a different kind of paradigm, and you will need different things to support it. This can be helpful if you're kind of doing really funny gradient tricks, but otherwise, in general, it's not as widely used in machine learning because, in general, it will be more expensive. But it can be very helpful if you're doing some types of gradient tricks that are somewhat more exotic.
Wait, can you say again why backward mode is advantageous?
Yeah, so it's actually not so simple to see. It has to do with the dimensionality of the quantities you're propagating. So typically in deep learning, we have a lot of parameters and we have one output, the loss, where the loss is a scalar, but we want to take the gradient of a scalar with respect to thousands of parameters. So this is the typical setup. In that setup, if you write down the size of those matrices that you need to propagate backwards, they're much smaller than the size of the things you need to propagate forward if you were going to do forward mode automatic differentiation. The problem will be reversed if you want to do something different. Like if the number of parameters were small, but the number of outputs were large, and you're trying to compute the Jacobian of a small number of inputs for a large number of outputs, you would prefer forward mode. But this is pretty rare in machine learning. So that is the reason. And again, these are kind of two extremes. In principle, you could try to have like, a scheduling thing over the graph of the computation that tries to figure out where I want to use forward, where you want to use backward, and merge them. And some people do that, but generally for deep learning, the backward mode is good enough and helps also be simpler to implement. So, yeah. So the main thing about automatic differentiation is we need to capture the computation that's performed. We need to know what are the functions that we did, that we applied to the quantity so that we can run them back. So most frameworks implement both paradigms, although it used to be that PyTorch was developed with this eager paradigm and TensorFlow with this graph paradigm. So in this eager paradigm, what the framework does is every time you call a function on one of the values, essentially it keeps a tape. It keeps a record. So, oh, I'm going to add these two things together. The framework makes note, oh, these two things were added together. And then when you want to compute the gradient, it just looks at all the things that were done in the tape, plays the tapes backward, and then unrolls the operations to compute the gradient. In the graph mode, so by default, TensorFlow also use that, although both frameworks are now capable of both. It's slightly different. Essentially, you write the function, and then you just say to the framework, here's the whole function, figure out, essentially trace to the function. So it's going to execute the function not using actual values, but using tracer variables that are going to figure out what operations are being performed, records the whole thing and says, okay, this is the whole computation graph. And now that you'll have the whole computation graph, you are free to figure out what the backward pass is. In the end, they are essentially the same. There are some interesting things you can do in the graph mode that are more difficult to do in the eager mode because you see what you're going to do before you do it. So that allows you to do some more optimizations. But on the other hand, it's not as ergonomic from a programmation perspective because you have to specify everything you want to do before you do it. So most frameworks now implement both. Typically, when you're trying things out, you'll be in eager mode, and then sometimes, especially in TensorFlow, if you're training the loop, then it will be preferably done in graph mode. But yeah, so this is more implementation in detail, but it does matter for some things like if you have control flow or some other aspects in your function. Okay, so one last question that you may have is how efficient is automatic differentiation? In terms of the number of operations you do, it's probably within the constant factor of the optimal thing that you could do to compute the same backwards graph. The main issue that you might encounter with autodiff is that it potentially has a quite large memory usage, because much larger than the forward progress. Because what you need to do is you need to keep the intermediate values so that you can compute derivatives with respect to them. So what do I mean? Imagine if I have this from x, I set x to be my input, I want derivative of x with respect to x. I compute y, which is cosine on x, and z, which is y squared. Then when I want to unroll the gradients backward, I can start with, say, if I'm given that the derivative with respect to z is 1, then the derivative with respect to y is 2 times y times the thing that's coming in. So in order to compute the derivative with respect to y, I need to store the value of y somewhere. And then the derivative with respect to x, so y was cos x, so the derivative with respect to x was sine x times the incoming derivative. So in order for me to be able to compute this, I also need to store x somewhere. So when I do the forward pass, in principle, I could look at x, and then after I used x, I'm not using it again, just throw it away, get y, also use y, I don't need it again, throw it away, and so on, and keep going, and I would have a constant space computation. But now in the backwards pass, I need to remember all these intermediate values to be able to compute everything backwards. So I turned something that was kind of constant space in terms of memory cost into something that's linear space in terms of memory cost. This can potentially be a problem for if you have very long graphs. So if you're unrolling some say Ode Solver or something like this, it can potentially be problematic. There are some cases where it can work. Yeah.
In general, how does the computational complexity of the backward pass compare to that of the forward pass?
Okay, yeah, that's a good question. It really depends on what the passes reflect. For a typical neural network, the rule of thumb will be 2 times more expensive for the backwards pass than for the forwards pass.
Only 2 times?
Yeah, so the reason for this is that if you think of the neural network essentially does bilinear operations. It takes the inputs, the activations, it takes the weights, it multiplies them together using some linear operator that gives you the activation for the next value, right? And then you keep doing this. And then, okay, so some non-linearities and so on in the middle, but these are pretty cheap overall. So when I want to compute the backwards, what's happening is that I take the incoming gradient of the activation, then I need to compute the backward with respect to the weights and the backward with respect to the activation of the previous layer. So if you think, the linear layer is just linear, so what are the backwards? They're just transposes. So they're essentially the same cost to compute. Not exactly, but a good rule of thumb. So you see that because I'm computing backward with respect to 2 inputs, I have 2 inputs and 1 output. And when I do the backwards, I have 1 input and 2 outputs. So that's kind of the rule of thumb. So that's typically a good guess. Yeah. Okay. Something that we'll see later, in some cases, automatic differentiation gives you something that is good, but not quite what you want, because you have some inside knowledge about how the computation was obtained. So the computation is some approximation or something, and you have some inside knowledge about how the input and the output are rated. So for example, one case that might arise is you have some computation which is not that numerically stable, and you did some specific trick to make it more numerically stable in the forward pass. There's no guarantee that this trick makes it perfectly numerically stable in the backwards pass, but you could write another backwards pass that does some other numerical trick, which is not numerically stable. A second example would be a Ode Solver. So if you have a differential equation, then using the adjoint, I actually have a differential equation that gives me the relationship between the gradient and the value. So if I step the Ode Solver forward, it's going to select the integration points in a smart way to try to minimize the error in the forward pass. There's no guarantee that the chosen integration points give me particularly good estimates for the values of the gradient on the backwards way. But because I'm solving an ODE, I actually know what the gradient should be. It has to do with the adjoint ODE, which I can write down. And I can ask the Ode Solver to actually solve this adjoint ODE, and it might pick different points, which are better suited to solving the gradient than solving the forward pass. So this is an example where automatic differentiation will do something, but there are smarter ways by leveraging the internal structure of the computation you're doing to maybe make something better. So there's a lot of work on essentially, in a lot of cases, you can just tell the framework, hey, please compute the backward pass of this component this way. I'm going to write it for you. And then you just plug it with everything else, and it'll all work together. And we'll see some examples where people have done that to pretty good success. Okay. And finally, the last thing that appears in these debriefing frameworks are these kind of modules that you can use. Essentially, there are ways to easily write parameterized functions where you don't write the parameters explicitly. So implicitly, here what we're defining a function. So as you can see, I can call it as a function. But implicitly, in each one of those blocks, there's also parameters I'm defining at the same time. And I can just get all of them. Essentially, the framework keeps track of all the parameters I have, and I can ask for them. TensorFlow works in very much the same way. So Torch is this Torch NN is the way to do these. TensorFlow is this Keras library, but they essentially work in the same way with some side differences. Like I don't need to specify the number of inputs in TensorFlow was I do need to specify the number of inputs in PyTorch. But aside from these kind of small, mostly cosmetic differences, they're essentially very similar. Okay. So now we have seen a little bit how these formats work. I want to introduce you, kind of give you a flavor of ways of using a deep network to solve a problem. So let's start with the simplest thing. So the simplest problem you might think of is, you've probably heard of this, is using, say, a convolutional neural network to classify image or predict something about image. So in this case, the problem is relatively simple. I have an image X. I want to predict its label, or I want to predict some continuous quantity of that image. And the way I'm going to do it, this is some function I don't know, right? I don't know how the image and the label are rated, but it's some function. So I can just say, okay, that function is simply a neural network. So I have a function that is unknown, and I'm just going to replace it by a neural network. And then I'm going to train on example pairs yi, xi, and be like, okay, just train the whole thing. And that turns out to work very well. In this case, there's no moving parts. There's just one function there, and I'm going to replace it by neural network. We'll see examples where we might, have more functions or different parts that we're going to replace. So this is essentially the baseline case, and I think most of you have seen something like this before. Okay. Maybe a more elaborate example would be a autoregressive text modeling problem. So this is, if you heard of GPT-3, this is essentially the framework they apply. So in this problem, instead of having images and labels, we're doing something slightly different. We're looking at the data we have, which are sentences. And what we're going to do is we're going to predict the next word in the sentence. So imagine I'm given the sentence, and then I look at all kinds of prefixes. So I look at the first 4 words, I'll try to predict the 5th one. I look at the first 5 words, I'll predict the 6th one, and so on. Now, again, this is very unstructured in that, we don't have good priors on how to predict the next word. Like the structure of sentences and so on, we don't have like powerful ways of parameterizing that. So we're just going to give up and say the whole thing is a neural network. So, how do I get from the t+1 word from the words 1 to t? I don't really know. It's a complex function. So a complex function that I don't know, a neural network. And then I get data by looking at sentences in the wild, so naturally occurring sentences that might occur, in written text and so on. And then I just train the whole network. So these two examples are kind of these. I know Miles mentioned that, said that he mentioned this idea of supervised learning, and also they have very little structure in the model they're using. They're just saying the whole model is a neural network because we don't understand a lot about the problem. There's no, there's no good domain knowledge about these problems that would help me design a better F in some sense that is not just a neural network. So this is what people do, and these methods are extremely successful at what they do. Now, something else you might have heard of is this idea of a variational autonomous. So this would be an example of kind of a mostly purely neural approach to solving an unsupervised learning problem. So I don't want to delve deep into that kind of the Bayesian variational inference interpretation because it's whole own kettle of fish, but you can think of it this way in that what I'm doing is I want to compress in some sense of lowering the dimension of an image or some other large dimensional inputs. And then I want to, from that compressed representation, decode it back into something that is similar or exactly the same idea. Now, if I were just do that with arbitrary functions, which is one way to think about neural networks, then you might know that with arbitrary real functions, dimensionality is not preserved. Right? I can kind of encode real numbers by smashing them more and more into different bits, and then it doesn't matter if it's 10-dimensional, 1-dimensional. I can kind of do these very not smooth encodings, but they have very high degree constant, but nonetheless, I can do it. So the way I'm going to prevent myself from doing this is by forcing this low-dimensional embedding to be somewhat stable in some sense. So if I hit it with noise in the middle, I can still decode the same thing. Then I'm hoping that this forces things to be smooth in some sense, and that if I perturb yourself at all, then you still be the same. So locally, you shouldn't change too fast. That would be the idea. And then there's a very nice formulation of this in the Bayesian sense, which is this variational inference that allows you to essentially compute this quantity that you might not think is computable easily. Although you can write a likelihood easily, and you can write some inference So encode it easily. This quantity is not obviously computable, but there's a trick to do it, and this is how the method works. But and again, here we don't have a lot of good information necessarily about how I can create this encoding. So we can't just give up and we say, well, to create the encoding, I'm just going to have some neural network, and to create the image from the encoding, I'm going to have some other neural network. So we can't replace wholesale the functions by neural networks, and we don't have that much more insight into the structure, so we just do it as is. This again has been a very popular method, although nowadays I think for the purposes of not doing Bayesian inference, so for like derivative models and so on, they're considered somewhat inferior in that they have issues with the quality of the samples they generate, especially for images that typically not as sharp, and we will see some better models that use some different type of structures. That is not just as simple as, okay, we're going to put two neural networks and try to compress everything, and we'll see that those work a little bit better today. Although again, this might be something that we haven't quite discovered the right way to use a variational autonomous. There might be a way to use it that is much smarter than what we're doing today, but currently they're a bit more difficult to make work. Okay. Now let's think about something that is slightly different from what we've seen, where we're not going to essentially directly necessarily parameterize something, but rather we're going to use a neural network to create a parameterization of something that is indirect in some sense. Okay, so the problem here that we want to do is we want to parameterize a distribution. So I want to have a family of distributions that is somehow very flexible, so I can encode all kinds of interesting distributions. And I want to use a neural network to do that, because a neural network is an easy way for me to have a huge amount of parameters. Okay? So one way to parameterize a distribution would be as a push forward. So if I start from a random variable that has a given distribution and apply a known function to it, then X will have some distribution that I can, in principle, compute. Now, if F is kind of an arbitrary function, X could have a pretty complicated density, right? The density will have to do with the inverses of X, but there could be multiple of them. In the special case where F is a bijection, so there's only one input for each output, then the change of variable formula tells us that the density of X is related to the density of Z, which is the point related to X, through the inverse of the determinant of the Jacobian. So this is what we can do. Is if F is a neural network, which gives us a very flexible way to parameterize things. Okay, it has to be an invertible neural network for this to work out, but it can still be a neural network. Then we can essentially encode a whole family of complex distributions by declaring that these distributions are coming from a fixed distribution to which I apply a function. And then this function then need to be able to invert it and need to be able to efficiently compute ideally this quantity here, the Jacobian. And okay, here I've given a one-dimensional example, but if you imagine there's large dimensions on each side, then hopefully there's an efficient way to compute this Jacobian without having to compute the 10,000 by 10,000 Jacobian itself. So this here we're starting to see that we're using maybe a neural network and a slightly more, yeah.
How do you make the neural network invertible?
Yeah, so that's a really good question. Essentially, you can try all kinds of tricks to make it invertible. One idea that people have, for example, is suppose that I have x1 and x2. And in the first step, what I do is I do x1 prime is f of x2 times x1. And in the second step, I do x2 prime is f of x1 times x2. Right, and then the inverse is very easy to compute. I compute those functions and then I just multiply them back, divide them back. So that's a classical example. There's
like pooling operations and that stuff. Isn't that non-invertible always?
Yeah, so you cannot do pooling operations. There's a lot of things that you cannot do. These are having the neural network be invertible is quite restrictive, and this is potentially one of the issues with these kind of things is that really. You are limited in the choices of neural network because you not only do you need to be able to invert it, you have to be able to compute this determinant of the Jacobian efficiently. And if you imagine that you're mapping images to images, for example, you're mapping something to an image. If the image has 1 megapixel, then the Jacobian is a 1 million by 1 million matrix. Okay, so you need to be able to compute that efficiently. So hopefully there's some way, and typically the way these works is that essentially each of the layers of the neural network, you guarantee that the Jacobian is identity and is upper or low diagonal in some sense, for which you can compute the determinant easily. Yeah.
Also a question. So we learn about those we do that like both sampling and the density relation should be efficient. But in practice, do you usually need both, or are there also applications where you just need to do more?
That's a very good question. So there's one problem that's much easier than the other. The problem of having efficient sampling is essentially infinitely easier than the problem of having efficient density evaluation. Because for sampling, we have this amazing trick called Monte Carlo, McCauchy Monte Carlo. I think a lot of you have heard of it. That allows me to essentially sample from pretty much anything. Okay, there might be some mixing issues and so on if the thing is too crazy, but it essentially allows me to sample from pretty much anything without too much issue. The problem of evaluating the density is much more tricky. In high dimension, the notion of a density is a very powerful notion, and we don't have all of it. You would pretty much only use a normalizing flow if you were to require to be able to evaluate the density, which can be important for some problems. One thing that we'll see later is the idea that F itself need not be a neural network. F could be related to a neural network, but not a neural network itself. So we'll talk about diffusion models where F is a stochastic differential equation. And in that case, the neural network will parameterize the equation, but F is not a neural network. And it turns out that for a stochastic differential equation, it defines a change of measure in a way that is related to kind of the neural network itself. Okay. So now let's think about something else that also happens to use neural networks. So you might have heard of GANs or generative adversarial networks. And the formalism I'm presenting here, which came a bit later, and this is kind of a retcon of how you might arrive at something like this, is known as the Wasserstein GAN. So here the problem we have is we want to learn the distribution of data from samples. So I'm giving you samples from data, and I would like to learn the distribution, at least in the sense that I can, sample from that distribution. So to be able to learn distribution, one natural way to say is, okay, I'm going to have to format the learning as some optimization in some metric. So you give me a distribution, I look at the distribution of the data, and I try to compare them to see if they're similar. Now, I'm comparing distributions, which are these kind of high-dimensional objects. And so one metric that people have to compare those is the so-called Wasserstein 1 metric. So it's a metric that is defined on the space of distributions. And you don't need to know the detail, but essentially, there is a way to phrase that metric in terms of an optimization problem, which is what I've written here. Given two distributions mu and nu, the Wasserstein 1 metric is equal to a optimization over all possible functions that are Lipschitz continuous with modulus less or equal to 1 of the difference. So essentially, we're looking at the expression under one distribution minus the expression on the other distribution, and we're trying to make them as different as possible. With the constraint that G cannot change too fast, right? If G could change very, very fast, then obviously you kind of emphasize the peaks in one and the valleys in the other, and you get something that's infinite. But since you're not able to change that fast, then what's happening is that you try to kind of emphasize the peaks and the valleys, but you have to trade that off with your constraint that the Lipschitz constant has to be bounded. Okay. So this is just math, right? It's a mathematical problem, and there are a lot of people who study this from the pure mathematical side. The field is called optimal transport, and it has applications not just in machine learning, but in all kinds of fields, and even from a pure math perspective. But now that we have access to this formulation, we can do something very interesting. What we can do is although this optimization might be hard to compute in general, right? It's a supremum. I need to search over an infinite dimensional space of functions. I could try to approximate it by trying the optimization. Right? I can get the lower bound on this by saying, okay, instead of optimizing over all functions, let's optimize over a large class of functions. What class of functions should I choose? Well, given the title today, well, I'm going to choose a deep neural network. So over a large class of deep neural networks, I'm going to try to optimize this quantity. Right. So I'm going to pick G to be a neural network from the insight that I want this optimization to be all functions, and neural networks are a good way to parameterize large classes of functions. Now, what I'm also going to do is that we did just before, I'm going to pick how can I parameterize a distribution in a very kind of expressive way. I'm going to also pick a neural network for the distribution. Right, so I'm going to do the same push forward trick. Now here, I don't need to evaluate the density as we mentioned. So F could be a general neural network. It doesn't need to be inverted by it. And I'm going to solve this problem. And again, W1 here inside, there's an inner optimization loop. So I'm trying to minimize this, but to evaluate even the cost function, I need to do another optimization problem, which is the supreme here. So what you end up is with these two neural networks, well, essentially what you're trying to do, on one hand, we have a generator, which is a neural network, which is F here, from which we get samples. And then we have discriminator, which is this function G here, which tries to make them as different as possible. And because these expectations, we can compute estimates of these, right, by sampling from mu and nu. So if I sample from real images and sample from generator, I can estimate the inner part of this optimization problem just from samples, right, by Monte Carlo. So this is an example where essentially I looked at some math, decided that, you know, the algebra math is too hard, but if I write it in a different way, and then I come up with some optimization problem of functions, and then I optimize over that by using a neural network. Yeah.
How do you constrain the, I guess, the discriminator to be rigid?
Yeah, that's a very good question, and it's one of the difficulties of this. So writing down the constraint is actually not too bad. A neural network is a composition of functions, right? And the Lipschitz constant of a composition of functions is lower bounded by the upper bounded by the product of the Lipschitz constants. So if I ensure that each of the layers I use is Lipschitz constant 1 or less, then this will work, right? And upper bounding the Lipschitz constant of the linear transformation is not that bad, right? I can just control the magnitude of the weights, for example. So this is what is in practice. I will control the magnitude of weights to very, very low level. Now, you know, this is pretty drastic in that I'm not just constraining the whole function, I'm constraining each of the small blocks of the function. So it's a pretty drastic thing that I'm doing. But in practice, it works very well in that, you know, the truth is, if you don't control it quite at this level, but at some constant level, the problem also works, right? It doesn't have to be 1. You just pick up a factor. So as long as I can controlling G to be all very similarly smooth, then this form will give me something interesting. Okay, so let's move on to another example, which is the study of contrastive learning. And the problem that we're trying to do here is where it's an unsupervised problem. So we want to kind of produce some kind of semantically meaningful embeddings from unsupervised data. So I give you an image or something, and I want you to give me some representation of the image, hopefully low dimensional, that represents the meaning behind the image in some sense that I can compare. For example, I could use that vector to search for similar vectors, and hopefully it should give me similar images. So embedding is just a function. So I take the image, I compute some function of that, and then I look at the vector, and I'm trying for that to have some meaning in some semantic sense. Okay. So again, here we're back into the world where, you know, how do I know how to construct something like this? I don't really know. It's a function, so I don't really know what's happening. So okay, let's just put a neural network for that function. And the slightly different trick here is that really what we want to do is we want that function to not be an arbitrary function, but somehow very slowly over images that are similar. So images that are similar should have outputs that are similar. The main trick and sometimes the main insight here is how do I know whether two images are similar or not? This is a difficult problem, right? I could, of course, you know, if I had labels, for example, say I knew I had images of cats, dogs, flowers, airplanes. I could say, well, clearly images of cats are more similar to each other than image of cat and airplane. That's a reasonable distinction to make. But labeling thing is expensive, whereas I could just take thousands of images. You know, everyone has a camera on their smartphone, but saying what is that thing requires human input generally, which is very expensive, and we want to avoid that. So here, this is an insight based on knowing a little bit about images. So what people will do is they will take an image and they will perturb it in a random way. So sorry, it's a bit small on the screen. But essentially what's happening is here I took the image and I flipped it. Okay, so it's essentially the same image. And here I took the image and I darkened it and cropped in a little bit. So I'm going to do these two things. And because they're images, we know that essentially say darkening or brightening the image or cropping into some bits of the image or distorting it in some small ways, this should not affect your image too much in some ways, right? Like if I take an airplane and I darken the picture of the airplane to the still picture of an airplane. So this is the fundamental idea. At least it's certainly more likely to be a picture of an airplane. Like it's closer to a picture of an airplane than if I were to take a random cat picture or any random actually picture from your dataset. So this is what we're doing. We're saying, okay, we're going to force we're going to look at the label produced by, or the embedding produced by my neural network. I'm going to apply the same neural network, or rather like a slightly, average version of my neural network to labels of an image that is slightly disturbed in some way. And now I'm going to force these two things to be similar. So this is the code I'm doing. And supposing this works, and it's completely supervision free. Now, this works because we have some kind of deep insights in some sense into what an image is, by saying that when we do these perturbations, they're similar. So this is a place where, if you have some domain knowledge, you might be able to come in and say, okay, I have some knowledge about things that should keep my data not exactly the same, right? But similar enough, more similar than if I were to pick some other random data point. Right? So I look at my data, I apply some constructions to it, and then this is still more similar to itself than some random data point I picked from my Ode sample. If I have some knowledge like this, then I have potential to be able to use this through a framework like this to do some kind of pre-training or embedding. Sorry, I think I closed my slides. Okay. Okay. Now let's look at some examples where the parameterization becomes even more delicate and complex. So here we're going to go through some kind of pretty indirect parameterization where we're parameterizing something that will then you then use to construct the function that we actually care about. So here in this idea of the neural ODE, we can parameterize the function as a solution of some initial value problem for ordinary differential equation. Right? So if I give you a differential equation, I give you the initial point or the initial conditions of the differential equation, and ask you what the value is at time t. This is a function that relates the initial conditions with the final value. Right? So this is kind of mathematically the case. Now, what I can do is I can say I'm going to parameterize the differential equation itself by a neural network. And this will implicitly parameterize the function, right? The function being the function that takes the initial value and gives me the final value. This function, this relationship changes as I change the coefficients or otherwise of my ordinary differential equation. So this is something that you can do here, right? So for example, you are given this differential equation, dy is g of yt dt, and I can then sample at different points, and these outputs at these points are essentially implicitly given to me by my parameterization of the function. So this is a way for me to say, okay, I don't want to write down the function directly. I'm going to write down the function through a parameterization through some ODE, and this ODE might be related to the physical system we're looking at. So you might be trying to learn the dynamics of a system, and you know that the system flows dynamics according to some differential equation, and you're going to parameterize it in this fashion.
Are you parameterizing both f and g?
No, so what I'm saying is f is given to me by the solution, so the solution to this ordinary differential equation.
Oh.
And then g is the thing I'm parameterizing here. Okay. So an implication of this will be an idea of, say, a Hamiltonian neural network. So the idea here is the following. For many dynamical systems, I can understand them as satisfying a partial differential equation that has to do with the Hamiltonian, which is a function that takes my momentum and position and gives me some notion of energy. Right. So here, what I'm going to try to do is I'm going to try to predict the position and momentum and observe them. But I'm not going to do it directly by taking P of t and Q of t as neural networks. Instead, what I'm going to do is I'm going to choose H as a neural network that I don't know. I'm going to observe P and Q, and then I'm going to fit my neural network so that it satisfies the differential equation in the sense that I'm going to fit this derivative to be close to a finite difference estimates of this quantity, and fit this derivative, so this derivative here to be close to a finite difference of this quantity. And if I do this, then essentially what I'll be doing is I'll be trying to make this equation hold on data observed. And as you can see here, it has the advantage of, because I'm learning a Hamiltonian, I get guarantees like if I use a good integrator, I'll get guarantees of conservation of some quantities. And this essentially allows me to integrate, for example, much further in time than if I were to try to directly parameterize the trajectories as a neural network, where I don't have a lot of control about how these evolve in time. Okay. One interesting thing to note here is that this is the loss function. And as I mentioned previously, the idea today is mostly to learn using gradient descent. So to learn from this, we need to take derivatives of the loss function. The loss function itself involves derivatives of my neural network. H theta is my choice of parameterization of neural network. So when I take derivatives of this, I will need to be able to take second derivatives of my neural network. Right? I will need to differentiate again. This is fine in most frameworks. Why? Because when you're doing automatic differentiation, the backwards path to compute the gradient, you can itself view it as a graph and apply automatic differentiation on that path. Especially for standard neural networks, this is pretty straightforward because all the operations are mostly linear. So as long if I keep taking derivatives of bilinear operations, I keep getting bilinear operations to a closed set. So I can take as many derivatives as I want. Of course, I should note that taking high derivatives is more computation expensive. This is an issue, and it's much more memory expensive. But from a kind of conceptual perspective, one of the advantages of AutoDiff is, I wrote the derivative once, I can use it again because I can differentiate anything, including the derivative itself. And finally, so this is one of the more recent models that has made a lot of noise in these contexts, is this idea of diffusion model. So again, we're coming back to this idea of parameterizing a distribution, but here, instead of doing it directly, we're parameterizing the distribution as a reverse stochastic differential equation. So a stochastic differential equation implicitly is a function between distributions, right? This is how it works. And I know that if I run a diffusion forward, I go from some data to random noise, right? If I run a large enough diffusion. Now, what I can do is I can look at the reverse stochastic differential equation that corresponds to running backwards. And it has a term here which has to do with the score function or the log marginal density, the derivative of the log marginal density at each step in my stochastic differential equation. And I can replace that part by a learn function. And when I replace it by a learn function, that allows me to essentially learn from the data what my distribution should be. So it's a way for me to turn random noise into observations by learning a score function from the data. And there's a lot more math that goes into here, but essentially you can show that there exists what's called a probability flow PDE, which allows you to compute through a PDE the distribution, so a continuous path of this SDE that have the same marginal distribution. They don't have the same point-wise distribution, but they have the same marginal distribution at each point in time. So these ideas are really, for example, what's behind clip and clip-guided diffusions, are what's behind DALL-E and some of the recent image text-to-image things you have seen. Okay. Last model I want to talk about today, which and then we should finish up this, is a model that you might think is absurd at first, but it has also reversionized a lot of graphics. So it's this idea of a neural radiance field. So the problem we're trying to solve here is an inverse problem. I'll show you pictures from different locations that are known of some object. And I try to ask you to reconstruct that object, or in the sense that if I ask you, okay, I take pictures from the side and ask you what would that look like from the top? And I'd like you to do that. So from a very classical signals perspective, this is an under-constrained inverse form, right? The pictures are linear systems. There's some unknown thing in the middle, which is a signal, and then I just want to solve this unconstrained inverse form. So the unknown signal we want to reconstruct maybe is like the color of this thing, right? The color of each voxel point in space. And we know that our kind of signal processing or measuring equipment is this, very simple. We integrate on the light ray or the color that comes in, weighted by some opacity function to hide what's behind it. So really what we're looking at is the signal, the color as a signal. And you might think, okay, this is a signal, so what do we do? Traditionally, what you would do is you choose something like a grid, right? An image, a very natural way to represent images is a pixel grid. A 3D image, you could try to represent it as a voxel grid, although it could get quite big. The idea here is, let's not try to do it as a grid. Let's replace C by a neural network. After all, it's a function of space, right? So I'm going to replace this function of space as a neural network. And it turns out that after a few tricks, this actually works. And you might think this is absurd, and I think it's pretty absurd, but it works. And now people have all kinds of applications. It's one of the most cited papers in very short time, like over 1,000 citations in a year and a half or something like this. And I think they're even using this in Google Maps now for some street view things where they reconstruct photogrammetrically some perspectives. So the reason I want to show this is, to inspire you in thinking, okay, many of these methods, what they do is they take an existing idea, right? A single processing idea, an SDE idea that's not new necessarily, and most likely not new. But what they do is, somewhere in that idea, there's a function that we don't know or that we would like to know. And we replace that function by a deep neural network. Once we have replaced that function by deep neural network, we can then use all the machinery on GPU compute and gradient descent to try to find what is the best neural network that will go there. And this turns out to be an incredibly successful idea that allows you to solve problems way beyond just casting an image. And sometimes, alongside with that, we might kind of come up with smart objective functions, say contrastive learning, based on what we know about the problem. Right? So if we know that 2 words in a sentence are more likely to relate to each other than 2 words in different sentences, we could use that idea to train BERT and have a state-of-the-art language pre-embedding. Yeah. I think that's it for me. Thanks a lot.
Any questions? I have not a conceptual question. Why didn't you cover Lagrangian neural networks?
I think there's like infinitely many variations you can do on something. But I think it's a good point in that you might know of other dynamical systems or other interesting systems that you might want to model using some kind of idea. And if you know of those and you try to replace some parts within your network, it can often lead to very interesting things. So once I had to skip because of time, is the idea that in reinforcement learning, there's notion of a Q function, and people used to in the 70s write Q as a table. It turns out that if you write Q as a neural network, it can scale much better. And then in some cases, especially where these things are kind of in the context of these things, where H should have a lot of meaning, I think Miles sometime this week is going to talk about trying to extract more meaning out of a learn function by trying to fit a symbolic function to it. So.
Oh, and I had another question. Do you think there's any applications of diffusion models for science?
Yeah, I think that's actually a pretty big one for science. It's an incredible way of writing parameterized distributions. I saw a paper pop up on our feed the other day where what they were doing is they were optimizing molecular conformations by looking at the diffusion over the torus. So if you think of angles, they are naturally over the torus as a topology, right? Because they wrap around this way and they wrap around this way. And if you think of, you can try to, the addition of diffusions, you can try to write them down in the sphere of the torus over some space that's not Euclidean space. Because they're actually defined by this kind of stochastic process. And then what you can try to do is you can try to learn that generative distribution of your angles and stuff like this using the torus. I think they show off promises and graph and all kinds of data that, of the GANs and so on might be difficult to apply on a sphere, but maybe diffusion is easier to apply on a sphere because again, it has connections. It has much more grounded mathematical connections with a lot of theory that we understand how to do. And we can carry over that theory to other spaces where they really help us. When we do things ad hoc, it might work in this thing we're thinking about, but it's not as clear how to transport these ad hoc methods into other domains. Whereas when we work with mathematically grounded problems, it's often much easier for us to understand. And the work has already been done on how to transport this into other domains that don't look as nice. Yeah.
Also regarding molecules, there was some paper from spelling that uses a current diffusion form like generative modeling for molecules. I guess it's also a scientific application.
Yeah, I think it's definitely come across my feed. I don't remember the details, but I think diffusion models have become the main paradigm for trying to write down generative models. They avoid all the pitfalls of GANs. So they tend to get much better results than VAEs in terms of generative performance. But unlike GANs, you can actually evaluate the density through a process called the probability flow ODE. So there's a differential equation, not a stochastic one, an ordinary differential equation that relates the input probability and the output probability. And because it's a differential equation, you can essentially do instantaneous change of variable that allows you to compute the Jacobian very easily.
You can get the density.
Yes.
So do people use this for like simulation?
I'm sure it's in the works. I haven't really seen papers based on this, but
I thought that's why normalizing flows were more popular.
Yes.
But I didn't know you could actually get density with these.
So this is much newer than normalizing a flow. The first successes with these methods were in like 2019, and then
I thought the original diffusion model was like 2015.
Yes, but people didn't realize anything about them back then. So between 2015 and 2019, essentially nothing happened. In 2019, one of the first papers about, hey, here's a diffusion model. And by the way, it beats GANs on images. So that was very important. That drove a lot of interest. And then people unified the idea of score matching generative models and diffusion models, which are kind of somewhat related. They're very related, actually. If you have this framework of SD that wasn't quite as developed then, once you have this framework of SD, then you can do all kinds of mathematical tricks that are harder to understand if you do not have this framework. In particular, what you'll be able to write is a ODE that has, if you follow the path of the ODE, marginally, it has the same distribution as the SD. So if I look at point time, then the path of the ODE has the same distribution. And then not because of ODE, I can compute the gradient, the Jacobian, through my ODE. That is also another ODE. That gives me a change of variable, and then I can compute the reweighting necessary to go from the Gaussian noise to this. There's still a lot of challenges that people are addressing with these models. They can be very expensive to sample because you have to solve a stochastic differential equation to sample. And the weights of the stochastic differential equation are given by neural network. So every time step of integrate you do, you have to evaluate a big neural network. So they can be expensive. There are ways, again, to try to say, okay, we can have better integrators. Again, themselves are neural networks. So the integrators of neural networks of SDEs that look at different places. Then they look at the weights, and then instead of using RK4, you use something much smarter, driven by neural network, and then you can do fewer steps. So there's all kinds of research in problems like this, and I would really encourage you to think broadly about where can you fit a neural network, and whether that might make sense in the context of your problem.
So perhaps related to this, what do you think about neural flows? I'm not sure, like in all this paper, they kind of propose to directly learn the result of the flow instead of parameterize the ODE, so you don't have to go to the neural network with the Ode Solver every time. Although they kind of used it only in 2 examples. I don't know, perhaps you have an opinion on that, how well that is scalable, more realistic applications.
Yeah, so it's funny. Here, what I'm saying is it's a good idea to turn a direct prediction into an ODE, because you get some guarantees of the Ode Solver, and it might be much nicer. For example, here, right, we have a Hamiltonian thing. It's much better to farm to the Hamiltonian than the path. But in some cases, we might be interested to do the opposite for all kinds of reasons. Right? One idea is this idea of coarse grading simulation. So some PDs or ODs might be, well, not really ODs, but some PDs might be extremely expensive to run in that, molecular dynamic simulation, weather simulations, and so on. One idea could be, can I predict, 10 steps into the future using a neural network based on the current state? And then maybe I can do that, and it varies much faster than in neural network. There's also work in using neural networks to learn force fields, for example, in the context of molecular dynamics, right? The forces that interact within the atoms is driven by some quantum mechanics that is hard to evaluate. So what people do, they use heuristics that look at angles and all of that kind of stuff. Okay, we're using a heuristic already, we're not trying to learn a neural network and so on. So there's definitely all kinds of applications where you might want to coarse grain, so you want to jump ahead using a neural network. Of course, the problem with those is that how do you guarantee that you have any accuracy when you jump ahead? That's very difficult to see. I think there's a lot of interesting things that you can do there where sometimes, so you don't have to always use your neural network to jump ahead. You could use the normal, your normal dynamics that you already have on the HPC. So for example, if you're trying to do some optimization based on some numerical simulations, you could start your optimization by using your neural network approximate model. And once it's good enough, hopefully, you can switch to the actual true model and then refine the optimal solution a little bit. So you give yourself a head start by using an approximate model that is driven by neural network. And then at the end, you still use the true model because you trust that more and it's more realistic and you won't have all the issues that could appear.
Thanks, Ken.
I guess I'll introduce myself. I'm David Hogg. I'm at Flatiron at the CCA, and I'm also at NYU, and I work on computational data analysis things. Am I allowed to take this off? Do you know what the rules are? Speaker can take off? Okay, good. Okay, good. I'm going to talk about linear models. I work on computational data analysis. I've worked in a lot of areas. I work in cosmology. I also work on exoplanets. I work on the Milky Way. I would be here for more of this. In fact, I would be here to do more things, except that Gaia DR3 is happening on Friday, and that is literally taking 100% of my brain right now. And if you don't know what Gaia DR3 is, I suggest you find out, because if you're interested in data and computational data analysis and machine learning, the number of projects that are going to become available because of DR3 is just ridiculous. Just something to put in there. Good. I'm going to talk about linear models. I volunteered to talk about linear models because at some level, I hate machine learning. So in astronomy, I'm kind of known as one of the people who introduced machine learning in astronomy, because way back we were doing various things. But I like to do simple things. And so I'm going to talk about extremely simple things. And some of you are probably working on very complex things. And I want to encourage you to think about simple things that might achieve the same goals. So what I'm going to do, my current outline is I'm going to start with a problem setup. I'm going to explain a problem setup, and then I'm going to say why you might be interested in this problem setup. Okay, so we'll start with the problem setup, then we're going to talk about why. Okay, good. So the problem setup is that you have some data y. Whoa, that's not the data you have. You have some data y, and this is going to be like, and this thing is going to be, let me not get this wrong. This is going to be an n by 1, meaning you think of this as a column vector, n data points. And our model for this data is going to be that there's some set of features x, and this thing is going to be n by p, meaning there's p features. So this is like rectangular data, rectangular features. For every object, you have a set of p features, and times a parameter, a weight vector, a weight vector, which is going to be p by 1. And this is not your whole model because, of course, there is noise. And that is a linear model. The linear model is that your data is explained as a set of features times a set of weights plus noise. And I have written a 60-page paper about this model, which is, let me give you an archive number. By the way, I will give a set of archive numbers in this talk, 1008. If you don't know what an archive number is, ask me afterwards. 86, this is Hogg, Bovey, Lang. That archive number, there's a 60-page paper about fitting a straight line to data. This is a straight line. Why is it a straight line? Because it's linear with respect to the features that you have chosen in advance. The idea of this is that your data are the y, the features x is some rigid set of objects you have, and you're trying to explain the data as a linear combination of your features. And one example of that would be like in the LIGO data. So the LIGO data, I don't know if you've thought about the LIGO experiment, but the LIGO experiment measures a gravitational wave strain that is literally a single scalar number at each location. They just have a scalar that they're reading out, and then they have 10,000 channels of housekeeping data. So then you could try to explain the scalar number you have as a linear combination of your 10,000 channels of housekeeping data, or of functions of the 10,000 objects. If you go to quadratic, you'll have 10,000 choose 2 plus 10,000 terms in your linear plus 1 terms in your linear model. You keep going, you can imagine making big linear models. Okay, good. Good. The paper that I mentioned here, this paper takes a kind of sorry, it takes a kind of probabilistic attitude. What do I mean by that? I mean that in that paper, we talk about a likelihood function for this problem. We talk about priors. We talk about marginalization. We talk about MCMC. We talk about inference. So if I had to distinguish machine learning from other kinds of computational data analysis I do, I would say that in most of the computational data analysis I do, I want to make a generative model for the data. I want to explain the data as a result of a process. Whereas in machine learning, you're more like trying to interpolate your data, and you're trying to kind of ignore a little bit what the physical process is, or what you really think the causal model is. You're trying to think, how do I interpolate these data? I've got a lot of data, let's interpolate them. So I can work in either mode. That paper that I'm citing, which you can't read there, I didn't realize how light green is, but whatever. That paper is really about the probabilistic attitude, like if you're a statistician or if you want to do things that saturate bounds. So like you think in terms of information theory or whatever, that's kind of where that paper sits. Okay, good. But in what I'm going to talk about now, I'm going to think about it more from a machine learning perspective. So I'm going to more think about it like there's some data, you want to explain it, predict new data, interpolate data, find outliers, things like that. Okay, good. By the way, there's another form of a linear model, which I'm not going to talk about at all, which is that you can have a classification where the classification is y is x dot b, sorry, I shouldn't say plus, greater than some threshold. This is like a classification model where you build a linear model that you then threshold, so it gives you trues and falses, and those are like object category A, category B. So there's a way you can use linear models to do classification. I am not going to talk about that at all. So I'm going to think about it entirely in terms of regression. So this talk will be entirely about regression, not about classification. But you can also do classification with this model. It works exactly the same way. And if you want to ask me like detailed questions about classification, stop me at any time and I can give you how it's going to look different. Okay, good. Okay, so the way this works usually, I haven't told you why you would do linear models yet. I'm going to get there. The way this usually works is that you are trying to find kind of the best parameters beta. And so writing in the usual machine learning way, you're trying to find the best parameters beta hat, and those best parameters are set by some kind of argmin over beta of some like norm, like y minus x beta. There's a dot in there. Something like that. Does that ring a bell? That's like machine learning terminology, right? So this thing here would be your loss function, and we minimize the loss function that gets us our weights or whatever of our model. Now, the cool thing is, if your loss function is a standard norm, like the L1 norm, the L infinity norm, the L2 norm, anything like that, your problem is completely convex. So we're going to come back to that in a moment, but the point, one of the reasons linear regression and linear models are so valuable is they provide convex machine learning methods. And you may not have thought about how the value of convex is, but oh my God. If you've optimized the big machine learning model, you know you can get stuck all over the place and you do all the sorts of weird things with dropouts and stochastic gradient descent and learning rates and all sorts of shit, and it still doesn't work. None of that. You literally just go downhill, you get the right answer. Linear regression always works. You never have to think about how you optimize it. And we've optimized linear models that are bigger than fit in the data center. Not that are bigger than fit in RAM, bigger than fit in the data center. You can optimize a model with 1 trillion parameters. It's convex. When things are convex, you can do basically anything. So we'll come back to that in a minute. Now, what loss functions do you have? I just want to say there's many loss functions out there in the world. There's a whole wild world of loss functions. So so for instance, there's things like y minus x beta, the L2 norm squared. But then sometimes people add a regularization that tries to make the parameters small, the weight small. And if you make this a 2 norm, that's great. That's a lovely thing to do. That keeps you in closed form. If you have that solution, we're going to see there's a closed form answer to that problem. I'm actually going to solve that problem in detail in a minute. But you can also do things where you make this a 1 norm, and then you get sparse solutions. And you might have heard that this is compressed sensing. Is that a word you've heard? Sparse models. And there's actually proofs that when you put on these L1 norms, you actually get the right answer in certain contexts. Okay, so there's some gorgeous things about linear models. By the way, do you guys know about norms? Have you talked about norms yet? Haven't talked about norms. So let me just use a little terminology here. So a side note on terminology. So if you have like A minus B like this, and you have a number here, and you have a number here, that norm, God, I hope I can write this correctly. I'm sure I can do this. It is the sum over components. So there's the AI minus the BI, like these are vectors or tensors or something like that. So I'm flattening it out. I'm summing over components, okay? And then I take that thing. Good, to the nth power. I think it's nth power and then nth root. No, it's nth root.
And then it q's power as a root.
Nth root. Do I believe that? But squared, you're squaring it.
Oh yeah.
See, I think it is this. Sorry. Yeah. Yeah. Thank you. See, this is like machine learning in real time. 1 over n. Good. And then this whole thing to the qth power. I guess I could have just said q over n on that thing, but that's the way I think about it. But so the idea is that if you have the 2, 2, it's just the sum of squares. And 2, 2 comes up a lot in physics because why? In physics problems, we like chi-squared, like if you have a Gaussian, if you think that your noise model is Gaussian, then you care about the sum of the squares weighted by the inverse variances. Ring a bell, chi-squared. I don't know if people learn that. It depends where like what field you grew up. There's something called chi-squared, which is like the sum of the model minus the data over the error squared. That's what we call chi-squared. And in this context, that's not what we do. In this context, what we do is use a model that looks like this: y minus x beta. Oops. Sorry, people. X beta transpose dot C inverse y minus x beta. So what's this? So, and I'm running out of room. Sorry, I promised I wouldn't get in. By the way, if I go below the bottom of the screen, you have to say something. It's your job. So what is this? So the idea of this is like the residual. This is your data. This is your model for the data. There's your residual. There's your residual again. Because this is transposed and this is not transposed, that's an inner product. So you get a scalar number. But we're weighting it by an n by n matrix. You see, this is an n vector. This is a horizontal n vector. This is a vertical n vector. We're doing the dot product of those two things through a weight, which is an n by n thing. And I'm only spending some time on this because you'll learn about Gaussian processes later. And my God, this matters for Gaussian processes. This is like the likelihood function for Gaussian processes. And this thing will become a kernel matrix, which is about some relationship between your data points. Anyway, Gaussian processes will come up at the end of this talk. Okay, this expression is chi-squared. Why is it chi-squared? Because this is the inverse variance of your data. This is like an n by n matrix that contains your inverse variance information. So it's like 1 over the error squared goes into this matrix. If you put it on the diagonal, you get exactly this, but this is a more general noise model. And this noise model applies to anything where you have Gaussian noise. So this is where why linear regression is so cool. If you think that your data is generated by a linear process and you have Gaussian noise on that, this is your objective function. And if you optimize this, your maximum likelihood under that objective, and that's like saturates information theory bounds and all sorts of things. So this model is incredibly powerful. And there's a lot of things in physics for which this is exactly true. Yeah. This is very related to MCMC in the following sense. This thing has a probabilistic interpretation. This thing is, this is off topic, but let me say it. This thing is -2 the natural log of the probability of the data given the model under some set of assumptions, under the assumption that the data are generated by this linear form plus Gaussian noise. And this object here appears is the likelihood, which then goes into a model that you could then do MCMC with. So this is connected to MCMC very strongly. But the funny thing about this problem is when you're a linear regression, the model is so simple, you actually don't need MCMC. We can do everything in closed form. So I'm going to give you a full closed form solution for linear models. Okay. If you have a model that looks like this one, if you have a model like this one that has the L1 norm in it, you won't have a closed form solution, but you still have convex optimization, which means if you turn on any optimizer you like, you will get to exactly the correct answer if you wait long enough. So one of the things I love about linear models is you never need to touch stochastic gradient descent. You'll never use stochastic gradient descent in this area. And if you ever do, you're making a mistake because stochastic gradient descent never finds the true minimum. It always orbits randomly around the true minimum. But here there really is a true minimum you can easily find. So linear models are kind of not machine learning because we are not doing any of the standard machine learning things. We don't need any backprop. We don't need any stochastic gradient descent. We don't need any layers to our neural network. We have just a convex problem. But it's very like machine learning in that we can put in arbitrary features. We can make our problem very large. In fact, I'm about to make the problem infinitely large. It might surprise you to know that you can actually do problems that have an infinite number of free parameters in this problem, which we'll talk about at the end. Okay, good. Everyone with me? Good. So there's lots more to say there. I can say a million things. What do I have written here? Oh, yeah. One, not sure when to say it. No, we'll talk about when we get to features. Okay, so let me talk about why. So why? Technically, this is section 1. That was section 0, which was the setup. So section 1, why would you do linear models? After all, you're presumably during these 2 weeks learning how to build 42-layer ReLU networks with pooling and hinges and all that stuff. I don't know what you learn in there. I don't know. And I like to make fun of all that stuff. Actually, the networks that I make fun of always have 42 layers. That must be a 42-layer ReLU network. That's a thing I say. So why would we use linear regression when you have all those tools available to you? So the answer is, there's many answers. The first answer I've emphasized already. One is convex optimization. So linear models can do remarkable things, and I won't say that much about what it can do. I'll give you an example in a moment, but they can do remarkable things, and with convex optimization, meaning you know optimization tricks, you just go downhill, you get the right answer. Actually, I'm going to show you things. Sometimes you even have closed form, so you don't even have to do an optimization. You just closed form, go to the correct answer. I'll show you that in a moment. The next thing is that I would say is linear models are very interpretable. Meaning, you have a set of features and you're going to combine them in a linear model. You can just look at the weights and ask, what were the most important features? It's just not that hard. And you can see that when it wants one weight to be big on one thing, it wants to be low on the other. You can drop a feature and ask, how do things change? They're just really easy to interpret. Totally different from the weights inside a neural network. In fact, the weights inside a proper neural network, your 42-layer Wheeler network, the reason those weights are not interpretable is there's actually complete symmetries inside that network. You know, you have all this connection. That means you can rotate within the connections, and then you have exactly the same model with totally different weights. So it's almost impossible to interpret the weights inside a network. And lots of people would disagree with me, but they're wrong. The weights inside a network can't really be interpreted, but the weights in a linear model are always very straightforward to interpret. And related to that, you can enforce sparsity, which means if you put on that like L1 regularization, that's trying to force parameters to go to exactly to 0. Many parameters will go to 0, and that just shows you those are less important parameters. And there's even proofs in that context that you will get the correct set of parameters. So if you generate data with a model and then you fit it with a lot of parameters, some of which are part of your correct model, some of which are not, it will zero out the wrong parameters. There's some proofs related to that. So like you can do things with this model that are very, very interpretable. And so as a scientist, we love linear models because I don't care whether the machine knows how to predict my data. I care whether I know how to predict my data. So the next thing I would say is that with linear models, you're going to explicitly construct your own features. We have to make this matrix X. There's this matrix X here of features. We have to construct that matrix. That's an input to the problem. That's some machine learning people, if you ask Jan LeCun, he'll say that's a terrible thing about linear models. You have to make up your features. Shouldn't the machine learning method find the features for you? That's what he'll say. But I disagree because I'm a physicist and I know in many cases when I'm working on what kind of features I want. I know my problem is time translation invariant, or I know my problem is rotationally invariant, or I know my problem has permutation invariance. Then I can make the features that have the symmetries I believe are there. Another thing is I think this problem will depend on the temperature, but I think it won't depend on the magnetic field. I can put in the temperature and not put in the magnetic field. I can make choices very straightforwardly at a low level in this problem. So feature construction, you could put either on the plus or minus side of this. The minus is you have to construct all your own features. You don't get to use your neural network to produce your features. But the flip side is you get to construct your own features. And so it's not doing crazy crap. Okay, good. And then last thing I was going to say is there's a bunch of information theory. And if you're interested, there's actually a lot of really, really good math around linear models. By the way, there's very few proofs about neural networks. There's very few proofs about what they can do, like universality and saturation of bounds and things like that. But there's tons of proofs for linear models. And in fact, nowadays people write these models, they say there are 2-layer neural networks. Which is amusing because it's a way to say, oh, I proved something about linear regression, but have it be relevant to the world. And for instance, there's a very beautiful thing called, there's a very beautiful theorem, I'm just like name checking this, Gauss-Markov. The Gauss-Markov theorem shows that linear regression produces the minimum variant, the standard ordinary least squares linear regression that I'm going to show you in a minute, gives you the minimum variance unbiased linear estimator in a problem. So it like saturates an information theory bound, which is not something you can ever be sure of in other contexts. So this is like, linear models have a beautiful role in science, because if you want to be able to say provable things about what you're doing, linear models are where you want to be. And that's where I work. Actually, if you had to characterize my research, I like to work on models where we have rigor, where we can rigorously prove that we're doing correct things. And sometimes we have to sacrifice performance for rigor. So there are problems where we lose a little performance, but we get rigor. And I'm willing to take that trade because I want to know that I'm adding stones to a brick wall, to a stone wall. I'm not building the straw house of the three little pigs. I'm building the stone house of the 3 little pigs. Okay, good. Which, by the way, did defeat the wolf. Oh yeah, there's one more thing that I should say is because linear models are convex and you know you're coming to the correct solution, they are great benchmarks. So there's many problems in astronomy where people do machine learning and get beautiful results. And then we do a linear model and we get just as good results. And that's a good example. Like that's a place where, so I can give you an exact example. I wrote down a reference here. Say again. Oh, sorry, thank you, well done. Love what you're doing. So here, one example is the Canon, which is a model for stellar spectra, and the archive number is 1501.07604, and that's Melissa Ness and various other people. But that model is a linear model that explains stellar spectra, and it's a linear model in complex features. We made complex features, but it's a linear model and it does as well as any machine learning method. Many people have worked on machine learning methods. The Canon does just as well as sophisticated machine learning methods, and it's a pure linear regression. So that's a very nice example of something where you can build a benchmark in linear regression and actually it's hard to beat. But the flip side of that is Melissa Ness and others, including me, spend a lot of time making those features correctly. We had to think about the features. But then we made a very good model and it's hard to beat. Okay, good. Questions? Okay, it's about to get technical. Yeah, hit me.
How effective is it when you can't like create good features, handmade features, like linear models? How effective is it?
Right, so you could ask the same thing, of course, in real machine learning, right? When you have your network, you still have to put things in the bottom that are good. So you need good features that are informative, but that is the problem with linear regression. So you have a huge amount of choice about what features you put in, and the linear regression is totally agnostic to that point. It doesn't really give you any feedback about that. All the linear regression does is say, you suck, and you try to find more features that do well. Whereas if the constituents of good features are going into the bottom of your 42-layer ReLU network, you can hope that at some layer in the network, it will produce good features, and then you're good. And in some sense, you can think of everything but the last layer in the 42-layer ReLU network. You can think of everything but the last layer as being constructing features to do a linear regression at the end, right? And so the answer is, I don't really have an answer, but because the proofs, of course, you can imagine the proofs are assuming that your features include the features you need. But in normal in like contemporary machine learning, where you have the networks, you need to make sure the constituents of your features are going in the bottom, whereas we need the actual features to be going in the bottom. So it does move effort to the investigator, for sure. And that's all my only answer. A little bit. Yeah, I can't. And of course, actually, one of my students is doing a big linear regression right now, like very big. And she is struggling with that issue because we have a lot of choices about how to order our features. We can make an infinite set of features, like we have an infinite set of features. So but then the question is, what order do you look at them? If you have an infinite set of features, you can't put them all in. Actually, you can. We're going to see that in a moment. You can sometimes, but in her case, you can't. And so we have to think about in what order do we try them? You see what I mean? Because if we can't try them all because there's infinity of them. So we're trying batches of them and asking, and we have to decide what batches to look at. And that's a hard problem. And if we mention that to, as I mentioned, Jan Lagun, he would say, why are you doing that? Just put it into the deep network and that'll figure out what features to put in. But of course, one of the reasons we're doing that is the student and I were trying to impose strict symmetries on the problem. So we only want certain features to go in. We don't want the network to be able to do whatever it wants. We want things to be coordinate free and certain geometric properties. We want them to be dimensionless. We want various things to be true. And so we want to control the problem.
Do you like enforce the constraints while choosing the features, or do you make those part of the model?
Great. And I'm not going to talk, actually, when I volunteered to give this talk, I said I could either talk about linear models or I could talk about like equivariant machine learning, like group equivariance, which is something I work on. And with group equivariance, if you work on like invariant or equivariant machine learning, you have to decide, do you build the equivariance into the structure of the network, or do you build it somehow into the things you put in? And I'm on team things you put in.
Why?
Because then you can just repurpose existing technologies. So we took a neural network that was best in class for a particular physics problem. We took the inputs, we made them dimensionless, and then the problem just worked better. We didn't have to worry about what were the dimensions all the way through here. We just put in dimensionless things in the bottom. There's no way they can get dimensions on the way. Came out dimensionless, we got a better answer. So we like that repurposing existing hardware. But there's only some problems are amenable to that. There's many problems where you can't find the right kinds of invariants, and then you can't do that. And then you have to put it into the network. So it's a very detailed question, like where you modify your method. Yeah. I love how off topic we are.
Are
Yes.
there any theoretical proofs in the direction of generalization and extrapolation of linear models? Or like,
No, we're actually trying to get proofs on, we're trying to get proofs now. So I collaborate with mathematicians. Actually, I'm going to cite our work with mathematicians in just a minute, where we're trying to get proofs about if you reduce the feature space to a feature space that obeys the symmetries you believe are there, whether you can prove that you will do better on problems. We find observationally we do better on problems, but proving it's turning out to be very hard. There's no proofs basically about extrapolation or generalizability right now that are useful. I mean, there is a proof that we were looking at, but it doesn't help you much in the real world. Most things that are provable don't help you much in the real world. That's my current thinking. But if you send me that as an email, I can send you back a specific paper that thinks about that question.
thank you.
Are there proofs for like infinite data or something like that, right? So those are
Yes.
the edges where it doesn't.
Right. There are
Yeah.
proofs. There are proofs for. Yeah, there are some asymptotic proofs. Actually, I'm going to show you an asymptotic result in a minute. There are some interesting asymptotic results that have some relevance, but many of them don't have much relevance.
Yeah.
So we've been working on some problems that look like causal inference, where you have a spacecraft observing stars, and the spacecraft is varying and the stars are varying. And the question is, when you see the variability in your data, is it coming from the spacecraft or from the stars? See how that's a very nice problem? And we're doing it using correlation. So if there's correlations in the variability of the stars, it has to come from the spacecraft, because stars in the real world don't correlate. So cool, we're solved, problem solved, we win. And then it turns out, no, that doesn't work, because you need infinite data for that to be true, because in any finite data set, in fact, the stars all correlate. So the proof, we have proofs that what we're doing should give you the right answer, and they don't. Why not? Because they're in the limit that you have an infinite time series. Yeah. That's the kind of, that is an area I work on. By the way, that's another reason I should have given that as another reason to work on linear models, is that if you're doing things like causal inference, or are you doing something more complicated with your model, you're trying to do some higher level inference, the linear model is valuable because it has a structure you can understand. Like, we fully understand the model we're building of the spacecraft and the stars because it's all linear. If it was nonlinear, it would be much harder to disentangle what's coming from the spacecraft and what's coming from the star. Yeah, that's the kind of problem I work on. I love problems like that. Okay, good. How are we doing? Okay, here we go. So this has already almost come up, but the question is how to make features. X. So let me just remind you, let me go back up here. I just want to say a few things about this problem. Here's our setup. Let's just annotate our setup. This y vector is n by 1, as I said. This feature is n by p, and this weight vector is p by 1. Meaning the data are a column vector, the x is a big rectangular blob, and then b is a column, beta is a column vector as well. Okay, so that's the setup. And then in general, there's training data and test data. So there will also be test data. There'll be like y star, which are test data, which is x star times the same beta plus noise. Right? And there'll be both training data and test data. That's our setup. Now the question is, how do we make features x? And then I could also say x star. The features, both for our training data and our test data, how we make those features. And there's many choices here, and this is like where all of the art, this is like the art, so I should call this the art of linear models. You have to decide what are you going to put into your linear model, and that's complicated. Now, you might think, well, linear models are very restrictive because I can only have the model depend linearly on what I put in. But what I can put in can be the time squared, the time cubed, the time to the fourth, the time to the fifth, and so on. And then I can get an arbitrary polynomial of time, you see? Or I can put in sines and cosines of my inputs, or I can put in products of my features and products of triples of my features and powers of my features. So you might think, well, a linear model is terrible because it's only a straight line, but it's a straight line in a lifted space that can involve all functions of your inputs. In fact, you can lift it, as we're going to see at the end, to a full Hilbert space, like an infinite dimensional Hilbert space of your input quantities. So you have a lot of freedom. It seems like a very restrictive model because it's just a linear sum of things. But a polynomial, remember, is also a linear sum of things, and a polynomial can represent any analytic function in a neighborhood. Right? Literally any analytic function in a neighborhood can be modeled as a polynomial. That's what analytic means, actually. That's literally the definition of analytic. And that's just a linear sum of terms you could write down. So linear models have more flexibility than you feel like they do because you get a lot of freedom with the features. Okay, so how do we make the features? Okay, so one way to make the features is sometimes you just have them. Like, for instance, I mentioned that the LIGO data has 10,000 channels of housekeeping data that come with the data. Well, if you believe the noise in the experiment is a linear combination of the housekeeping data, you've got 10,000 channels of housekeeping data. That's an extremely flexible noise model you have. You have a 10,000 parameter noise model now. You just have those features. You don't have to do anything. Like, literally, the experiment just gave them to you. You can make the noise model as a sum of those features. And if you don't think that's enough, take all the products of the features. And that gets you up to, I don't know, 400 million or something. So yeah, sometimes you just get them. And then sometimes you make them, and of course, really usually do both of these things, make them by taking functions. Okay, so let me give you a very concrete example. So imagine I have in some space y, there's my data y, versus some parameter t, which you can think of as, say, the time at which I take a bunch of data and I get some data points. Here's some data. And I want to interpolate these data. So what I want is some, function that interpolates these data. That's what I'm looking for. That's why I'm doing linear regression. Now you might say, well, look at those data. There's no way that these data can be interpolated with a linear model. But of course they can, because I can take time I can do any function of time I like and include it as a feature. So if I was going to try and model this with, say I was just trying to interpolate these data. By the way, one thing I should say is all of machine learning, in my view, is just interpolation. Like, how do you find pandas in YouTube videos? You take YouTube videos that do have pandas, you take YouTube videos that don't have pandas, and now you take a new YouTube video and you ask, does it live in the interpolation space of the videos that have pandas, or does it live in the interpolation space of the videos that don't have pandas? Boom, you found your pandas. So that, I think all of machine learning is fundamentally interpolation. So here's a trivial interpolation problem. You have a few points, y versus t. How do you set up your matrix X? So what you do is you make this matrix which has 1, 1, 1, 1, 1, 1 down this first column, and the next one, thank you, good call. And then the next column, it's going to have sine k t. I guess I should call it omega because I'm a physicist. It has sine omega t for the first data point, and then it has sine omega t for the second data point, and sine omega t for the third data point, and so on. And then it's going to have cosine omega t for the first data point, cosine omega t for the second data point, and so on. And then it's going to have sine of 2 omega t for the first data point, and sine of 2 omega t for the second data point, and so on. And then it's going to have cosine of 2 omega t, and so on. And you see how I can make an arbitrarily large feature matrix this way? I can put in ones and then sines and then cosines and sines and cosines, sines and cosines, and I can go as long as I like. And you see, I can go, I'm going to go this way. This way, I'm going to go p times, and this way is my data. That's n times. I have n objects, and each of it I have p features. And here I've hand constructed these features. And you might think, well, that's ridiculous. You could have chosen anything. This is bullshit. It's totally subjective. First comment is all data analysis is completely subjective. Second comment is actually these functions are a representation of time translation invariant spaces, right? If you do your group theory and you ask, I have time translation invariance in one dimension, what is the natural basis for explaining functions? Sines and cosines. And so this is actually a very natural basis if you believe you have a stationary process at your disposal. Imagine this is a set of measurements of the brightness of a star. Well, the star didn't tell you what time to start observing it, so it's probably generating a stationary output, and therefore you want to represent it in a stationary basis. So this is actually a beautiful model, actually, for. And notice I can control p. Now I can set p to anything I like. I can just take more and more terms in the sequence if I like, or fewer. So I have complete kind of authority over this. Also, I can decide I don't care about high frequencies, and you can cut them off. Or I can say I don't care about low frequencies, and I can set the minimum omega that I use to be large. See, there's all the choices that I want there are there. I can say I want stationary, you see? Now, imagine I have multiple dimensions, not just time. In most of the problems you're working on, you have like many more parameters than just the time. You have all sorts of things. You have the temperature, you have the magnetic field, you have the polarization, you have all sorts of other things. Well, then you're going to have to use a more general basis set than this. But you can see how you could just use all the functions in the basis set. And I particularly chose this one as an example because this is also a Hilbert space. Yeah. For instance, yes, Fourier analysis actually, yeah, in fact, the problem that we're going to show will look like that. But it doesn't really matter because you could also do polynomials here and nothing I'll say will change until the very end. So, right, you could do polynomials here. You could do, if you were on the sphere, these could be spherical harmonics. And then sometimes you don't have those symmetries, and then you might want to use more random functions. In fact, some people literally use random functions. Right? You can randomly generate polynomials, and then you can just evaluate random polynomials. You can put them in. And you just choose P random polynomials and use them. That's also allowed. Right? So you can do. Say again. Yeah, it's very related. Yeah, I mean, I'm not going to talk, actually, I'm not going to talk about sparsity much, but yes, this is actually quite a good problem to think about those problems for sure. And actually, I'm happy to take questions about that because I thought about that a little bit. Okay, good. So my point here is, first of all, sometimes you just have the features you want to use. Like when in the problem with the stellar parameters, we knew that all that matters really is the temperature of the star and the surface gravity of the star and the metallicity of the star. We knew that there were just certain things we needed to know, and we used those as features. Sometimes you don't know what your features are, and so you just expand them out. You like lift them up into some function space. Sometimes you do a combination of both things, and sometimes you use a lot of knowledge you have about the problem. Like if you just know that there aren't frequencies higher than something, you just don't use frequencies higher than something. Or if you know that the temperature can't matter in this problem, you drop the temperature. Or if you know the magnetic field is very important, you might go to higher degree in the magnetic field than other things because you know the magnetic field needs to be in there. Various things. So this is the art of the problem. I literally said this is the art of the problem. That is where you have to make decisions, and that's the limitation of linear models. Okay, good.
Isn't in that sense basically all of science manual feature engineering?
In some sense, yes. Actually, we wrote some papers in the last year about how to make, as I mentioned earlier, how to make problems like equivariant with respect to certain group actions. And our referees came back saying, this is just feature engineering. And we're like, no, it's not feature engineering. It's about enforcing exact symmetry. And then we're like, oh yeah, it's actually just feature engineering. They were right. And so in some sense, you can think of all of science, yeah, as being feature engineering.
Because in the end, also the variables that you're using were like engineered or decided upon at some point.
Exactly. And even if you're using your 42-layer ReLU network, you made choices in there that were effectively feature engineering. Even the number 42 is a feature at some level.
There was a paper for like speech and music processing where they first trained an encoder to predict like MFCC, which are the spectral coefficients, which are like the best performing features, and then not froze that, but maintained that encoder and trained a linear predictor over that, so that the encoder would be similar to predicting the subsource coefficients, but not exactly it, and that apparently performed better.
Yes, we've done some things like that. There's some, that's a very good thing. So for instance, if you're doing image processing, so one place where people don't generally use linear models is in image analysis and image processing, although I do that. I have some linear models. But one of the things we've done in image processing is we've taken an existing trained network that works on ImageNet. We cut out a layer near the top. We call those our features, and then we do linear regression with those features. And so we let the previously trained network tell us what features to use, and then we use them. Because you're allowed to get your features from anywhere. Now, of course, the disadvantage of that, of course, is we lose some interpretability because now we have these features that are just these random things that are produced by it. But sometimes they're very interpretable. You've probably seen the things where in neural networks on images, they look at neurons at intermediate layers and they look like stripes and spirals and dots and things like. So sometimes they are interpretable, and we do think that those things are valuable. Yeah, so that is actually one of the strategies for finding features. So as usual in science, you have this big knob to turn between making all the choices yourself because you know best, letting the machine make all your choices. And linear regression lets you work any place in there you want to work. And that's kind of why I love the linear regression side of machine learning and simple models, because you have a lot of control over what you're doing. Okay, good. Okay, now we're in section 4, according to me, which doesn't make sense because the last section was 2, but whatever. This is now section 4. There was no section 3. Okay, good. How to optimize. So I said that we're going to do that. This weight vector is the argmin of something. Argmin over beta of some loss, which is going to look somewhat like this, maybe plus some penalty on the coefficients as well. Most of the losses we do look like that. Okay, so there's some kind of, I've drawn that very badly, but that's supposed to be a norm of beta, and this is a norm of, so there's a norm of beta and there's a norm of the difference between the data and the linear model. And the norm of beta is trying to control things so you don't get crazy ringing where it's doing like 1,000,000 times one feature minus 1,000,001 times the other feature. And the first part of it is trying to make the model predict the data well. Right, so that's what typical kind of loss that people do, and how do you minimize it? Well, the first comment which I made earlier is that this is completely convex. So if you don't like using your brain, just put it into any optimizer and go get a cup of coffee. You will get exactly the right answer. It is guaranteed. If you don't get exactly the right answer, your optimizer is broken and you can sue. So it's really trivial. And in fact, there's a whole mathematics of convex functions. And if you know things about your convex function, you can optimize really well. And in fact, in the cases where you're either using L2 or L1 or a mix of L2 and L1, there are custom things. L2, you use linear algebra, although actually the way linear algebra is done under the hood is with conjugate gradient, but whatever. If you're L2, you do conjugate gradient. If you're L1, you do these crazy iterative schemes that Candes invented and various people expanded on. And if you're a mix, you do the crazy Candes things. But you don't have to learn anything. Don't learn that. You don't need to. You literally can put it into any optimizer and we get the right answer. It just, you're done. If you program this thing in JAX, you have your derivatives, it goes wham. If you didn't do it in JAX, okay, you have to wait longer. But it really is trivial. But there are particular cases that we care about deeply in physics. And I'm a physicist, so I'm going to tell you about that. By the way, who here is a physicist or an astronomer? Yeah, or astronomer. Astronomers count. Okay, who here is totally not a physicist or an astronomer? Okay, who here does not want to identify? Several people didn't raise their hands. Okay, fine. In physics, we usually have very well defined data weights. We weight our data, which is what I would call inverse variance weighting. But there's data you care about, there's data you don't care about, there's data you think are very high precision, there's data you think are low precision. Physicists and astronomers are obsessed with giving data points with error bars. So we tend to do things where everything is weighted in a very specific way. So I'm going to talk about that objective function because there's a very general objective function I can write down that does all the data weighting. And that is, I wrote it down a minute ago, but I'm just going to write it down again. So my beta hat is going to be the argmin over beta of the thing I wrote down earlier, which is y minus x dot beta, which is a column vector. I'm going to transpose it. I'm going to dot it into a set of weights, which I'm going to call C inverse, and then dot it into y minus x beta. This is a generalization of L2. This is very, very similar to y minus x dot beta 2, 2. It's very similar to that. It's the sum of the squares, but it's the sum of the squares weighted by this weighting. So if all you ever want to do is L2, you don't want any of that. You don't have any data weights. You're like, screw that shit. Everything I'm doing here still applies. You just have the identity matrix in for C.
Yeah. Isn't C just for, I guess, normal weighting? Isn't C just diagonal here? Or are you?
If every data point is weighted identically, it's just the identity matrix. Now, if you weight them differently, you have different numbers on the diagonal, but this is more general than that because in principle, you can have covariances of your data points where you think that if this point is an outlier upwards, you expect these other points to be outliers upwards because of maybe some systematics in your problem.
Oh,
so
it's just like something that's actually happens.
Yes, absolutely. And if the Gaussian processes talk happens, I don't know if it will. I don't know if we have somebody to take it, but if the Gaussian processes talk happens, that will be discussed in the Gaussian processes talk. Because that is what you're doing. In Gaussian processes, you're modeling the covariances of data points. So we really do believe we have it. Yeah.
And it's related to what people call like kernel regression.
Very much. In fact, I'm going to put the exact equation for kernel regression in just a few minutes. We're going to hit it automatically. We can't avoid it, actually. What's my timing? Really? I'm allowed to just blast at everyone for 90 minutes? Awesome. I'm loving that because I can do 240 if you want it. Anyway, okay, here we go. So, yeah, hit me.
So, like, if C is the identity matrix, we said like this is just the MLE for.
It's just L2 norm, just that thing.
Right. Yeah, we corresponded to an MLE with Gaussian noise, right?
Actually, it's Gaussian noise in all cases here.
Right.
It's just covariant Gaussian noise or non heteroscedastic, you might call, if you want to use big words.
My question was if like there was a mapping from the noise prior to C.
There is. There's a lot to say about this. If you're a physicist, this is like a metric distance. This thing is a very beautiful object, actually. This is like a metric distance where you have a difference between your data and your model. And a metric distance in physics is a distance that can be written as a quadratic, like a quadratic distance through a metric. This is like a metric. And then this is like a Euclidean distance under this non-trivial metric. So now you can think about that as a noise model, or you can think of this as defining a coordinate system in which everything's isotropic and you get back to this. So you can actually transform coordinate systems and then you get this problem again. If you can diagonalize this matrix, you can get back to this problem. You see?
Yeah.
So there's like a lot of beautiful linear algebra and geometry. And actually there's statistics. This is really, it's subject in statistics. And in statistics, there's fully geometric. You know, there's a fully geometric description of statistics. There's statistics textbooks that don't have equations. They just have diagrams. Because there's a fully geometric description of statistics, and that's kind of the way in. That's the route in. Because you see, that's a quantity that exists in geometry. That's a geometric object. Physicists love that. That's just a beautiful thing. And that's also the fundamental thing in general relativity, right? You start with a metric distance in general relativity, and then the metric becomes a dynamical quantity. Yeah.
Can you recommend a good entry reference into that direction?
I can, but not off the top of my head. Send me email, and I'll get here like I'll go up to the top of my slides, and I'll write my email address. My shortest email address is dwh2@nyu.edu. That's my shortest email address. My longest is my Flatiron email address, so I won't write it down because it has FLATIRONINSTITUTE. I can't even type it correctly. I've never typed it correctly.
Very hard to type.
It's ridiculous. It's so bad. Exactly. It's basically impossible. And if you have eyesight like mine, I can't even tell where I've typed it right because ININSTI. I'm like, Anyway, now, the most general problem that has a closed form solution, this thing is a closed form solution. I'm about to write it down. The most general thing that has a closed form solution is actually a little bigger than this. I can add, actually, there's even a more general thing, but I'm not going to touch it. But almost the most general thing is to then add a penalty, the L2 on the parameters, which looks like beta transpose lambda beta. And this part here looks like the L2 norm on beta. But it has this lambda in there. What's that lambda? It's a set of weights on the betas, so I can weight some of the betas more than others. I can say that I think these features are more likely to have high amplitudes and these features are more likely to have low amplitudes. That's going to be extremely important in a minute. You don't think that all the features you're putting in are equally likely. So if you put in a Fourier series like we were doing up here, so if you just put in a pure Fourier series, you're just doing some Fourier transform of your data. But if you now weight the Fourier series by what you expect, then you're doing something that's more like some kind of filtering of your data. You see, if you say, well, high frequencies need a lot of evidence to be put into the model and low frequencies I'm happy with, then you're kind of somehow low pass filtering your data. And you can do the opposite and high pass filter your data. So you can think of filtering of your data also as a kind of machine learning method here. And actually, machine learning came out of signal processing, I believe. If you look at the history, I think it came out of these filters like Wiener filtering and things like that is one of the things that led to machine learning. Okay, good. Okay, now, if this is your problem, it turns out this is a linear algebra problem. This is the linear. So I took linear algebra as an undergrad, and we never saw a matrix that wasn't square. And so the linear algebra I learned in college was absolutely literally useless to my future. And all of my linear algebra I learned myself. This linear algebra expression that's written there, that linear algebra expression can be, you can take a derivative of that. And you can set that derivative to 0, and that is the optimum. This is a convex problem. So if you find a place where the derivative goes to 0, you have the solution. That's why convex problems are. What's the solution? The solution is, and many of you have seen this solution before, that beta hat is X transpose C inverse X plus lambda, all inversed, acting on C inverse Y. End of story, we're done. We didn't even turn on an optimizer. Now, of course, if you actually ask your code to do this, guess what it does under the hood? Optimization. It's actually the way, if you put in large linear algebra operators into and operate on them, what is it doing under the hood? It's actually doing conjugate gradients. So actually, it is doing an optimization when you do this closed form expression, but you write it closed form. You never see the optimizer. The optimizer is invisible to you. You can just write that as an expression in your code. But I should say one thing. I'm going to write it in red. Don't ever use inv. If your code contains the inv function, it's a bug. That's literally a bug. Always use solve. And if you want to know why, and also if you want to see the derivation of this expression, we talk about this a lot in a particular archive paper, which is 2101.07256. That's a pandemic paper. And in that paper, we talk about why that's the solution of the problem. Also another form of it, which I'm about to write down, and also tell you why you should never use the inv operator. Fundamentally, the inv operator is trying to find the numerically best solution to the inverse. The solve is trying to find the numerically best solution to the inverse times something, and you always want the inverse times something. You never want the inverse of a matrix. You always want the inverse of the matrix times something. That's why you should never do inverse, because you don't want that. You want the times something. That's what solve does. Yeah.
Could you speak a bit more to how to determine C and lambda and how difficult it is compared to the finding feature?
Good. That is a great question. I love that question because my answer is no. No, I can't. And so at some level, the C inverse has to be delivered to you by the people who took the data, which might be you, but whoever took the data has to tell you, here are the data points and here are their precision. C inverse is like the precision of each data point. Here are the more precise data, they have higher values in C inverse. Here are the less precise data, they have lower values in C inverse. And then you, as the investigator, decide on lambda. Lambda is, we're going to see in a moment, lambda is like the power spectrum of your fit. Like you make lambda larger when you think these components are going to matter more, and you make them smaller when you think they're going to matter less, or the opposite of that. That might be lambda inverse. Anyway, lambda or lambda inverse is telling you how important you think different components are, which is, you made your feature decision. These are the features we're going to use. Unfortunately, you have to make an additional decision, which is like, how much do I like these features versus these features? And in reality, the way you set lambda really is by like cross-validation. It's a choice. It's a model choice. So you're going to do it with like a validation, unfortunately. It sucks. Yeah.
Can't you also solve for C?
In principle, you can learn things about C. Yeah. I'm not going to talk about that because that definitely goes beyond linear regression. But if you imagine you believe the noise is Gaussian, and imagine you believe the noise is Gaussian, you believe the linear model really is a good model, then you can learn C. Yeah. But that's a lot of additional assumptions. You can use a linear model even if you think it's inappropriate, but you can only learn C if you're sure it's appropriate. See what I'm saying? Anyway. You can, yeah. Yes, you can, and you will get an answer. Yes, good. Love that. Agreed. This, by the way, this beta, it turns out, so literally my favorite fact. Oh, I dropped something in this expression is wrong. You should have noticed that it has the wrong units. That expression had the wrong units. There's an X transpose C inverse Y. That had to be there, right? Because beta is a ratio of Y to X, right? It's something you're going to multiply X by to get Y. See, this beta is something I'm going to multiply by X to get a prediction for Y. That means beta has the units of Y per unit X. This thing is X squared. So you need and it's inverse, so you need an X here. Have units of X per unit Y. Actually, one of the things I really encourage people to do is to think about the expressions they're writing down in terms of dimensional analysis. And that's something you can do in linear regression, which you cannot do when you have your 42-layer ReLU network. I have 20 minutes and I want to say surprising things. Okay, good. Let me say one thing and then I'm going to get on to surprising things. So the one thing I was going to say is when you have this so one thing I learned when I was a baby, like literally, oh my God, my postdoctoral advisor was like, if somebody was giving a talk and he was listening to them and he started to think that the person had more parameters than they have data, like you're measuring some like rare objects like millisecond pulsars, and then they would be fitting a model to them and they would be using like, the galactic distribution of stars and some heating mechanism and some age mechanism and so on. He's counting parameters, he's counting them up. And if he decided if there were more parameters than there were data points, he would just get up and leave. He would just leave because he's like, that's wrong. You can't have more parameters than data points. Well, he's dead now, unfortunately, because I've learned that that's not true. Look at this expression. Nothing in this expression says anything about N and P. Remember, we have N and P. So in this expression you have here, you can have N greater than P or you can have N less than P. remember our matrix X was n by p. N is the number of data points, p is the number of features. You can have either case. This case is called underparameterized. Yeah, good. I'll get there in a second. That's underparameterized. And this one is overparameterized. You can have either case. Nothing about this problem. Once you have this regularization we added here means that beta can be an arbitrarily large object and we can still get a solution to this problem. That is extremely important to machine learning. This is incredibly important to machine learning because if you look at your 42-layer ReLU network and you count up all the weights and all the thresholds that are going into that network, you always have more than you have data. You always do. And machine learning is always in the overparameterized regime. When I was your age, you would not receive your PhD if you had more parameters than data. Now you won't receive your PhD if you have fewer parameters than data because you don't have any machine learning in your PhD. What were you thinking? See? Big change. Now, if this expression I wrote here makes the assumption somehow, should take my mic. This expression here makes the assumption somehow that you're underparameterized. Because this thing, look at this object here. This thing here, this is x is n by p. So x transpose is p by n. This thing is p by p. So this is assuming that this is the small object. But if you're overparameterized, n by n would be the small object. So it turns out, and this is the single linear algebra fact I'm most proud of. Of course, I didn't find it, but I'm still proud, is that this expression is literally identical to the following expression. I hope I can fit them both on the screen. Yeah, I think I can. Beta hat, this is literally identical. What I'm going to write now is literally identical, not use one in one case, use one in the other. These are the same expression. And I invite you to prove it. It is an exercise left to the reader. God, I hope I write this correctly. Lambda inverse X transpose. X lambda inverse X transpose plus C all inverse Y.
Are you missing lambda inverse minus? Well, I know the expression, and I think
there is something disturbing about here because there's an unmatched lambda here, and there's an unmatched C here. That disturbs me. And yet it's straightforward to prove that these are identical. Like we first wrote these two down. We wrote these two things down on totally different grounds. This is in this paper that's right here. We wrote both these things down because by one path you get to this, and then you take the derivative a different way, you get to this. And we're like, okay, we must be wrong somewhere.
But isn't it just Woodbury between the two?
Say again?
Isn't it just Woodbury or?
Yes, it's Woodbury. It's Woodbury.
Yeah, okay. Try to do it in my head.
No, don't do it in your head. But yes, the fact your input to there's a word named Woodbury, which is something you can look up on Wikipedia, which gives you a relationship between products of matrices that is the key to showing that these are identical. You have to apply it twice, I think. It's actually a little bit crazy. But notice this contains a P by P that we have to invert. This is P by P, right? Because this went between the betas. And this contains an N by N, and this is N by N that we have to invert, you see? So you use this one when you're over-parameterized and use this one when you're under-parameterized. Same answer, but numerical stability. This is very numerically stable when you're under-parameterized, and this is very numerically stable when you're over-parameterized, you see? Again, linear algebra, linear models let you use linear algebra and you get all the tricks of linear algebra, like the Woodbury formula. You get lots of things that give you a lot of power to make very stable things. And one of the things that's a problem is if you have millions of data points and hundreds of thousands of parameters, or if you have hundreds of thousands of data points and millions of parameters, your linear algebra will be unstable in general. So you have to think about how you're doing it. Yeah.
Why do you want it to be small?
Just because this operation, this inverse or this solve operation that you would do to do this becomes less and less stable as you have more dimensions. And it also gets way slower. It scales as the number of entries to the 2.6 power. People in the world say it's the cube power, but you do the experiments, it's 2.6. The difference between cube and 2.6, I invite you to read about it. It's insane, insane. I also invite you to come up with a way to invert a matrix that it scales as n to the 2.6. There's some very good people that built these things. Many people died to bring us this SciPy linalg sparse or whatever. Many people died. Okay, good. In my remaining 12 minutes, I'm going to tell you two surprises, two secrets, surprises that every person, it should be obvious to everyone, but I have to say I learned 2 years ago. And I've been doing linear models literally all my life. One of my first things I did as a PhD student was build an astrometric map for an imager that was on a telescope. We had to figure out what the mapping was between the image pixels and the sky coordinates, and we used a linear combination of polynomials, which I now know is a stupid model, but anyway, we used that, and that was a linear fit. That was like the first linear fit I ever done. I've been doing linear fits all through my life. It's now however many years, 30 years later, still doing linear fits. I learned the following two things during the pandemic. You ready? Here's one of them. So, surprise number one. Here's surprise number one. Okay, let me say something that you will all agree with. And then I can say something that might be new to some of you. So I have the data. So I'm gonna define something which is like a residual, or the statisticians call a risk. I don't know why they call it a risk, but it's a residual. It's like the expectation value over new data. Like if you get new test data, the expectation over the new data of the difference between the new data and your prediction based on your linear model, right? You fit a linear model, that's how you got the beta hat. You got the beta hat by fitting a linear model. Now you're gonna predict new data, and I guess that X should be X star. And so we want the expectation over all new data you could get of what's that risk, or what's that residual. Good?
Is it defined squared or
Fine.
No,
two.
I'm asking.
No, you're right. I mean, I need it to actually be a scalar because I'm about to draw a scalar here. So it has to at least be a norm, but it's actually generally the L2 norm. But then you could do it as the chi-squared that we defined up here if you want, whatever. I don't really care. Whatever risk, whatever residual, risk, mistake, badness of fit, whatever you want to call it. So if we plot this versus P, remember I have a model where I can just choose how many features I use. I can either create them by adding more sines and cosines. I can just add more and more sines and cosines to my matrix, or maybe I can just use more and more of my housekeeping data. I have 10,000 channels. I use the most important 5, and then I can use the most important 15, most important 300, whatever. So I have some control here. And what you'll find is that if you use too few regressors, you do very poorly. But as you add more and more regressors, you do better and better at fitting your data. And then if you use kind of just the right amount, it works really well. But then if you use too many, you start to overfit, and then you do badly on new data. Remember, this is an expectation over new data. That Y star means it's not the data we trained on, it's new data. So what happens is there's a sweet spot, and you go, yay, I have the right place that I should be working, I'm done. And you can do that through cross-validation or validation or with test sets. There's lots of ways to find it. It's easy to find. You can do that. That's one of the reasons we love linear models. You can just like go, oh, there's the right place to work. We're going to work there. That's the best you can do. That makes sense, everybody? So the people often call this side underfitting. And they call this side overfitting. End of story. For the last 80 years. And then around 2018, people started to go, what if we just keep going? So keep on going because I'm an idiot. Keep on going. And oh my God, it comes back down. And the break point is, you guessed it, at n equals p. And then it goes like this. And usually for many models, this part goes below that part. Often, the best place to work is actually enormously over-parameterized. This, first of all of my career, I've been doing linear fitting. I never even thought to go here. I was like, that's idiotic. Who would do that? My postdoc advisor would have left the room, first of all. Second of all, I would never think it would do better. Like, okay, maybe you could go over there, but why? And this effect is called double descent. Well, it has multiple names, but the name that's kind of most common these days is double descent. And there's many papers on this, but I think the best paper on this is 1903 this is not by me. I've written papers on this, but they're very inside baseball, by Hasty and others. This is a very nice paper. I can't recommend it highly enough. And that paper by Hasty shows that you can always do as well as the best over-parameterized model if you regularize in certain ways. It's a very nice paper that talks about this phenomenon, where it comes from, and so on. And this is extremely easy to demonstrate. Like, it's crazy. I didn't know this, but you can just make polynomial data. Make a few hundred data points, take a polynomial model and raise the polynomial up through a few hundred, and boom, it goes like this, and then it comes back down again. And strictly speaking, the proofs in this Hasty paper is a mathematical paper that's proves some things. They prove it for the limit as n goes to infinity. So it's proven in an asymptotic limit. There aren't so many proofs non-asymptotic, but the phenomenon is very stable. It appears non-asymptotically.
Sorry, when n goes to infinity or p?
Well, both with a ratio. Okay. So you define a ratio gamma, and you do it in terms of that ratio. So then you don't plot it versus p, you plot it versus the ratio n over p. Yeah, and then it has a beautiful asymptotic form, but the asymptotic form is stable. If you have something with thousands of data points and you have thousands of parameters, you get it. It just is there. It's beautiful. Okay, so that's surprise number one. And yeah, hit me. It asymptotes as p goes to infinity generally. So it depends a little bit. It depends on some details. If you start throwing in truly random features, it will go to hell again. So it's a little bit depends. There are a bunch of assumptions. That's why you really have to read the paper to see it all. But if you do things like the sines and cosines that I said here, then it does generally asymptote. So as you add higher and higher frequencies, it basically just asymptotes. But of course, you have to be regularizing with this lambda term here. That has to be there, because otherwise you don't have a well-defined answer. Yeah. Good. Excellent. Good. I've got 4 minutes. This appears to be true. If you go to like a 42-layer ReLU network, what is the number of parameters? It's actually a little hard to define, because you can count them, but that isn't quite the right number. It's more like some kind of capacity. Empirically, it appears that neural networks have the same property. So that's why people are excited about it, by the way. There's a huge literature on this. Instantly, like overnight, it was kind of like pointed out as being a puzzle around 2017, 2018, and then boom, huge literature overnight. And part of the reason is that people do see very related effects in neural networks. However, it's hard to compare because it's hard to know how to count the parameters. It's hard to see what the regularization looks like. And this Hastie paper is about how you adjust the regularization to make this peak go away. And so a lot of the tricks people use in machine learning to make the models work well are actually tricks that look like the ones that make the peak go away. So it's complicated, but yeah, the reason people are excited about it is that the reason underlying this is very general. I hope nobody asks me what it is. I mean, I actually can tell you what it is, but maybe not in 3 minutes plus the other surprise I want to say. Yeah. You're going to say what?
No,
Yeah.
I don't want to take away from your other surprise.
Yeah.
I was just wondering if this had any like ramifications in astronomy. Changed what they had already done using.
Not really. I'm thinking about this right now. And the paper that I cited up above, this one, that 2101 paper, that paper is published in the astronomical literature. And we're thinking about things like wavelength solutions. So imagine you have a laser frequency clone that illuminates your spectrograph, and now you know a set of wavelengths, control wavelengths. Now you want to put a smooth wavelength model through it. That's a perfect interpolation problem. Now, how many parameters should you use for that? You should either use fewer than the number of laser frequency comb spots you have, or way more. So now we're pushing to way more for this reason. So I think it will have implications for astronomy eventually. But right now it's very new. It's new days. But I'm going to say something very relevant to that in just a second. My other surprise. Yeah, hit me.
Yeah, can you give an intuition for why this happened?
Nice. That's exactly what okay, fine. The intuition is yes, the intuition. Okay, so if you look at this expression, where's my expression? Okay, good. If you look at this expression here, these things are n by p. These both are n by p. This is a p by p. And then the other version I had an n, no, this is n by n. And the other one I had p by p. But in both cases, when n is close to p, this thing is very close to low rank. So imagine you had n by p and p was a little less than n and you made the n by n. You see how it would be a low rank matrix? And if you had p very close to n, but the other way around, it would also be very low rank. When p and n are very close to each other, this thing is very close to being low rank. If you have n much larger than p and you make the p by p thing, it's full rank very beautifully. And the other way around, you're also full rank very beautifully. But when n is close to p, this thing becomes very close to being full rank. And then this inverse becomes unstable. Right? So it's something like that. It's about how the rank of that object appears. But it really gets into numerical linear algebra. And then some people look at this literature and go, oh, that's just because you're not doing your linear algebra in a robust way. But that's not true. This can be shown mathematically, but it does relate to robust linear algebra in the sense of if you make this lambda large, the result of that Hastie paper, which I cite, is that if you make this lambda large enough, that peak goes away because this protects you from low rank situations. Yeah. Something like that? Does that help?
Yeah, I think that.
Hit me.
Maybe one more question regarding that. What's like the relation to Occam's razor?
Well, okay. There's a great question. My answer to that is Occam's razor is wrong.
Okay.
And I'm happy to discuss that over coffee in -1 minute. Yeah.
Also, I think like the reason why this was like not analyzed for like so many years is that people first realized that some similar phenomenon was happening in like deep neural networks.
Yeah.
And so then Hastie and all are like, you don't have to have like a deep neural network. This happens with linear regression as well.
Good, which relates to the question that was over here,
yes.
Is that really the reason they started looking at it is because weird phenomena were appearing in the neural networks. That is exactly correct. And then Hastie and other, yeah, good. Okay, I want to just say one thing and then I'll let you go. So I have this expression. There's this crazy expression for beta hat. I want to say one thing. I'm going to try to say it as quickly as possible. I realize I'm over time. Here we go. imagine I'm predicting for my new test data. So this is not my new test data, this is a prediction for my new test data. What I do is I multiply the features of my new test data times this beta hat. Okay, you with me? So now I'm just going to write this out. I'm going to try to write it out quickly because there's so many goddamn symbols. It's X star lambda inverse X transpose X lambda inverse X transpose plus C all inverse Y. Now, if I call this matrix K, that is a matrix, that's just a square matrix, which is the size of my data. It's n by n. You see that's an n by n matrix. It's the size of my data. This I could call K star. This is a matrix that is the size of my training data, my test data by the size of my training data. This is a rectangular matrix, size of the test data by the training data. It's rectangular because I don't necessarily have the same amount of test data as I had of training data. With me? Then this expression becomes K star K plus C inverse Y. And that is exactly the formula you get in Gaussian processes and you get in kernel regression, which somebody mentioned a minute ago. Oh yeah, sorry. Kernel regression. So this is exactly the formula you get in Gaussian process and you get in kernel regression. What is a Gaussian process? A Gaussian process, which you haven't learned about yet, well, some of you know about Gaussian processes, is the limit that P goes to infinity. So imagine P goes to infinity. You might think, well, I can't construct this because it would take me infinite amount of computing to do this inner product. See, this is an n by n object. To make this n by n object, I did a P sum and a P sum and a P sum. Now, what if those P sums become infinitely large? Well, in many cases, you still have a converging series. That in particular is true when these are drawn from some reproducing Hilbert space and you have a kernel. So a kernel matrix appears when you have the size of this space go to infinity, and then you get a Gaussian process. So the Gaussian process really is the limit of a linear regression where the number of features goes to infinity. Because if you are in the right kind of space and you have the right kind of weighting function, lambda, then these sums converge even when P goes to infinity. So for instance, if the weighting weights the higher and higher frequencies lower and lower and lower, then the sum will converge, and this becomes a kernel, and this becomes the rectangular kernel to the test data, and that is kernel regression or Gaussian process mean. So the Gaussian process really is just the limit of the linear fitting. And you can take P to infinity. P doesn't even have to be finite. It's not just that you can be over-parameterized. You can be infinitely over-parameterized. And in the 2101 paper that I cited up above, we showed that the Gaussian process actually saturates the asymptote. So this thing asymptotes to the Gaussian process you get at P goes to infinity.
Maybe one more question.
Yeah, hit me.
If we have time.
Yeah. Well, I have time. I mean,
can we think about this similar maybe to like random forest, that like you just like it's just approximation in the end, that you like more and more just approximating with more features, smaller errors?
Yeah, actually, one of the things we showed in that 2101 paper that I cite up above, what we show is that actually you don't have to go very far out in P before you really hit the Gaussian process. So we have a finite P model and we have the Gaussian process model, and they lie exactly on top of each other. In fact, we plot one with a thin line and one with a thick line, and thin line goes right through the center of the thick line, even though we didn't go to infinity. You don't actually have to go to infinity, right? Things converge fast. It's beautiful.
What kind of number?
So in that problem, we were at 1,000, we were fully converged. In general, one of the things that's interesting about machine learning is usually when you get into numbers that are many thousands, you start to saturate the accuracy of your linear algebra for other reasons. And so actually numbers above 1,000 are generally starting to, you're getting into some asymptotic machine. Okay, good. I'm sorry I went over. What's the schedule right now? Is it a coffee break?
We have a quick break, but we have to head over to 162 also.
It's a 162 to what side? Where are you going in 162?
CCD classroom, 7th floor.
So should we just walk over there and chat over there? Is the coffee break over there?
I mean, it's wherever we want it to be.
You mean Math for America isn't going to come in here guns blazing?
Yeah, I don't think they're going to like force coffee down our throats if we, you know.
Okay, good. Well, then why don't I walk over with everyone to the classroom and then I'll defer to the classroom over there.
Yeah,
okay, good. I'm going to turn this off.
Thank you. Thank you for the introduction, Domenico, and for having me here today and for the other lectures this week and I guess also next week. We'll see. So welcome. So today I'll start with giving an introduction to machine learning techniques for many-body quantum systems. As you will see in a second, the schedule is relatively long, so we'll try to get into the topics as they come. But it's very important that you give me your feedback, since I know that there is a diverse audience in terms of backgrounds, and not all of you are familiar maybe with quantum physics. Actually, let me ask that straight ahead now. So how many of you don't know about quantum physics? Okay, that's good. That's okay. Good. Right. So, and because you are computer scientists or other things. Okay, that's great. So I will give a short overview of what you need to know about quantum mechanics, knowing that, of course, I cannot tell you everything. So before we get started, there's a couple of useful references that you might enjoy reading. So okay, apart from the general books in machine learning, and I'm sure you have your favorite ones. If you are interested in application to physics, a couple of years back, we wrote a review that was up to date up to 2019. So it might be not so up to date as of 2022, but still you can find a list of interesting topics where machine learning is being applied to physics. This is in Review of Modern Physics in this one. And also what I will cover today can be found almost entirely redacted, if you want, in these lecture notes that we wrote this year. Especially chapter 5 is going to be a version of what I'm going to present you today. And in general, this is like 300 pages of lecture notes of machine learning in quantum in general. So I invite you to have a look if you want to also know about not only chapter 5, but also the others before and after. Okay? There's a lot of material, of course, that I cannot cover. During these lectures, you will see also tutorials by Javier Robledo Moreno, who's going to tell you about especially the open source software that we develop, that we started developing here, and now we moved to Europe, which is Netcat, and this is based on JAX and Flux, I mean, and all these BIS, maybe you're already familiar with, and you will learn how to use these tools if you want to solve problems that are interesting for quantum physics. Now, what are the main goals? So as I was already mentioning, I will do an intro recap for most of you maybe of quantum mechanics, or what do we need of quantum mechanics. And then I will tell you about several different types of variational methods. So I will tell you what this means, but keep this word in mind, variational methods in quantum physics or in quantum chemistry. I mean, these are very broad techniques. And then I will mostly focus on these two applications, if you want. So first, I will tell you about machine learning techniques to find the ground states wave function. Again, I will tell you what a ground state wave function is in a second, but for those of you who already know, you know what I'm talking about, and also to study dynamics of quantum systems. I just want to stress that these applications, maybe in contrast with more standard applications of machine learning, even to science, do not require external data, meaning that we don't have a pre-solved problem, if you want, that we are trying to fit, in a sense, in a supervised setting. And I will try to tell you how we do this. And we use machine learning as a tool to actually simulate from first principles without any external input, in a sense, the physics of these objects. And then later on, I guess in the next lecture or even next week, we'll discuss about how to use machine learning to learn from quantum experiments. So in this case, it's clear that we have external data because you are making measurements, for example, on your favorite quantum device, and we'll see how we can leverage this information to do something interesting. Okay, so today no external data, and we'll get started with, if you want, a small recap on the fundamentals of quantum mechanics. I realized that my handwriting really sucks, so if you have issues understanding, just ask. Okay? The prototypical example of quantum system that I will be mostly interested in these lectures are quantum spins, right? So spin 1/2. And spin, as you might know, is a property that, for example, you can find in electrons. So imagine that I have an electron, that you can find electrons everywhere inside of your body, everywhere. And essentially, you can think, I mean, up to some extent, that these objects can rotate, essentially. I mean, again, this is a simplified picture in 2 directions. So let's say counterclockwise direction, so like this, or they could rotate in a clockwise direction. Okay, and we say, and it's found experimental that if you want, the electron can have only these 2 possible, if you want, rotation around their own axis. And we say that in this case, for example, you might associate this to spin plus or up it's the same kind of notation. And in this other case, you might say that the spin that is rotating instead clockwise is a down spin. Okay, so essentially each of these electrons, you have to think that they have 2 possible internal states, so 2 possible way of rotating, either clockwise, and we say it's let's say down, or counterclockwise, and it's an up spin. Okay, so we have in total, again, 2 possibilities, if you want, 2 possible values, in the sense that if I measure this object, the spin rotation, I would find only these 2 possibilities. Okay. Now, what does quantum mechanics tell us about this? So there is the first postulate, so the first thing that we cannot prove, but that we accept, if you want, as quantum mechanics. So as people who work with quantum mechanics, and the first postulate tells you that the properties of this quantum system, so especially in this context of this single spin, are fully characterized by what we call a state vector or a wave function that I'm denoting here as a psi, as a vector, right? So you see, this is the vector that I would call the state vector. Essentially, what the main postulate of quantum mechanics is that this is going to be a combination, a linear combination of some, if you want, basis elements that I'm writing E1, E2, up to a certain number. And essentially, if you want, the dimensionality of this vector, again, of the state vector, is coincides, so the number of possible, if you want, the dimensionality of this psi is equal to the number of possible measurement outcomes of my quantum systems. Okay, so what does it mean? It means that, for example, if I have a spin, and I've told you that this can take only plus or minus or up or down, then my state vector will be just a 2-dimensional, if you want, vector that will have 2 components, and I would call with, if you want, coefficients C1 and C2, right? Or that I would call for also C up or C down. Okay, because in this case, the number of possible outcomes are just 2, up or down, and the entries will be these 2 coefficients, if you want, that that are in general complex. Okay, so these Ci belong to complex numbers, and these are known as so these complex valued coefficients are known as probability amplitudes. Okay, so in other words, if you want to describe the state of your electron, which can be either up or down, the only thing that you need to do is to have access to these two coefficients, C up and C down, that are known as the probability amplitudes. So why so? Because there is a second postulate that goes, rather naturally after the first postulate, the postulate 2, which is also known in literature as the Born rule, Born's rule. And this postulate tells you that these coefficients indeed are probability amplitudes, in the sense that the probability, now if I make a measurement, for example, of my spin, the probability of observing that the spin is in the up, let's say, position, or let's say rotating counterclockwise, is given by these postulates by the square of the coefficient C square. Okay, so if I know the entries of this vector, and if I know that I don't know, C up as a certain numerical value, then its square will give me the probability of observing that the spin is going in a certain direction when I perform a measure. Okay, and as a consequence, also the probability of measuring the spin down is going to be given by C down square. Right? So you see already immediately that this implies that if I want these probabilities to be normalized, I need to have that the sum of C up square plus the sum of C down square must be equal to 1, because I have in total, there are only two possibilities, so the spin is either up or down, and then the sum of the two probabilities must add up to 1. Okay. So this means that, again, as I was already mentioning, if I have a single spin, so let's say a single electron, for example, so knowing these two coefficients, these two complex value coefficients, C up and C down, is enough to predict all properties of the quantum system. So for example, I can predict how many times I will find the system in the up position, or what is the average value of the spin. I can predict all sorts of physical properties of my isolated spin. Okay? So for the people who are not familiar with quantum mechanics, I hope it is at least clear what we are talking about. If you have questions, just ask. Now, what is the problem? So why we are here, if you want? Because up to this point, it's just about mathematically, it's about like knowing a couple of complex value coefficients. It's not a really hard task computationally, if you want. The hard computational task begins when we start considering the case of many particles, or if you want, in this case, the case of many spins. Now imagine that instead of having an isolated, if you want, electron that can be either up or down, I have many of them. Right? So in a chunk of material, you will have an Avogadro number of order of the Avogadro number of electrons. So it's really a huge number. And what's the problem there? The problem is that if you consider now what are all the possible measurement outcomes, remember the postulate 1 of quantum mechanics, you see immediately that there is an exponential explosion of possibilities. So for example, I can find all the spins that are up, so this would be a legitimate outcome of my measurement. Or I could find that, for example, they're all up but one, for example, the last one that is down, and so on and so forth. And I can order them, if you want, lexicographically. I'm implicitly doing this here until I reach the last possible state where all the spins instead are down. Okay. So you see that in this case, the main complication when we have many spins, so that's why we talk about many body quantum physics, because we have many bodies, many spins. We have in total 2 to the power n of possible measurement outcomes, right? So an exponentially large number of measurements, or possible outcome measurements, which implies, if you want, that if I now consider my state vector, so the wave function, which is also known as the wave function, that describes in full detail, if you want, all the properties of my many body electrons, of my spins, then these, by the first postulate, should be a linear combination with some coefficients. So for example, C up would be the amplitude of having all the spins up times a basis vector E up plus C up down with the basis vector where I have all of these and the last one is down, plus all of them. I'm not going to write all of them, of course, because they are exponentially many, but just to again, to use the same ordering as before, the last one in this specific ordering that I'm choosing would be the one where the spins are now pointing all down. Okay, so you see now, and this is really the origin of all the problems that we have, if you want, in quantum physics. I need, if I want to specify and know or predict all the properties of my many bodies, or my system composed of, made out of many electrons, I need to specify 2 to the power n coefficients are necessary. Okay, so now you see immediately that contrary to the single spin case where I only need the 2 coefficients, now I need 2 to the power n. So this is an exponential amount of, if you want, information that in principle I need to predict what my many body spins are doing. And this is at the heart of what we call the quantum many body problem. It's a simplified version of that, but it's the main ingredient that you find in many other places in physics. So this is again a strict manifestation of what we call the quantum many body problem. So the quantum many body problem is the fact that just think of storing, right, on a hard disk, if you want, all the possible coefficients, also all the possible probability amplitudes. So these coefficients, C up, or etc., right, is essentially impossible for I can give you some number, but I mean, this is very optimistic. Let's say 80, more than 80 spins. Okay, so let's say more than 80 electrons. So why am I giving you this number? It's not completely random, because if you do the calculations, so essentially this would so if you take the case of 80 spins, roughly speaking, 2 to the power of 80, right, which is the amount of memory, of the order of the amount of memory that we need to store all these coefficients, is roughly equal to the number of atoms that we have on our planet. So this means that if you transformed our planet into a hard disk, then maybe you'll be able to store all this information that a mere 80 spins contain because of the wave function, right? So this would require, again, a giant hard disk, essentially as big as our planet. So we would require a disk with order of 2 to the power of 80. I mean, do the math, it's a lot bytes of information. Okay, so this is the quantum many body problem, essentially. So the main manifestation, so the fact that we cannot really afford storing these coefficients, these probability amplitudes, when we have many electrons, many particles. And as I will try to see in the following, we have to do some meaningful approximation that could be also very, very accurate. And that's where machine learning will enter the game. But before doing that, I mean, we need to know the last ingredient, if you want, for the non-physicist, which is the problem of how can we determine these coefficients, right? So up to now, I've told you that. So how can we determine these probability amplitudes? I've told you just that they exist. It's a postulate of quantum mechanics, but I haven't told you how they are determined. So how nature, if you want, gives us these coefficients. And well, we have vectors, and the vectors are, these state vectors, this wave function. And we also have matrices. And matrices, in the context of quantum mechanics, are associated with observables. So I cannot go too much into the detail of this, but the most important matrix, if you want, that we will discuss in this context is the Hamiltonian matrix, or the Hamiltonian operator. I mean, more generally, it's a linear operator. And this, I mean, in this context, is essentially identical to an Hermitian matrix of sites 2 to the n times 2 to the n. Okay? So it's in general a complex value matrix, Hermitian, time that in this context of many spins, it has this size 2 to the n times 2 to the n. So it acts on the same space, if you want, of my state vectors. Okay, so now how do we determine the coefficients in my state vector using only this Hamiltonian operator? Well, this is Schrödinger's equation, so especially the so-called time independent Schrödinger's equation. So essentially, we solve an eigenvalue problem. So we want to find the eigenstates of my Hamiltonian, so my matrix H, that I'm calling here psi n, because I will have in general 2 to the n of them, right? And these will have some eigenvalue En, and then again, so this is just an eigenvalue problem if you want. So I have a matrix, a vector equal to a constant times my state vector. So these are the eigenvalues. And these are real because the matrix is by construction, if you want, Hermitian, so its eigenvalues are real. So this is the time independent Schrödinger's equation. Okay. Now, the main postulate of another postulate, if you want, of quantum mechanics, is that these eigenvalues, so these En, for example, are associated with all the possible measurements outcomes of this operator. So in this case of the Hamiltonian, which is itself associated with the energy. So this means that once I solve for the eigenvalues, I also know how many, what is the energy, what are the possible energy values that my Hamiltonian, that my quantum system can take. So these eigenvalues are the possible results for an energy measurement. So I measure the energy of my quantum system, and then I will get strictly one of these eigenvalues. Okay, so you see that then the main actually application that we will do in this first lecture will be about finding what we call the ground state of the Hamiltonian. And the ground state of the Hamiltonian is mathematically, again, forget about physics. I just have this huge matrix, this exponentially large matrix, 2 to the n times 2 to the n. I diagonalize it, okay? And then I find, so this vector, so this eigenstate, if you want, of my Hamiltonian, that I call now psi 0, which has the property that its energy, so its eigenvalue, if you want, is the smallest of all. So I set now the things in a way that it's 0, so if you want, the eigenstate, the eigenvalue associated with psi 0 is smaller than E1, is smaller than E2, until I reach the last eigenvalue. Okay? And this vector here, so finding this little vector here, so this is known as the ground state wave function, wave function, or the ground state, wave function. Okay, so essentially the main goal that we will set for today will be to find an approximation of this object, so this vector, and of the ground state energy, so this E0. So we want to find both the vector and its eigenvalue. Okay, great. So this is going to be essentially all you need to know about quantum physics. So hopefully we are all up to speed. I will just give you the last word that something that we will use a lot, which is Dirac notation. So how many of you are already familiar with Dirac notation? Not all of them. Okay, great. So you had the question?
Yeah, I was wondering what in particular makes the ground state interesting.
Yeah, sorry, I forgot to mention. So So typically nature tries to favors states with lower energy because it's somehow lazy, right? And it wants to prepare things that have the lowest possible. So that's typically the states of matter that we see around are in the ground state. Not always, but in several interesting cases. So Dirac notation is another way of doing linear algebra. So for example, instead of writing my vector psi in like this, as you would do in in standard standard linear algebra notation. So Dirac was a famous quantum physicist, one of the fathers of quantum mechanics. You introduce this notation where psi now, I mean, this vector, this row vector, sorry, this column vector is represented with what we call a ket. Okay, so instead of putting, if you want, an arrow on top, we use this weird notation if you want, I mean, but it's actually extremely efficient. And then row vectors. So if you want the transpose of psi in this case, is denoted in this way. So which is, if you want, the transposals of the notation, right? So with which the brackets, and this is known as bra. I mean, that's the name he gave. So we have bra and kets, and they are essentially the same as column vectors in the case of kets and row vectors in the case of bras. Okay? And this notation is quite nice because, for example, if you want to do, let's say, an inner product between the same vector, for example, to compute the norm of this vector, which would be just doing psi transpose times psi, then you see that in this Dirac notation, you can write it as psi, which is my now psi transpose, times psi, right? And you see that this is the typical notation, powerful notation for the inner product. And that's also why the notation is called bra and ket, because now this is a bracket. Okay. So when the bra meets the ket, you get a bracket and you get an internal product, which is a scalar in this case. I hope you can see that. And you can also see that the eigenvalue equation that I wrote before, so Schrödinger's equation, the time independent Schrödinger's equation can be written in this form, right? So I have this operator H that acts on that. I'm putting a little hat on top to say that this is an operator. It's a matrix. It acts on my ket, and I give you and it's what we call an eigenket, which is nothing but an eigenvector in this case. And now you see also in this notation, I can write that my state of n spins can be written as the sum for k that goes from 1 to the n of some coefficients ck times, if you want, a basis state in this very large 2 to the n dimensional space, where simply, I mean, here I'm just taking these I'm just ordering, if you want, them in a way that, for example, state 1, so k equal 1, would correspond to having all the spins up. I mean, it's the usual notation, it's the usual ordering that we started doing before. Whereas the state, if you want, 2 to the n, would correspond to having all the spins down. Okay, so if you want, I'm picking a lexicographical order for the spins, all the possibilities of the spins. Right? Great. So all clear, or most of things are clear. That's great. Now, there is something that maybe also physicists haven't thought about, so that's where it gets interesting also for you. And there is an important simplification in most physics problem. I would say in all physics problem actually, and it's about the structure of these Hamiltonians. Okay, so if we think about physically relevant Hamiltonians, or if you want, matrices, right? So they are not, if you want, random Hamiltonians. They have very special properties. And the most important property that these Hamiltonians have it concerns the number of non-zero entries that they have. So there's a sparsity, if you want, problem, a feature that we have when we study physics Hamiltonian. So what do I mean? I mean that if now I consider the matrix element of my Hamiltonian, okay, So again, this is just, if you want, in standard notation, this would be the matrix element of H between K and K prime. Okay, so this is just the matrix element of my Hamiltonian in the basis that I've chosen. So it happens that the number of non-zero matrix elements, right, when I fix the row, so if you want, I fix K in this thing, so this is fixed, okay, is only polynomial in the number of spins. So the number of non-zero elements, so the number, if you want, of K prime, such that this matrix element is non-zero given a fixed K, is only polynomial in the number of particles in the number of spins. Okay? So you see why this is a huge simplification, because in general, so if I draw, if you want, my Hamiltonian matrix now, which is 2 to the n times 2 to the n, so it's exponentially large. However, if I fix a row, so if I fix this index k, which amounts to fixing one of the rows, so in general, for the most general emission matrix, I would expect that I have 2 to the n non-zero matrix elements, which correspond to all the row here, right? But for physically relevant Hamiltonians, the number of non-zero matrix elements is only polynomial. So this means that the non-zeros, which are these x's in my little drawing, are only, I don't know, n or n squared, so they are not 2 to the n, right? And this is a feature that we will use a lot in the following, and it's what you might refer to as being as the Hamiltonian, or your matrix being column sparse. And because of hermeticity, also row sparse, right? Because the matrix must be, Hermitian. So it's both column and row sparse. So which means that, again, if I fix a row, I can have only polynomially many non-zeros. And this is known also in the language of, it's related to what in quantum information is known as the Hamiltonian being K-local. Okay. So maybe some of you have heard about this notion in the quantum information, but when you say that an operator, so in general, for example, the Hamiltonian is K-local, means that the number of non-zero entries in this Hamiltonian are only polynomial for each row. The total number is still exponential, but for each row there are only polynomial. All right? Is this clear? I mean, at least that's a simplification that we will use a lot. Okay. Okay. So maybe just for the physicists, I will give you an example of Hamiltonians that that satisfies this property. So such an Hamiltonian is for example, the transverse field Ising model. So how many of you know about the transverse field Ising model? Okay, that's a good number. So here essentially, do you know the classical Ising model, though, right? Have you seen the classical Ising model in statistical physics, right? So in that case, you know that you have interactions among the spins. So classically, for example, you would have that your energy, if you want, classically would be given by the interaction between your spins with some constants, Jij, and I would have, for example, interaction between my spin I and spin j along the z direction. So this would be the equivalent of the classical interaction energy that you have in a classical model. So if you think that my spins now are classical, they can be either up or down, and they have some energy that depends on if they are aligned or anti-aligned. And depending on this value, Jij, they might prefer of being aligned or anti-aligned to lower the energy of the classical system. Now, in the quantum setting, typically a minimal extension of this to introduce quantum effects is to add what is known as a transverse field, which is essentially this term here. So now I add also an external field in the x direction of the spin that is proportional to this term gamma here. So gamma is a constant that I can change as much as I can change also this Jij. Okay. Now, if you think about this Hamiltonian, so it's clear that this Hamiltonian is K-local and satisfies the properties that I was discussing before, because if you compute, for example, the matrix elements of this object, so maybe just for those of you who are not familiar with this notation, because I guess I thought maybe I'm jumping a little bit too far. But essentially, when you see that people write these kind of things, it means that so for example, sigma I x means the tensor product of identities on all spins. So for example, I1 tensor product, I2 tensor product, for example, let's say I minus 1, I is the 2x2 identity in this case. And then I have a sigma x polymatrix, which is just this 2x2 matrix 0, 1, 1, 0. And then I have other identities up to the nth, up to the nth, if you want, spin. Okay, so you see that if I take the tensor product of these 2x2 matrices, n of them, at the end I get so this object here would be a 2 to the n times 2 to the n matrix. Okay, is this clear more or less? Hopefully. So that's a shorthand notation that physicists use when we write these objects. You have to think that there's a tensor product of these 2x2 matrices up to this one. Okay. And the same thing is true also for this case, where you have tensor products of everything but two matrices that are the sigma z matrices. So in this case, you would have, for example, if I have sigma I z and the sigma I plus 1 z. So this would mean that I take the identity on the first side, so on the first spin, and then I would have, let's say, the sigma z polymatrix, which is this diagonal matrix here on spin I, tensor product with the same matrix but now acting on spin I plus 1 up to the last one that is still going to be an identity. Okay. Now, if you do the math and I mean, given this notation that I've just explained to you, you can immediately see that then the Hamiltonian as this 2 to the n times 2 to the n matrix is indeed k-local. For example, we can check this immediately by noticing that if I take let's say this matrix here, which is the only one that is off diagonal in my basis. So you see that these are all diagonal matrices, and this term here will be automatically diagonal in my basis. So this would correspond to the diagonal elements in this matrix. Okay. So now the question is, how many off diagonal elements do I have that are non-zero? And this can come only from these terms here. Okay. I hope you can see that. Otherwise, take some time to think about it. But if you look at that then, and we try to compute, for example, how many non-zero matrix elements we have for this sigma ix, for example, object that I just wrote here. Okay. So you see that this object is going to be different from 0 only if k prime contains what we call a spin flip. So it means that in this case, k prime would be almost identical to k, but it will contain a spin flip. So if I call now the value of my spins in the configuration k, like sigma 1 z, sigma 2 z up to sigma n z, what will happen is that the k prime can be will have a single spin flip. So meaning that the value of the spin on the ith spin will be flipped. Okay, right. So this means that, for example, if I have that k now is a string of spins that is up, down, up, down, up, down, then the only k prime such that this object is different from 0 is the one where I take the ith spin in k and I flip it. So if it was up, I make it down, and if it was down, I make it up. Right. So you can convince about this mathematically, even without knowing physics, just because this operator here, so this matrix, is like a knot, if you want, a gate in computing. So it flips bits, right, from 0 to 1 and from 1 to 0. Okay, so that's what this gate does, and you can see immediately then that the number of non-zero matrix elements will be proportional to n, because I have n of these terms in the Hamiltonian. Okay, so in this case, I have order n, so the number of non-zero is actually linear in n. Great. So hopefully I didn't lose you on this small example, but if you have questions, again, don't hesitate to ask. Okay, now we set up the problem, which in most applications it's always the hardest part, because if we set up the problem correctly, then we know also most of the time how to solve it. And indeed, what I want to do now is that I would like to try to find, to discuss techniques that would allow me to find an approximate ground state wave function, a ground state vector that would correspond as much as possible to the true ground state. So at the heart of what I'm going to tell you in the following, there are what we call, what physicists and mathematicians actually call variational methods. Okay? So variational methods appear everywhere in physics, mathematics, statistics, but they are especially old, and they are as old as quantum mechanics when it comes to studying quantum systems. And the idea is very simple, but very powerful. And it's the following. So imagine now that I have my huge, if you want, space of all possible wave functions. So this is going to be, mathematically speaking, a Hilbert space, or in this simple case of spins, this is just a vector space, right? So it's a vector space of sites 2 to the n. Okay. Now, and in this huge vector space or Hilbert space, I have that my wave function, I mean, my state psi n can be can essentially take any, you know, any possible value in this huge space, right? So all the, if you want, the coefficients can take an arbitrary value, and this will correspond to a state, if you want, in this huge, you know, if you want, land of all possible states, physical states, of all possible quantum states. However, I mean, the idea of the variational method is that we don't care about describing random states, if you want, in this huge vector space, but we want to describe only the states that are relevant for physics or chemistry. Okay? So we don't want to describe a state which has random vector, absolutely random vectors, random coefficients, but we want to study what we might call physical states, again, or chemically relevant states. I'm just simplifying here. Okay? So, for example, all the eigenstates of the Hamiltonian are definitely physically relevant states. So let's say psi 0, psi 1, all these eigenstates of the Hamiltonian. And these, if you think about that for a second, and if you know now, and now we know that these Hamiltonians are not random matrices. They have a specific structure. They are sparse. They contain a lot of structure. So it's clear that we are not interested in random states, but only to eigenstates of very structured matrices. Okay, so and this is the main, if you want, insight that people started having when started thinking about variational methods, because now what we can do is that we can try to restrict our attention to these physically relevant states, and it's what I call the idea of accessing corners of this huge space, accessing corners of this vector space. So I'm not interested in somehow describing a generally random state, but what I can do is that I can describe a state psi that will depend, if you want, parametrically on some parameters that I call theta. So I can have in general a lot of them. Okay, in the sense that if I want to be specific, if I write a representation of my state as a linear combination of my basis vector, now what will happen is that my basis coefficients, if you want, so my probability amplitudes, which are just the coefficients in this representation, will depend also parametrically on some parameters theta. Okay, and this will be my variational state. Okay? So again, once more, what I've done is that I've injected, if you want, the parametric dependence of psi through these parameters theta that appear explicitly only in the coefficients of the state. Okay, And typically what I want to do is that I want to use only polynomially many of these coefficients, right? Otherwise I would be back to square one and I would be stuck with just storing these variational coefficients theta. Instead, I just want to use a finite and possibly very small, hopefully, number of parameters to try to span, if you want, this set of quantum states that are relevant for physics. Okay, so by parameterizing the coefficients, I try to span now this subset of relevant states. Okay, so this is the main, if you want, the idea that people have been using in quantum mechanics for a long time. And then the question is, how are we going to find these optimal parameters? So these optimal parameters. And that's where, again, ideas from mathematics and physics somehow join together. Because, for example, if we are interested in describing the ground state wave function, we know that we can find the best value of theta that would describe the ground state of my Hamiltonian by minimizing the average value of the energy of my state psi. Okay, so in other words, we can form what in mathematics is known as the Rayleigh coefficient, which is this quantity here, so E of theta, that will depend on my parameters theta, and it's the if you want the inner product between my variational state that now will depend on some parameters theta, my matrix H, and the state itself psi. Okay, so in general, so this state might also not be normalized, so it might be that its norm is not equal to 1, so we have to renormalize for that. So just believe me that the correct thing to do here is to also divide by the norm of the state. Okay, so this is known as the variational energy of the state, and this is strictly equal or greater than the exact ground state energy. So if I call it 0 again, as before, the exact ground state energy. So we know that this object, that again in mathematics is known as the Rayleigh coefficient, will be strictly greater or equal than the exact ground state energy. So if now now, as you can see, I can set the problem of finding an approximation of the ground state into an optimization problem, where I will be interested in minimizing this object by changing the thetas. Okay, so this is the variational principle in quantum mechanics. So for those of you who are still not familiar with the Dirac notation, this object you can write this object also as psi transpose. Again, this if you want times this matrix H times my vector psi. Okay, where again all the entries of my vector depend on the parameters theta. Okay. Actually, I mean, admittedly, this notation is more compact than this one, but okay. We prefer this one because it has other nicer properties. How many of you have seen a proof of this relation? I mean, of this inequality before? Okay, so it's roughly relatively well known, but I mean, just to glance over it, I mean, the idea is that you can, if you write essentially psi of theta in the basis of the eigenstates of the Hamiltonian, because imagine that I've diagonalized the Hamiltonian, now I can always write this as sum over k, some coefficients gamma k, the eigenstates of my Hamiltonian. Okay, now you can see, by using this expansion, then you can write E of theta simply as the sum over k of these coefficients gamma k square times the eigenvalues of the Hamiltonian divided by gamma k square. Okay. So I skipped the little derivation here, but I hope it's clear. So you just use the fact that now this operator here acts on its eigenstates, so that's why you get this ek. And that's where essentially then you get a square because I have gamma k here, and then the transpose conjugate gives me gamma k star. Okay. So, and you see immediately that now I have a convex combination with these coefficients gamma k of the energies of my system. And since this is a convex combination, so you know the best thing that can happen is that all the coefficients with k larger than 0 are 0, and only the first one is non-zero, and this would correspond to having that this to having E theta equal to E0, so the ground state. In the other cases, instead you will have a combination with positive coefficients, so that this will increase the average value, so the value of the energy. Okay, so this is a little proof of the variational theorem. All right, so we will use this result a lot in the following, so it's important that we know how to prove it if necessary. Then, I mean, there are mainly two main classes of variational states that I will sketch today. So the first class, so there are two main classes of variational states. So there is a first class that I mean I call class 1 just for simplicity, where we can compute this expected value of the energy, this E of theta, if you want. So the object that I wrote here before. Exactly. So I put exactly in a quotation mark, meaning that apart from controllable rounding errors. Right? So you know that if you run your computations on a computer, you will always have some rounding errors because you are not working with actual real numbers, but with finite precision numbers like float or double or integers. Okay? But in any case, within that precision, you can compute. There are some families of variational states for which you can compute E of theta exactly, and I will tell you in a moment what these states are. And then there is a second family of states that will be the most interesting for our lectures, but again, I just want to make the distinction, for which we can compute E of theta approximately, only approximately, where approximately means, I mean, not in a random way, but in a controlled approximate way. Okay, so this means that in principle, I have a knob that somehow is the amount of computational power I can spend on my problem that will allow me to improve the precision on the accuracy of this computed E of theta that I would like to compute. Okay, is this division clear? So we have exact and approximate quantum states for which we can compute this. Now, belonging to the first class of states, there is a very famous wave function. So let's say examples. I will give you one example actually of the first kind of wave function. Unfortunately, we don't have a third kind, otherwise we would have done a nice encounter. They are too young to get the go. But anyway, it's a movie. But anyways, okay, or maybe it was not fun, but it's also like. But okay, so the example of first kind for which we can compute the one very important example are what we call mean field states. Okay, so mean field states are sorry, there's no A here. So these are just example of wave functions for which we can compute everything exactly. So mean field states, maybe you've seen, hopefully you've seen them also in other contexts, but the idea is very simple, is that we write now our vector, if you want, psi, my variational vector, if you want, psi, so that again, in principle, it's a 2 to the n dimensional vector, so we cannot afford that because that would consume too much memory. But we can write it as a tensor product of smaller vectors of size 2 in this case. Okay, so what I will do is that I will write it as a tensor product of, let's say, a vector phi1 that is a two-dimensional vector times another vector phi2 that is again a two-dimensional vector until I reach the last vector in this if you want representation phi n. So now I have two-dimensional vectors. So each of them, if you want, only has two coefficients. So it's in total, you see that here I will have two coefficients for this one, two coefficients for this one, and two coefficients for this one. So in total, I will have two times n, not 2 to the power of n, 2 to n complex coefficient. And if I consider my state now to be the tensor product of these smaller vectors, it's clear that I have a manageable compact representation of my initial wave function. That is, of course, an approximation. So it's a variational approximation for my state. Okay. So, for example, and right. So and then again, so what I will do is that I will say that the variational parameters in this representation are essentially the entries in this matrix. So, for example, are the amplitudes of my state, let's say phi I, on a given spin projection. So, for example, if my spin I is up or down, so and this will be two variational parameters per I, so that I can call, for example, theta up for spin I and theta down for spin I. Okay, so if you want, each of these phi is a vector of dimension 2, and my variational parameters in this case will be 2 for per I, so I will have 2n in total. And these are essentially the amplitudes in this mean field language of observing spin I up or down, independently on the others. So this is the heart of this mean field approximation, because the probability now observing a certain spin being up or down will be completely independent from the other spins. So there's a factorization, if you want, of probabilities, meaning that the probability of observing again spin I to be up does not depend at all on the other spins. They can do whatever they want. The probability will always be independent on the others. Okay, so there's a factorization. I have a factorized model also in the language of, if you want, of machine learning. So the only, if you want, condition now that I have is that these thetas are such that theta I squared, if you want, plus theta down I squared will square to 1. So their sum will be to 1, because my I spin can be either up or down, so they have to sum to 1. And as I was already mentioning, in total I will have 2n, not 2 to the power of n parameters. Okay, and you can see immediately that in this representation I can also compute very efficiently all expected value of operators. So let's say that we are again in the case that I had before, where my Hamiltonian, just to remind you, was this transverse field Ising model. So it has these two terms. And let's say that I want to compute the expected value of only these terms, right? So let's say that I want to compute the expected value of this operator sigma x. Okay, so this term here. So how can I do that? Well, you see that because of this tensor product structure of the state, so because all the spins are independent, it's actually very easy, because now the expected value of, if you want, over this state of this operator sigma ix, so if you want, this is the mean polarization of the spin in the x direction. Okay, so this is strictly going to be equal just to the expected value over my smaller state phi I of my 2x2 matrix, if you want, 0, 1, 1, 0, which is my sigma x. Okay, so because of this factorization property, now I can write all expected value in terms of matrix vector products of only 2x2 matrices. So this is beautiful, because I don't need to, if you want, consider this 2 to the n dimensional, huge state, but only these smaller 2-dimensional states. Okay, so you see now I have a 2x2 matrix. I multiply by size 2 vector by its conjugate, and this is a scalar, and this is what we call the expected value of this operator. Yes.
I think what is the phi
Phi I are these states here. So essentially, if you want another way of writing this is to consider the amplitudes of the wave function more explicitly in the sigma z basis. So this variational state psi now can be written as the product of phi 1 of, if you want, sigma 1z times phi 2 of sigma 2z, right, times phi n. So these are just the mean field, the probability amplitudes of observing, for example, spin 1 to be up or down. Okay, is it clear or? I didn't ask if you were familiar with tensor products. Maybe that was a mistake. But if you're not, go back and revise your linear algebra classes. So if you think about the probability distribution, so in general, probability distribution depends on everything. So it will depend on variable 1, 2, 3, 4, 5. Okay. So in this case, these variables are up or down. So each of them can take two possible values, so up or down, plus or minus 1, 0, 1. I mean, call them whatever you like. So in this approximation, what we are saying is that this probability density, so this probability amplitude, does not depend on everything, but it's just the product of these individual terms. Okay. So this is the main approach, and these phi's are just the individual terms that enter this. Okay. Great. So this is the simplest case of wave functions that we can handle, because now since we are able to evaluate all these expected value essentially exactly. For example, for sigma ix, but then we can evaluate this for all of these n terms. We can evaluate this as simple matrix vector products, and also these terms, believe me, can be done in a similar way. So I can evaluate the expectation value of the Hamiltonian. So again, this quantity that I wrote here at some point, which is this one, I can write it just using matrix vector products of 2x2 matrices essentially. So it's very easy and efficient. And then I can just minimize this energy, and optimize the coefficients if you want in this phi to minimize the energy. So that's how you would do a mean field calculation in this case. All right. Great. Now, so this was an example of the first kind. However, as you can already imagine, there are some strong limitations. Coming from this exactness, if you want, exactness, I don't know how to, but essentially the fact that we are forcing, so we are limiting ourselves to considering variational states for which we can compute the expected value of the Hamiltonian exactly. So these are a much smaller, if you want, family of all the possible interesting variational states we are interested in. So again, if you consider now your huge and deserted land, which is this space of this vector space of size 2 to the n that contains all the possible states. I told you at the beginning that sure, I'm interested only in physically relevant states. But these factorizable states, or if you want, these states in general for which I can compute the expected values exactly, in turn, they certainly occupy only a smaller, much smaller fraction of what we are interested in. So these are factorizable states, for example. Okay. Again, I'm calling them factorizable. I hope it's clear because I'm writing the amplitude as a product of individual factors phi I that depend only on each of the spins and not on all of them. All right. So this class of variational states is very convenient, but also very, very limited. Okay. So the question is, how can we go beyond this family of states? There are several ways, and the way that I will discuss during this lecture, I mean, for reasons that are obvious since we are giving a machine learning a school. Just a second. It will be based on deep learning and on neural networks. Yes.
Is it possible to have a factorizable state that's not
Well, I guess all factorizable states can be written as ground states of single spin Hamiltonian, which in a sense are all physically relevant. But yeah. Now, so this is second family of states. Actually, the family of states that I will be interested in. So let me jump already to the form of these states, and then I will tell you how we handle them, because there are some interesting technical, if you want, but even conceptual problems there. So what we want to do is that we want to represent again these high-dimensional wave functions. So instead of using factorizable or very easy, if you want, representations of the amplitudes, what we would like to do is that we would like to represent these wave functions with neural networks. Okay. Now I hear that you might not be familiar with tensor products, but you know neural networks, right? That's great. So what does it mean in practice? I mean, this is rather natural, actually, if you think about it for a second. But the idea is that we can construct a very general and flexible variational form that will allow us to represent these amplitudes. So these coefficients, if you want, psi k. Okay. So this is another way of rewriting my basis coefficients, ck. Okay. So these are all equivalent notations, or we can write them, for example, like psi of sigma 1 z, sigma 2 z, sigma n z. So these are all equivalent notation. I hope that you don't get lost in all these different ways of writing the same object. But again, just to remind you, I have my state psi that lives in this 2 to the n dimensional space, and I'm writing it as a sum of k that goes from 1 to 2 to the n of these coefficients ck times some basis state k. Okay, and I've told you that this k can be seen also, I mean, just as an integer version of all the possible combinations of sigma of the spin on all the electrons, if you want, on all the spins. Okay? So I told you that k equal 1, for example, corresponded to sigma 1 up, sigma 2 up, and sigma n up, and k equal to 2 to the n, where instead all the spins are down. Okay. So what I'm saying here is that what I will do is that I will represent these coefficients ck with a neural network. So I will use a neural network that will allow me to return the value of these coefficients on demand. So I give you a value of k, or equivalently, how the spins are pointing, if they're all up or down or in some random combination. And the output of the neural network should tell me what is the amplitude that the neural network is predicting that this state should have. Okay, so if you want, this is if you want, very simple. One thing that we can do is that we can say that this ck now, so these coefficients, will depend on the neural network parameters, theta, so the weights, the biases, and everything you have in your neural network. And for example, I can parameterize this with a deep feed-forward network. So just to introduce some notation, I could say that this is the composition of some nonlinear function g at layer d times some weights, some weight matrix w, times again some other nonlinearity g, and then I have some weights w, and then I have my g1, and then I have my w's, and then the input, if you want, here will be my sigmas, if you want, my vector of sigmas. Okay, So I don't know if this notation is clear or if you've seen it, but essentially this is another way of writing feed-forward networks from the input vector, which is in this case sigma, that again, in our case will be a vector of n plus or minus 1 or up or down or 0, 1, whatever you want. And then, I mean, this is the input layer. Then in the first layer, what I will do is that I will apply a linear transformation, so a matrix W, okay? And this will give me another vector. Then I will apply component-wise, so I guess this is what, this symbol here, in a nonlinear function that I call here G1. This could be your rectified linear unit, it could be your hyperbolic tangent, whatever nonlinearity that you have in your neural network. And then I apply on this vector another linearity, nonlinearity until I reach the last layer, that in this case is D. So I have D layers, if you want, in this notation. So, and also pictorially, I guess you've all seen this, but the input layer now will be this, again, binary variables, if you want, sigma 1, sigma 2, up to sigma n z, that can take plus or minus 1. Then I do my first layer of, I take linear combinations with some matrix and some nonlinearity, until I reach the last layer. So if you want, the only constraint that we have in this architecture is that the last layer must return a scalar, okay? So you see that these CKs, amplitudes, are just complex valued numbers. And the output, if you want, of the neural network, as I was anticipating, must be CK, or again, if you want, the amplitude of this variational state psi of theta given a given vector of inputs k. Yes?
I'm just wondering, so how do you produce complex value output?
Yes, I will come to that, I guess, in a second, because that's interesting. So just to give you the, so we did this already in 2016, and the original reference is this one, so that you can find. And it's what we call, what I call neural network quantum states. So neural network quantum states. So this is 355, okay, 601, 2017. Okay. Now, as I was telling at the beginning, in general, these complex, these coefficients, so these probability amplitudes are complex valued. This is again a postulate of quantum mechanics. I'm not telling you, why this makes sense, but it's been proven actually even experimentally that these coefficients must be complex and not real. Very recently, actually, it's a very recent thing. So it's really a fundamental thing of nature that these coefficients are complex. And what are we going to do about that? Well, you know that typically if you have a neural network with only real valued weights and real activations, what happens is that you can only produce real valued outputs. Almost by definition. So there are many possibilities. So how do we deal? So how do we deal with complex? Okay. So there are essentially two strategies. So historically, but okay, that's maybe. So the first thing that I did, for example, in the first paper was to do something that is natural for a physicist, but not for a computer scientist, which is essentially take the W, so the weights, if you want, in your neural network to be complex valued. Okay. So you can just take your weights to be complex valued. So your matrix now of weights is complex. You apply it on a real vector of inputs, which are these plus or minus 1, but then the vector is complex. So you see that if my G's, so if my nonlinearities are well defined in the complex plane, in the complex domain, then the output will be complex and there is no problem. Okay. There is the only issue that typically you can have poles in the complex plane because you can have divergences and other nasty things that you typically don't have at all. Instead, if you work with purely real weights and the purely real nonlinearities. Okay. So this is the first possibility. The second possibility is just to take two outputs. So typically, actually, what we do is that in most applications, we do not represent psi itself, but the logarithm of psi. Just a second. So we represent this log of ck, so the logarithm of this, if you want, of the wave function amplitudes, and we can represent them, if you want, as the real part fr of k plus I, right, imaginary part of k, and you can think that these two objects here are nothing but the two outputs of a neural network. So instead of having now a single valued complex output, I have a completely real network, so you can do whatever you like in terms of activation functions and weights. But instead of having a single output, I have two real valued outputs, and I interpret this as the real and the imaginary part of the logarithm of the amplitudes. Okay.
So in the first case, when you make your weight complex,
yeah,
like what would ReLU look like?
It doesn't look like, because indeed the ReLU is one of those cases that is not defined. You have to find a new definition if you want the ReLU. So something you can do. So for example, but this is not unique indeed. So for example, something you can do is that you can say that ReLU of Z, so a complex value, is something that is, for example, the modulus of Z should be equal than 0. So if this is, sorry, if the modulus of Z is larger than 0, then this is equal to Z, otherwise it's 0. So you do it on the modulus of the number, right? So if you want, you use the abs of the complex number, but this is not the unique definition. You could do it for the real part or the, I mean, there are many possibilities. Yeah, sorry. Right, yeah, sorry. Right, sorry. Yes, so greater than some constant delta, yes. Yeah, so you can think of this in the complex plane as essentially, if my number is inside this ball, then the activation is 0. If it's outside, then it will start spiking in this complex plane.
But you started at 0 at the border of the circle, like basically you haven't put a function value there yet, right? Like,
yeah, I'm saying that it's equal to Z outside of the border, or you can start to 0. Yeah, indeed there are many possibilities. Most of them are very empirical. I mean, there's no mathematical justification, not specifically. Actually, what we prefer to use, because they're a little bit more justified also from models that we can write with the hands if you want. So oftentimes we take G of Z to be things such as, for example, the log of the hyperbolic cosine for reasons that arise from the energy, from the Boltzmann distribution and other things. So these come from really from physics-inspired things. And these are all, you know, they are analytical functions, so there's no problem. You can define them very naturally. Yeah. And log cosh behaves a little bit like ReLU in the well, it's a symmetric ReLU in the real domain, so it's in a sense also a rather natural extension. Yeah. So the reason why we do that. Yeah. So in general, the states we are working with are not normalized. There are specific cases where we can make them normalized, but in general they are not. So as much as in machine learning you use models for probability distributions that can be either normalized or non-normalized, the same thing applies here. So we can either use models that are normalized or that are non-normalized. Yeah. And the reason why we model the logarithm is because typically these amplitudes can take a very large dynamical range of values, like probabilities. So this means that we want to represent things that have a probability amplitude of 10 to the minus 20 and something that has a probability of 10 to the minus 1. So doing that in a real space, not log space, would be quite inefficient Instead, in log space, it's much more natural. Okay, so this was the introduction that I wanted to do to neural network quantum states. So we have 15 minutes, right?
12 minutes.
Okay, great. Now, I mean, just to tell you something a little bit slightly more mathematical, but you know that there are some general representation theorems that apply to neural networks in general, and specifically also to quantum wave function, that tell us that essentially, so these are the works of Sibenko. I mean, have you seen this before in machine learning courses, or are you familiar? But essentially, there's this famous work by Sibenko from 1989, and before that, actually, I would claim that this was proven by Kolmogorov and Arnold. In 56, so before neural networks. So essentially, they prove, I mean, Sibenko proves that if you have a neural network that is large enough means that the number of units, so the size of this matrices W is large enough, you can describe an arbitrary, sufficiently smooth function. So specifically, this applies also to wave functions because they are nothing special. They are just, just another function. So this means that in principle, we can, by increasing the size of these networks, we can make more accurate approximations of our wave functions. So these kind of general representation theorems also apply to the case of wave functions. So there's no surprise there. Where, by the way, you have to be careful because it might be that in the worst case, the number of neurons, if you want, so the size of your network could be exponentially large, right? So that's the conservation of the bad luck, the no free lunch theorem. So essentially it tells you that in the worst case, indeed, if you want to describe the most general crazy random function, you need to take exponentially many neurons. There's no way out. But in practice, as you've seen from many applications nowadays of deep learning, we find that even modeling crazy complex functions, for example, that correspond to translating from Greek to Latin or from Greek to Japanese, then these can be modeled very efficiently, typically with poly size. So let's say millions of parameters, but not 2 to the 80, if you want, parameters like we would expect in our wave functions in general. Okay, so there's a hope that also in our case we could try to model our states with these smaller neural networks. And also, I mean, there is a result. Okay, maybe most of you are not familiar with this concept, but I just want to mention it about the entanglement. So you can show that these neural network states at the variance, for example, with respect to these product states, so this mean field wave function, they can capture entanglement among different parts of the system. So entanglement, in a nutshell, means that if I do something on my spin here on the left, the spin on the right can potentially feel what I've done to the spin on the left. Okay? Maybe you've heard about quantum teleportation and other things like that. So these are all based on this concept of entanglement. And they all boil down to the fact that the coefficients of the wave function are not factorizable. Indeed, that's the main, one of the main properties, requirements that you need to have. Instead, if your spins are completely independent, as in the mean field approximation, there is no entanglement. So I can do whatever I want to this one, but this other spin will not feel anything on far apart. So it's really key that instead I don't take a factorized form, but instead I put my correlations, if you want, inside my coefficients. And you can show, this has been shown in this paper that if you want, I can cite here. So Levin et al. This is a PRL Physical Review Letters 1225301, 2019. That, for example, if I have a convolutional neural network that represents my quantum state, okay, I can have something where essentially two spins very far apart can influence each other sufficiently enough if I take the depth of my neural network to scale like a power law of the number of spins. So in other words, if I take local filters, so filters that have a certain range of action, they only see range of vision, right? So they act only on neighboring spins or neighboring bits of information. Then in order to have this information propagate farther, so if I want to entangle, so if I want to correlate my spins here with my spin there, using a convnet without pooling operations, I need to have a number of layers that scales at least like the linear sides of my system. Otherwise, I will not propagate the information from here to there enough. Okay, so this is related again to this concept of entanglement. I will not have time to tell you much more than that, but yeah. Yes, so the other extreme is that instead you use a single layer if you want fully connected network where my W's now are not local, but they connect a spin here and the one on the moon, and that's completely fine. However, I mean, we know, and as physicists, we tend to prefer things that are more local. So in this sense, convolutional networks are quite natural also for physics applications because they act only locally on our degrees of freedom. But if you do that, then you have to go deeper. And that's how you want to go deeper. Okay, so this is my yes, sorry, yeah.
I'm wondering, for the neural network quantum states, if you wanted to train it, you would still need to iterate over like 2 to the n states.
Yeah, so this is the important part that I will tell you about in the next lecture. Yes, unfortunately, since I had to give a long introduction, I didn't have time today, but I will tell you how we can essentially go around this limitation of having to sum over all the expected, over all the states, because as you are correctly anticipating, so this will be our next problem. So evaluating this E of theta, if you want, for a given neural network. And you see that if I write E of theta, maybe, yeah, we can do this because we have still some time. So you see that E of theta, I mean, just I remind you the definition. So let me write this in terms of vectors now. It would be psi transpose H psi divided by the norm of my state, of my vector. Okay. But you can see that I can also write this now. So inserting completeness relations. So I hope that you are familiar with that. Okay. So let's say, so I can write this as sum over K of psi transpose, so conjugate. So I have psi star, if you want, of K. So psi of star of K now means C star of K. These are all equivalent notations, as I was mentioning. Then I will have the matrix elements of my Hamiltonian between states K and K prime that I sum upon times psi of K prime divided by sum of K psi K squared. Okay. So is it clear how you derive this, how you come to this from here? Hopefully. So you insert completeness relations, so identities. So if you want okay, just a second, because I mean, it's important. So essentially the identity for this 2 to the n space is the sum over K of these projectors here. Okay. So, and by using that and by inserting 2 of them, so one here and one here, I will have 2 summations on the full space K and K prime, and then I will get this expression. Okay. But as your colleague was correctly anticipating and foreseeing the problem, you see that in principle, if I wanted to compute this object exactly, I would need to sum over 2 to the n squared actually elements, K and K prime, and this is a problem. As we can start doing, we can do a little massage, if you want, to this equation and writing like this. So we write sum over K, and what I do now is that I multiply and divide by psi K. Okay, so I am now at the numerator. I multiply and divide by psi k. Okay, I can always do that, and I will tell you why it's not a problem if psi is 0 in a second. So if I multiply and divide, then I will have, if I multiply psi star with psi k, I will have psi k squared. You are with me, right? And then I will have this summation k prime, h k k prime, and then I have to divide again by psi k here. Okay? And then at the denominator, I have what I already had before, which is this summation of psi k. Okay? So I did a very simple manipulation. I multiplied and divided by psi k. But now you see that something very interesting happens, because I can interpret, if you want, this psi k squared with its normalization, which is this summation here, as a probability density. It is actually probability density. It is this Born probability density that I was introducing before. So you can see that I can write this as a summation over k over some normalized now, if you want, probability density p of k times this object. So sum of k prime h k k prime psi of k prime divided by psi of k. Okay. So I'm just defining, if you want, this object here to be my psi of k with its normalization. And now you can see that I can interpret this as the expected value, so E, over this probability distribution P of this object that you can see written here. And this object that you can see written here is what we call in jargon the local energy. So that will depend only on k, right? Because I'm summing up k prime. And that's where we now finally find the condition that I told you about at the beginning. And the condition that we were using was the fact that the non-zero matrix elements of H are only polynomially many. So if I fix k, and that's what I'm doing here, I'm fixing k and then I'm considering this object, then the number of k primes I have to sum upon in order to compute this local energy. So this object that is written here, this is the definition of the local energy. You see that the number of k primes now is only polynomial, so I don't need to do an exponential summation. So this means that if I'm able to compute expected values over this distribution, P of k, then I can compute also this E of theta efficiently, but just by statistical averages of this local energy. Yes?
Just wondering, so how do you get sampling access to P of k? Because I see how you get density evaluation.
Right, yes, so I will tell this the next time, yes. So so far I've only told you how to compute the unnormalized P of k if you want for an arbitrary k. Next time we will see strategies, and it's good that in the middle we will have a lecture on Monte Carlo by Dan, right? Forma, I think. No. Oh, okay. But you will have a lecture on Monte Carlo, right? Okay, that's great, because then you will know how to do this already, essentially just looking at this lecture. And then there are also other strategies, but the main strategy will be Markov chain Monte Carlo. Okay, so we generate samples from this P of k, and then we measure this expected value of this local energy. Okay, so this is the last thing that I wanted to tell you. The next time I will give you more details, because I mean I realize that I have been a bit fast on this, but yeah, please pay attention to the Markov chain Monte Carlo in the next lectures, and then all of this will be very natural the next time. Okay, thank you.